Hello friends, welcome back to the tetrahedron chemistry classes. So guys, as you know, I have already done an extensive lecture series on coordination chemistry, which is very important for your CSIR NET, GATE, IIT JAM examination, and as well as for JEE Main and JEE Advanced examination. So what I have decided actually, I'll take say somewhere around 150 questions, 150 brand new questions based on the various aspects of the coordination chemistry. And so it is not possible to actually complete that those 150 questions in one stretch. So I'll take a I'll make a series of these, right? So say in the first series I'll complete 20 questions, and in the second series then again I'll complete the 20 questions. This would be very helpful for your examination for the upcoming GATE examination and as well as for your IIT JAM examination. So be careful how and see. If you have learned all these concepts from my videos, then it would be quite easy for you to understand how actually I am solving these problems. However, I will also explain each and every concept related to the particular question. Okay, and see, if you check, say for example, I have say this particular question. Okay, so this question. Right, and this question is you can see it's a quite straightforward and quite simple question, and this question says that the coordination number, if you read this question from here, the coordination number of the metal ions in the following 4 complexes. So 4 complexes actually have been given to you, and you have to tell what is the coordination number of the metal ions in these complexes. So this is actually your first complex, which is your Ag H2O whole twice, right? So this is actually your first complex, and of course one chlorine is over there, and you know whatever the metal ion, whatever the ligands are present within this square bracket, they are actually the coordination number. So in that case 2 water molecules are there. So in that case the coordination number of your silver ion is 2, and similarly if you check your next complex, that is Fe H2O whole 6, right? And you can check here Cl2 is already there, and you know the iron in the center, and I has already told you other than the metal ion, right, whatever the molecules are there, they are the coordination number. So in that case the coordination number of Fe is 6. Okay, now if you focus in that particular problem, okay, again you can see 6 cyanides are attached, so the coordination number is 6 in that case. And similarly if you check this particular complex, within the square bracket you see the 4 ammonia molecules are there, so the coordination number in that case is 4. So your answer is what? 2, 6, 6 and 4. So this would be your answer. Now check in the given option. So 2, 6, 6, 4. So option B is the correct option for this question. Okay, and then we will take another question. Say this is your second question. What it says that the correct sets of the oxidation states of the metal ions given in the complexes, right? So you have given the complexes. Your first complex is Pt Cl4 and 2 negative is over there, and if you want to calculate, then it's very easy. X plus Cl having -1 of formal charge, right, and it times 4, and -2 is the overall charge on the complex ion, which is an anion actually. So your X would be equals to -2 plus 4, that will give you 2. So in that case your oxidation state is 2 for the first complex. So automatically you can see this cannot be your answer, because it is saying that the oxidation number of Pt is 6 in that case. It is not the case. And similarly this D cannot be your answer, because it is having the oxidation state of 2, it is saying 4. So you have to choose out of these 2. Now here you can see in the option B, it is saying that the oxidation state of platinum is -2, and here we have calculated the oxidation state of 2. So this cannot be your answer. So only correct option is what? option A is the correct option. So this is the short trick by which, see, this is how you can check the questions which one is correct or which one is not, because in your competitive examination you have to take care of the time also, right? But if you want to calculate the oxidation state of other metal ions given in the complexes, so you can write your second complex, which is CR NH3 whole thrice, right, and Cl3 is over there. And if you want to calculate, then you can put X for this one. You know ammonia is neutral, and times 3, and plus -1 is the ligand, times 3, that is Cl is -1, okay, and nothing is there, so you will put 0 because it is a neutral complex. So your X equals to 3. So in that case, your oxidation state for this chromium is +3. So it is also following +2, +3. Similarly, you can go for this one, like you are having, you have given this complex K3 Cu Cn whole 4, okay. So I can change the color, okay. So right, so if you ionize this particular complex, so you will get 3K positive, and then you will have CuCN, and over there 3 negative. Since the overall complex is the neutral one, if 3 cations are there, so to balance these, so you have to put 3 negative over there, right? And of course your 4 cyanides were already there. So if you want to calculate for this copper, so you can put X in place of copper, plus -1 is the formal charge present on your cyanide, times 4, because 4 cyanide are there, and this would be equals to -3, and that would be equals to X -3 plus 4, that will give you the 1. So in that case, copper is having the oxidation state of 1, and it is following just like that, okay. Similarly, you can calculate for this one also. Say this is your chromium, and this is your NH3 6 times, and Cl3, right. So if you ionize this particular complex, so you will get CH3, sorry, Cr NH3 whole 6, and then you will put 3 positive over there, because in the ionization sphere 3 chloride ions are there, okay. So you know X is in place of this chromium, plus ammonia is 0, times 6, it will not make any difference, equals to 3. So here you are getting the X equals to 3. So again, in this case you can see it is in +3 oxidation state. So your answer is just like that, 2, 3, 1, 3, right. So your correct option is this particular one, okay. Now moving to the next problem. Okay, you can see what is given here actually. You can see the number of the ions produced in the solution from the complexes. So you have given the complexes in that form, right? They are not given in the coordination compound form, but it is given in the some different form. For this you have to have an idea about the Werner's coordination theory, and if you have the idea of Werner coordination theory, only then you can solve these types of the questions. And also these questions are the memory based questions actually. If you have actually learned these questions and read these questions previously, only then you can solve it, right? So how we can solve this particular question? So I can write for this complex, this is CO Cl3 dot 6 NH3, okay. This is given to you, and you know when it forms a coordination compound, right? So it will form the complex just like that, CO NH3 CO NH3 6 times, and your Cl3 just like that. So if you ionize this particular complex, then you will get CO NH3 times 6, okay, plus 3 Cl negative. Since 3 negative are there, so you have to put 3 positive over there. So 1 ion is this complex ion plus 3 of the chloride ions, so it will give you total of 4 ions. So your first complex is giving total of 4 ions, right? So if it is giving the total of 4 ions, so that simply indicates that this cannot be your answer, because in my first complex I am having the 4 ion, and similarly this cannot be your answer, okay, because 9 ions it has given here. So you have to select between the option number B and option number D actually. So you can take your another complex, right? Say for example, I am taking this complex here, CO Cl3 dot 5NH3, right? And see, when it forms the complex, right, when this compound forms a complex, so it will form the complex in that manner: cobalt and 5 ammonia in the coordination sphere along with the 1 chlorine, just like that, and you have to put 2 Cl2 over there. So if you ionize this particular complex, so it will give you CO NH3 whole 5 Cl, it is the complex ion, okay, and 2 of the Cl negative. So you have to put the 2 positive over there. So 1 ion is this complex ion plus 2 of the chloride ions, it will give you the 3. So second is giving 3. So if you check here, it is in the option D, first 4 and second 3. So this cannot be your answer. So your correct option is the option D in that case. So if you want, then you can calculate for this one also. How you can calculate for this one? Say this particular complex, which is CO Cl3 dot 5NH3, okay, dot 1H2O, when it forms a complex, right, according to the oneness coordination theory, it forms a complex in that manner: cobalt and your 5 ammonia within the coordination sphere, okay, along with 1 water molecule and your 3 chloride ions would present outside. If you ionize this, okay, if you ionize this, then it will give you CO NH3 whole 5 H2O plus 3 Cl negative. So you have to put 3 positive over there. So 1 ion is this complex ion plus 3 of the chloride ion, total 4 ions. So you are getting 4 ions for the first one, and then you are getting 3 ions for the second one, and again you are getting the 4 ions for the third one. So 434 is the correct answer, which is this particular one, okay. Now moving to the next question to understand what is actually your cobaltous chloride, right. So cobaltous chloride is what? CO Cl2, right. You know your cobalt actually forms the +2 and the +3 compound. So if I am saying that the cobaltous chloride, so it simply means that CoCl2, right, and that CoCl2, if you put the aqueous solution, right, aqueous solution, the light pink aqueous solution of cobaltous chloride. So why it is light pink? Because if you dissolve this in water, so like the previous question, it would also form the hexaaqua complex, which is CO H2O times 6 and 2 positive, as we are saying that it is the cobaltous chloride. So it is light pink, and why it is light pink you will actually see in the transition part, actually DD transition, okay. In that case I have made a video on this, you can go through the lecture series. If you are watching the video for the first time, So what you can do, you can straightforward type the coordination chemistry by tetrahedron chemistry classes in the YouTube, you will get the result actually, right. So actually this is light pink. So if I want to write, then it is light pink. And what it says, it turns the deep blue on the addition of the concentrated HCl. So if you add the HCl to this one, so it turns blue. So what is the reaction? Say if you add HCl to it, hydrochloric acid. So it simply means that these chloride ions will replace the H2O ions and it will form COCl4, right, and it is 2 negative over there plus 6 of water molecule and plus H positive. Right? This is how you can take. So now you can think about the structure of this one. So coordination number is 4. So it may be your square planar, okay, or it could be your tetrahedral. TD I am writing for the tetrahedral. Since the size of the Cl negative ion, this particular ligand is quite large, so it is actually these chloride ions will actually try to take positions as far as apart to decrease the repulsion. You know, in the tetrahedral complex the bond angle is 109.5 degrees and in square planar complex the bond angle is 90 degrees. So in that case the bond angle is quite high, so the repulsion would be minimum. So this complex is actually your tetrahedral complex. So this is a trick you should know actually, how we can decide whether the complex will form the your tetrahedral or the square planar geometry, right. And when this ion is formed, actually it is deep blue in color. This ion is deep blue in color, deep blue in color, okay. So this is how you can understand. Now we can go for the next question, and what the next question says, you can see COCl2 in presence of the cobaltous chloride in presence of the ammonia solution on passing air produce an octahedral complex. Okay, what it says that you are having that this cobaltous chloride, okay. Say for example, you are having your COCl2, it is cobaltous chloride, okay. And see, you know, first it will form what, as I have made in the earlier question, CO H2O times 6 and you will put 2 positive over there. First of all, you will get this particular complex. Now if you pass ammonia, or if you put that complex in the ammonia and you will pass the air to it, right. So it will this complex will change in the hexamine complex NH3 times 6 and 2 positive, right. And this complex is actually you know this is actually 2 positive and in the ammonia environment actually, right. So in this particular environment it is very easily oxidized. So the oxidation would occur for this one, right, and it will form CO NH3 times 6. So in that case actually your say if you want to write, if I delete it, then you can write Cl2. Of course cobalt is in +2 and it will very easily oxidize to this particular complex where cobalt is having +3. So you can check which option is the correct. CONH3 whole 6 Cl3. So this cannot be your answer. This cannot be your answer, okay. Similarly you can see here, this cannot be your answer, okay. This one is your answer. Option D is the correct answer in that case. So this is how you can solve these problems. So guys, you can see this is my next question, and this question you can see it's relatively easy question, and you have to apply some tricks to solve these kinds of the questions, right? So for example, if you can take here, it says that the question says that predict the oxidation state of manganese. It should not be on. It should not be on. It is of manganese ion and the color of K2MnO4 and KMnO4. So it's quite easy, you know, your KMnO4 is what? It is purple in color. KMnO4 solution is purple in color, right? Aqueous solution is purple. So check the option where purple is given, in which option actually that option purple is given. So in that case you can see here, second should be your purple. So here actually purple is given here, so this could be your answer, right? But in that KMnO4 is given green, so this cannot be your answer. You know the KMnO4 is green, and neither it is pink, right? And it cannot also be your green. So by using this particular short trick, you can easily identify that the option A should be the correct option. So if you want to confirm that you have predicted correctly, so what you will do actually, you will check the oxidation state. So how you can check the oxidation state? Say for example, you have given this K2 MnO4. Okay. So what basically this is actually, it is nothing but your MnO4 2 negative ion. Okay, if you want to calculate the oxidation state of this one, so you can put X instead of the manganese, right? And you know the -2 is the formal charge on the oxygen times 4, because it is present 4 times, and this could be equals to -2, right? So that will give you what? X minus 8 equals to -2, that will give you the X equals to 6. So in that case the manganese is in +6 oxidation state. Okay, and if you go for the KMnO4, this is your KMnO4. If you ionize this, then it will give you the K positive plus MnO4 negative. Okay, if you want to calculate the oxidation state, then it must be X plus -2 is the formal charge on the oxygen present 4 times, and it will be equal to -1. And if you solve this, this will give you -1 plus 8, that is 7. So in KMnO4 it is in +7 oxidation state. So you check these options whether they are available or not in the given options. So 6 and 7 you have to check. So this is +6 plus 7, +6 plus 7. So these, see, +6 plus 7, +6 plus 7, these three can be the answer. But you know the color actually, right? This is purple in color, so option A is the correct option, right? Why it is correct, this one? Because +6 and +7 is matching, and you know the KMnO4 is the purple in color, right? And from here you will also know that K2MnO4 is green in color. Okay, so it's very easy to remember the color of the KMnO4, but it is little difficult if you haven't learned or you haven't read that the aqueous solution of K2MnO4 gives the green color, then it would be difficult. But you can apply some of the tricks to solve these kinds of the questions. Okay, now you can see here my next question, which is question number 8, and it says that the angle between the two tetrahedral units of Cr2O7 negative, it is a dichromate ion actually, right? So it is a dichromate ion. So I can write here dichromate ion, and this dichromate ion is formed by the two tetrahedral units. Then definitely if two tetrahedral units, that mean you are having that the chromate ion. Chromate ion. Now how we can form the chromate ion? It's quite easy. You know the chromate ion is what? CrO4 2 negative, right? This is your chromate ion, and the very famous salt of this one, what? Potassium chromate, K2CrO4. It readily used as an indicator when you determine the chloride content in the water sample. So it's an indicator actually, right? So in that case, if you want to draw the structure of this chromate ion, so it is tetrahedral, right? It is tetrahedral structure, and you will put chromium here and 4 oxygen in the 4 tetrahedron corners. Okay. And of course, you will put 2 negative over there. So, there is no need to put 2 negative. So, you can put 2 negative any of the 2 oxygens, right. So, this is actually the structure of the chromate ion, and the 2 tetrahedral unit forms the dichromate ion. So, how it can form the dichromate ion? So, for this, place the oxygen in the center, okay, and connect the 2 chromium atoms in that manner, okay. Dichromate ion, you can see here it is Cr2 O7 2 negative. Potassium dichromate is the famous salt which is used in the analytical chemistry very frequently, and then you can put 3 oxygens over there and 3 oxygens over there, okay, and 1 oxygen remain as such, and it is given in the literature. Do not forget to put 2 negative over there, and it is given in the literature. This bond angle is actually 126 degrees. So, your correct option is option B, right. So, this is how, but this is a memory based question, right, and you have to learn these types of the questions. It is very important, okay. And now moving to the next question, say in this question what is given here? The group of the monodentate ligands, right, which groups, which ligands are monodentate and which ligands are the bidentate, but you have to select the your monodentate ligand in that case, where the denticity is 1. That means the donor atom, the atom which will donate the electron pair to the transition metal, it should be 1 in that case. That is why it is written as monodentate, right. So, if you want to find that monodentate, so you should know some very important point. Say your monodentate ligands, what ligands are the monodentate ligands? So, I can write monodentate. So, in general, see, I have made an extensive lecture series on the types of the ligands. You can go through in the, and find in the YouTube in my lecture series, coordination chemistry lecture series, right. So, monodentate like your thiocyanide, right, and CS negative. So, sulfur is the donor atom only, right. So, it is monodentate. Then pyridine, you can take the example of the pyridine. Pyridine is what? You can put nitrogen over there, right. So, nitrogen is a donor atom. So, it is again a monodentate one. If you take NO2, right, it is also a monodentate one, because only one of the oxygen which will having the negative charge it will donate. Hydroxide ion, that means oxygen is donating, monodentate. Similarly, your SCN, here nitrogen is the donor atom. So, it is a flexidentate ligand, NCS, thiocyanide or isothiocyanide, okay. And then your cyanide, nitrogen is donating, okay. And if you have your methylamine like CH3NH2, so in that case your nitrogen is the donor atom. Similarly, your carbonyl, see, they all are the monodentate ligands, right. And if you go for the bidentate ligands, So, what are these bidentate ligands? So, basically actually they are ethylene diamine, which is generally written as En, and your carbonate ion is bidentate, right, because 2 oxygen atoms are there to donate electrons, right. And say if oxime is there, it is given here, it is also a bidentate ligand, right. Glycinato, right, glycinato, it is also a bidentate ligand. So, variety of the monodentate and bidentate ligands, and this question is again based on the memory and your practice, right. So, if you want to check here the groups actually which will form the monodentate ligands. So, you see this cyanide, if you check here, this cyanide is monodentate, SCN is monodentate, OH is, this could be your answer, okay. The glycinato is actually bidentate, so this cannot be your answer. Similarly, ethylene diamine is bidentate, this cannot be your answer, right. Carbonate is bidentate, so this cannot be your answer. So, correct option is the option number 3. So, option C is the correct option for this one. Now, moving to the next problem. So this is problem number 10, and what this problem says, it says that the hexa aqua iron 3 ion, right, complex, it forms a blood red colored complex on addition of thiocyanate. So it's a very, very simple question. How you can check? Say for example, you have given this hexa aqua complex, which is Fe H2O times 6, and then you will add the oxidation state, and if you put your SCN ions, thiocyanide ions, right. So any iron 3, right, if iron is in +3 oxidation state, right, if iron is in +3 state, as it is here actually. So it actually, what it does, it replaces one of the water molecule from here and take its position. So the complex which you will have H2O whole 5 SCN, this should look like N, right, just like that. And since 3 positive were already there and you have putting a negative ligand in the coordination sphere, so it will get 2 positive, overall 3 positive. Again iron is in +3 oxidation state here, also is in +3 oxidation state here. So this actually forms the blood red color, okay. So you can check the option, option B I think is the correct option in that case. So this is how you can understand, okay. And then moving to the next problem is the problem number 11, and what this problem says, the geometry of these complexes. Okay, this is quite simple. You see, you have given this complex, right, Ru di Py whole thrice 2 positive. So it's a dipyridine. Pyridine I already told you, nitrogen over there, and if it says the dipyridine, then a nitrogen somewhere here, that means it's a bidentate ligand. So when it is a bidentate ligand, right, see, please check the structure of this dipyridine by your own, okay. So I am assuming that this nitrogen actually presents at the 2 corners. So if you, okay, I can draw this again. So I am putting nitrogen here, I am putting nitrogen here, lone pair here and lone pair here. It's dipyridine, right? But please verify the structure by your own also. So it's a bidentate ligand, and you know the bidentate ligand, the denticity is 2. Then definitely if they are present in the 3 times, so you will multiply that coordination number with the denticity to get the overall coordination number. So the overall coordination number is 6, and you know the when coordination number is 6, right, when coordination number is 6, in that case your compound would be octahedral, okay. This is something very, very important. Now you are having next question, next complex, which is given here V O AC whole twice. This complex is given, okay. So this oxygen is present here. So what you can do, and what is this actually, this AC, this is acetyl acetonate. This ligand is acetyl acetonate, and it is also a bidentate ligand. It is also a bidentate ligand, okay. When it is a bidentate ligand, right, so that means to get the overall coordination number, you will multiply that 2 with the denticity to get the value of the 4, and 1 oxygen would present at the vertex. This oxygen is already there, it will present at the vertex. So this structure of this particular complex is what? Square pyramidal. Square pyramidal. So how you can get the square pyramidal structure? I can draw the structure for you. right? Say I'm removing these, okay, and then I'm taking my pen from here. So you will put your V in the center, right, and then you will put acetate, oxygen connected here, oxygen connected here, and all these things, oxygen connected here, oxygen connected here, and one oxygen here, right. So this is actually your acetyl acetonato, right. So it forms actually the square pyramidal structure. So your this should be your octahedral and square pyramidal. So check whether this option is here or not. See, tetrahedral cannot be your answer, tetrahedral cannot be your answer. These two you have to select in between these two. So if tetrahedral is the option, that means the coordination number should be 4, but the coordination number is 5 in that case. So your correct option is option D. Okay. So this is how you can check this one. Now moving to the next problem. Okay. And that problem, what it says that, so okay, I have to replace this. Okay. Now say, okay, so predict the correct set of the primary and the secondary valencies. Okay, you have to check the correct sets of the primary and the secondary valencies. So for this you have to actually write the structure for this one. Again, it's a basic question. PT NH3 times 4 Cl2 and another Cl2 over there. So secondary valencies actually are the coordination numbers. So whatever is present in the inside the coordination sphere, they are the secondary valency. So I am writing secondary valency. In that case, it is 6. And if you write this particular complex K4 FeCN6, okay. So again you can see here, sorry, I can put this here actually. So again you see this is the secondary valency within the coordination sphere. So secondary valency is 6. So check the option where the secondary valency is given 6 and 6, right? Check the options. So secondary valency 6 and 6, this could be your answer. 6 and 6, this could be your answer. Secondary valency 2, secondary valency 4, this cannot be your answer. Secondary valency 2, secondary valency 4, this cannot be your answer. Okay. So check the second part actually, this and this. I have calculated 6 and 6, so this could be your answer. 6 and 6, this could be your answer, but this cannot, these two cannot be your answer. Now go for the oxidation, primary valency. Primary valency is your actually the oxidation state. So if someone says that primary valency, okay, PV I am writing, so that means the oxidation state. So you know, if you calculate the oxidation state here actually, so put X in place of this platinum and ammonia is the neutral times 4 plus -1 is the formal charge on the Cl and times 2 and 2 positive over there. Why? Because this will actually have the 2 negatives. So overall, see if you ionize this, right, so it will get the 2 positive over there. So in that case your X equals to 4. So platinum in that case is having oxidation state of 4, right. So primary valency is +4 in that case. Now check the options here. So plus 4 is given here. So this would be your correct answer. Okay. So there is no need to go further. So this is how you can form the problems of your coordination chemistry. So in this case, I have solved only 12 problems, and I'll say, as I already told you, I'll daily solve per day. I'll solve 12 to 15 such problems, right? And then I'll complete that around 150 questions for this one, and this would be your practice for your coming examination. Okay, I hope you like the lecture. If you like the lecture, please share it with your friends and like the tetrahedron chemistry classes. And if you are new here, do not forget to subscribe the tetrahedron chemistry classes, guys. Okay, thank you very much. Hello friends, welcome back to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss another very important problem based on the coordination chemistry, right? And in this series, my first question to my today's first question is, you can read the question, the magnetic moment values for the complexes, right? You have been given two complexes. First is your this cobalt, and in that case, you know, your cobalt ion is in +2 oxidation state, so you can put 2 positive over there. And then you have given the second complex, and in this particular complex your cobalt is again in +2 oxidation state. So you have to decide you have to calculate the magnetic moment for this one. Okay, so if you see this particular complex, I can write the formula here, right? You are having COCl6, this complex you are having 2 positive over there, sorry, not 2 positive, sorry, 4 negative is there. Okay, and obviously it will have cobalt is in +2 oxidation state, and when cobalt is in +2 oxidation state, it's simply a 3d7 system. Okay, so it's a 3d7 system, and you know this Cl is what? It's a weak field ligand. It's a weak ligand. When it's a weak ligand, definitely the complex would be high spin complex. Okay, that would be your high spin complex. What is the meaning of the high spin complex? When the crystal field splitting occurs in the octahedral field, so you have to fill your 7 electrons in it. 1, 2, 3, 4, 5, 6 and 7. So you are having total 3 unpaired electrons. Okay, you are having 3 unpaired electrons. So for this for these 3 unpaired electrons, if you want to calculate the magnetic moment, that would be equals to mu under root of n into n plus 2. Okay, now if you put the value of n equals to 3 in the equation, then you will get 3 plus 2, 3 to 5, 5 is a 15, that means under root of 15, and if you solve this particular value, then it will give you 3.87. Okay, of course the unit would be Bohr magneton. So this is the case for this your cobalt complex. Okay, for this particular one, check and see, this cannot be your answer, this cannot be your answer. Out of these two, one would be correct in that. Now you can go for your next question, next complex. Okay, and your next complex is given in that manner, which is CO CN5. So in that case, you can see the 5 cyanides are there along with this water ligand. Okay, and you know, in that case, when you see this cyanide is the strong ligand, I am writing SL for the strong one, and this is a weak ligand. So the number of the strong ligands are much higher than the number of the weak ligands, so it would be a low spin complex. Okay, so what is the meaning of the low spin complex? Again, you can see the cobalt is in +2 oxidation state if you do the crystal field splitting in it. So you have to fill 7 electron now in these available orbitals. How you can put the 7 electrons in it? 1, 2, 3, 4, 5, 6, and your 7th electron would be here. Okay, now if you apply the formula to calculate the magnetic moment, that means n into n plus 2. Okay, this will again give you what? Only one unpaired electron is there here, you can see. So you can write 1 into 1 plus 2, it's simply under root of 3, and under root of 3, you know, it will give you somewhere around 1.73 Bohr magneton. So you can see the option C is looking the correct option in that case. So you can mark this option C as the correct option. So this is the first problem. Now moving to the next problem, what it says, spinal structures of these two spinals are given to you. So I have solved a problem based on this in my last lecture, but I am giving you a little trick here. Say for example, you are having, not trick actually, it's a clear cut concept. What happens in the normal spinal, and then what happens in the inverse spinal. You should know these things. See, in that case, your bi-positive ion that would go into the tetrahedral voids, okay, and your tri-positive ions, say B3 positive, they'll go to the octahedral voids. This is the case of the normal spinal, okay. And in that case, of course, the CFSE, crystal field stabilization energy, of your B3 positive ion, that means whatever the tri-positive ion would be there, they would be actually greater than the CFSE of A2 positive ion. Remember, both in octahedral fields, okay. So this is also in octahedral field, this is also in octahedral field, this is, you know. And if you invert this, right, so what you will get here in that case of inverse spinal, so your A2 positive, it will go into the octahedral voids, and your B3 positive ions, it will go into the tetrahedral voids. If you calculate the CFSE, so definitely your CFSE of bi-positive ion in octahedral field, okay, would be greater than CFSE of tri-positive ions, both in octahedral fields, okay. These things you should remember actually, right? So if you apply the same formula, so for normal spinal, you can give this formula for normal spinal. I can write here A in the tetrahedral voids, okay, and your B2, they would be in the octahedral voids, and of course here oxide ions would be there. This is how you can check. Now you can go for this particular example. You are having COFe2O4. In that case, you can see basically this CO2 positive. In that case, you know, the first ion actually which is given here, it is 2 positive. This is cobalt 2 positive, and it is quite stable in the octahedral environment. Okay, it is stable in the octahedral environment. So your bi-positive is going into the octahedral environment, and you see that it is bi-positive is going into the Cu2 positive is going into the octahedral environment. So it is a inverse spinal. So this is your inverse spinal. Now moving to the next one, say in that case, if you check here, this is actually the very special example, and this is actually exception one. This is hercyanite. This spinal is hercyanite. In that spinal, you see here, see if you compare your Fe2 positive, this is 2 positive, and aluminium is your 3 positive, okay. So in that case, you see in the last lecture also I told you this Al3 positive has a special affinity for the octahedral side. So it is going into the octahedral side. Your tri-positive is going into the octahedral side. When tri-positive is going into the octahedral side, you can see here, so it should be a normal spinal. So this harnesite is a normal spinal, okay. So this is how you can solve the problem. The first one is your inverse, second one is your normal spinal. So option B is actually looking the correct spinal. In that case, you can solve. But this harnesite is a very this example is a very famous example. It is an exception one, okay. Very important one. Now moving to the next problem, what it says, the incorrect statement about the polydiamide. So guys, if you see, this question is again based on this is based on the memory. This is memory based question. So to solve this question, actually you need to know the structure of your polydiamide spinal, okay. It's a kind of the spinal, okay, or say it's a mineral actually, right. And this mineral is having the formula in which your nickel is present in 2 positive ion, and also your 2 nickels are there, right. It is in 3 positive ion, and it's a sulfide. It's a sulfide mineral. So first you check the first statement. it is a sulfide based spinel, true. Okay, nickel 3 ion is not stable in the sulfide environment, this is false. Okay, this is false. Why? You see, nickel 3 positive ion is here and it is forming this polydiamide in the sulfide case. That means it is stable, that's why it is forming this particular compound. So second statement is actually your false and it is the correct answer in that case. Now if you want to move further, nickel exists in both +2 +3. Yes, it is true. In polydiamide, nickel 2 positive, nickel 3 positive are there. It is an EPR active. Definitely it is an EPR active. And you see, if you are having the nickel 3 positive, right, you are nickel 3 positive, it's a 3d7 system. And when you have the 3d7 system, so it will have the unpaired electron. And all the species which are having the unpaired electron, they are EPR active. Okay, so this is EPR active. This is also true. So this one is also true. So only incorrect answer is the option number 2. So you can mark this option B as the correct option, but it's a important problem. Okay, now moving to the next one. The calculated magnetic moment of this particular complex, which is given here, is this one, which is different from the experimental. Okay, in that case the experimental magnetic moment is 4.40 Bohr magneton, but calculated magnetic moment based on your say number of the unpaired electrons. So it is having, actually you see the 3 unpaired electron. This complex is having 3 unpaired electron. Okay, see, in that case cobalt is in +2 oxidation state, and when cobalt is in +2 oxidation state, that means it is having the 3d7 system. Okay, so it's a 3d7 system and it's a weak field ligand. And in the weak field ligand, if you fill the electrons, weak field 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3 and 3 unpaired electrons are there, which results in the 3.87 Bohr magneton. I have calculated this in my first example. Okay, first problem I have solved this particular one. And then experimental moment value 4.4, it is found at 4.40. So remember one point, whenever your experimental magnetic moment is higher than the calculated one, it's simply due to the contribution of the orbital magnetic moment. So you can blindly mark in that case the option number C as the correct option, contribution of the orbital magnetic moment. It is something very, very important. Okay, see, T2G is unsymmetrically filled, and definitely this unsymmetrically filled orbital motion will contribute to the magnetic moment, and this will give you the higher magnetic moment than 3.87. Okay, now moving to the next problem. The molar, again this problem is based on your memory. If you have learned the magnetic properties of the complexes in pretty much detail, only then you will be able to answer this one. Okay, now you see what the question is asking actually. The molar magnetic susceptibility value for the larger multiplate, it is saying that for the larger multiplate, width compared to the KT is given by the equation. So this question is memory based, and I am telling you, see, whenever your multiplate width is greater, right, when it is greater, which is given here, okay, in that case actually the L and S coupling, LS coupling would be very, very strong. These vectors actually very, very strongly interact. Actually the interaction between L and S will be very, very strong, and when this happens, when the strong coupling between this L and S occurs, then your J actually, right, this rotational quantum number becomes very, very significant. Okay, and you see the J becomes very good quantum number in that case, and your quantum numbers L and S actually they will not dictate the ultimate magnetic properties. So magnetic properties would be decided by the J value, not actually by LS, because they when the multiplet width is greater, they are strongly coupled to produce this quantum number, and this will decide the magnetic property. Okay, and in that case actually what will happen, actually the molar magnetic susceptibility value in that case would be given by this particular this particular formula. Molar magnetic susceptibility, that is xm or the chi-m, whatever you want to say, that would be equals to n mu square J divided by 3 of KT. But again this problem is based on your memory. Now moving to the next problem. The spectroscopic term for symbols titanium 3 positive ion and chromium 3 positive ion. See guys, this problem you can see here, I can This is titanium 3 positive, and this titanium 3 positive simply means it's a 3D 1 system. Okay, it's a 3D 1 system. So how you can fill the electrons in it? 1, 2, 3, and say this is 5, 1, and this is 1 electron which is present here, and you know the value of this is +2, this is +1, 0, -1, -2. This goes in that manner actually, right? And only one unpaired electron is there. That means simply you can have your spin of half. Okay, and you know your electron, see I can write here S, P, D, F. So L value 0, 1, 2, 3. This goes in that manner actually. So when see your L value actually is 2 in that case actually, right? Yeah, L value in that case is 2. You can see here. Okay, so it is in the D orbital. So it simply means your capital L value is 2. Now you have the two values. Value number 1 the spin, value number 1, 2 is L. Now you want to know the J value, and when this happens, you know this this D orbital is less than half filled. So in that case actually J value would be calculated by L minus S. Okay, so your L value is actually 2. Okay, and you are minus this value from this one. So this is actually giving you the 3/2. So J value is 3/2. Now if you want to calculate the term symbol, okay, so what basically the term symbol is? Term symbol is that spin part which is 2s plus 1, okay, and the value of L and the value of J. So 2s plus 1, if you see here in that case the spin, if you want to calculate the spin for this one, so how you can calculate? S is equals to 2s plus 1, 2 into half plus 1, that will give you 2, 2 gets cancelled, so you will have the value of the 2. So it simply means 2, and L value is 2, so it is in D, so you can write D here, and J value is 3/2, so you can write 3/2. So for this titanium ion the value is actually 2 D 3/2. Check the option which is the correct one. So you can see the option D, it is given here. So you can blindly mark this as the correct option, and there is no need to calculate for this one, but if you want to calculate for this one also, so you can calculate for this ion also. You are having, say in that case your chromium in 3 positive state, and when chromium is in 3 positive state, it simply means it's a 3D3 system. It's a 3D3 system, and if you put 3 electrons in it, so this is 1, this is 2, this is 3, and I already told you this is +2, this is +1, and this is the 0. Okay, so L value in that case you can see here +2, +1, +0, that will give you the 3. So whenever this L value is 3, it belongs to the L value of F. You can see here this is F. Okay, so F is given here, and your spin you can see it is 3/2, because 3 unpaired electrons are there, 1, 2, 3, and they are having 1/2. So basically it's 3/2. Okay, and if you want to calculate the J value, so again you can find that J value, L minus S, and this will give you your 3 minus 3/2, right? And this 3 minus 3/2 will give you again the 3/2. Okay, so in that case you can see the value if you apply this formula again here, this particular one. So your spin would be in that case, how you can write? 2s plus 1, capital S equals to, so 2 into 3/2 plus 1, that is equals to 4. So your spin is 4, electron is present in F orbital, you can see here, right, F1, and 3/2 is the this particular J value. So this is the symbol. You can see, you can calculate for this one also, but nonetheless it's a very important problem, good problem to solve. Now moving to the next problem, what it says that is the state the magnetism of your two complexes, right? So guys, this is a very simple problem. In that case you can see the iron is in +2 oxidation state, and in that case again iron is in +3 oxidation state, but you know this NO2 is a strong ligand. It's a strong ligand, When it is a strong ligand, that means it is a low spin complex, and when it is a low spin complex, that means it should be low spin complex are diamagnetic in nature, because all the spins are paired in that case, so it's a diamagnetic. Okay, so you can check the option. This cannot be correct answer B, this cannot be correct answer C. You can opt from A, out of A and D. Now moving for this one, this fluoride is the weak ligand. Okay, and when this is a weak ligand, so it's a high spin complex. And high spin complexes, actually they are having the unpaired electrons, so they are paramagnetic in nature. So second complex is paramagnetic. So you can see the option A is looking the correct answer in that case. So you can mark the option A as the correct option. Now moving to the next problem, what it says that, you see for water gas shift reaction, the spinel based catalyst. Again, see this guys, this problem is based on your memory. If this question is in your memory and you have actually learned this theory several times, only then you can you will be able to solve this particular one. So in that case, see basically iron chromite in that case, right? In that case, your iron chromite, right? More specifically, iron 2 chromite. Okay. This is actually the catalyst, okay, which this actually catalyst is used in the synthesis of your hydrogen from the reaction between the carbon monoxide and the water vapor. So again, you can see, you can blindly mark the option number C. If you have learned, if you have read this question several times, only then only then you will be able to solve this one. Now moving to the next problem, what it says: addition of orbital magnetic moment to spin moment is possible. Okay, see, though I have solved a problem based on this in my earlier lecture. So basically, if you are calculating the magnetic moment, okay, and you are having the spin only moment, that is the value which comes from the mu, by using the formula that under root n into n plus 2. Okay, this, you know, this would be calculated as under root n into n plus 2. Okay, so when your orbital magnetic moment will contribute, okay, and will add to this value, what are the conditions required for this one? Okay, so you can blindly mark, you can see option D. See, unrestricted movement of the electron is allowed from one orbital to orbital. Yes, it's true. When electrons are free to move from here to there, then definitely they will add to the magnetic spin only magnetic moment. Okay, orbitals are degenerate. This is something very, very important. This is also true. Okay, when orbitals are having the same energy, then the electrons can move very freely here to there and they can contribute to the spin movement. Again, it is true. Orbitals are of the same shape. Definitely when the shapes are same, the quite good overlap would be there, and due to this overlap, your electrons can move from here to there. This is also correct, right? So all options are true actually in that case. When all are true in that case, that means option D is the correct answer. Now moving to the next problem, what it says that, that is here the spin only and spin plus orbital moment. See guys, again it's a very, very simple problem. Okay, I can solve this particular problem. Say for example, first of all, it is asking the spin only formula. Spin only formula I have just given you. It will give you under root n into n plus 2, and your chromium is in plus 3 oxidation state. It simply means it's a 3D3 system, and 3D3 system means it is having 3 unpaired electrons. 3 unpaired electrons. Okay, that mean 3 into 3 plus 2, that mean under root of 15, and under root of 15 will give you 3.87 Bohr magneton. Okay, so your this option cannot be correct, and this option cannot be correct. So you have to select between the A and the D. So now your orbital contribution would be there. So how actually the orbital contribution would be there in that case? So whenever the orbital contribution, you are looking for your orbital contribution, so simply you can write mu L plus S. S you are simply this spin, okay, and L is actually your orbital contribution. So for this you will use this particular formula, under root of L into L plus 1, okay, and this should be your 4s plus 1. Okay, so 4s into s plus 1. So this is the formula, right, which goes in that direction. So if you solve that particular problem, so basically it is your this system. This is +2, this is +1, this is 0, okay, and this is -1, -2, and you are having 3 electrons in it. So you can place 3 electrons, 1, 2, 3. So your L value, if you want to calculate, that is 2 plus 1 plus 0 equals to 3, and this value, L value, is 3, so you can write 3 here actually, right? So if you want to write the 3 here, so how you put those values in that case? So you can write in that manner: 3 multiplied by 3 plus 1, there is no problem, plus 4, then you spin, you see 3 unpaired electrons are there, so spin would be 3 by 2 in that case, okay. So you can write 4, okay. So you can write 4 into 3 by 2 and 3 by 2 plus 1. So I am not going to solve a mathematical step in it. So if you solve this value, this will give you value somewhere around 5.20 Bohr magneton, okay. When this, you can check the option 3.87 and 5.20. So option A is looking correct option, so you can mark this one, and this is the wrong one, okay. Now moving to the next problem, what it says: the strong field nature of CO over cyanide is okay guys, this problem is quite simple, right? And this is again a theoretical problem. You can brandly mark LFT, ligand field theory. So VBT you have studied, it deals with the hybridization of the complexes, so it is not giving this idea why the CO is actually strong field than your cyanide. Similarly, molecular orbital is something different. Crystal field, you know, so you may have the confusion between B and C, but you have to select the C. So guys, see, according to what happens in the ligand field theory, actually this ligand field theory actually explains the ligands of the nature, right, through their orbital symmetry, and what happens through overlapping integral approach. See, both carbonyl and cyanide, they are good pi acceptors, you know, whether this one or this one, they are very good pi acceptor, okay. Why they are pi acceptor? You know, carbon triple bond oxygen, and you know they are having actually what, pi antibonding, pi empty antibonding molecular orbital. They can accept the electron from the metal from it, so they are actually they can form the back bonding from the metal actually, okay. They are the acceptor one. But you see, if you compare your carbon and nitrogen, as in case of the cyanide, okay, they are very closer in energy. Their energy is very similar, closer in energy, I can write for this one, okay. And if you see carbon and oxygen, there is very vast electronegativity difference. Electronegativity difference. Sorry, my handwriting. Sorry for my handwriting. It is electronegativity difference. Electronegativity difference is very vast in that case. When this happens actually, so there is no more. See, there is more mixing. No more actually. There is more mixing of your pi antibonding orbital with cyanide, because they are the closer in energy actually. When they are very, the mixing is very in that case very high. So what happens actually, metal d orbitals donates the electron density towards the ligand, and there is less mixing. That means less mixing means a weaker pi bond between the metal and the cyanide, right, when compared to this one. So this is the theoretical idea about this one, okay. So you can learn the theoretical theory, but you can see this actually ligand field theory gives this idea actually, okay. Now moving to the next problem. Gauss balance can directly measure, okay. Now this again, it's a very simple problem based on your memory. If you have read this magnetic susceptibility experiment, only then you will be answer to this one. So Gauss balance actually directly determines the gram magnetic susceptibility, okay. Now moving to the next problem, what it says: among the following most strong sigma donor ligand, okay guys. So this is again, you see the very simple problem, and option C is the correct option in that case. Why option C is the correct option? You can see in that case, right. See, they are it is positive, that means electron deficient, so they cannot donate electron very much strongly, okay, because they are electron deficient. But you see, this is having the negative charge, and these two are also having the negative charge. But you see, the chlorine is more electronegative and your nitrogen is also more electronegative. So they are very reluctant to release their electrons for donation actually, right? So they cannot be the very good donor. So what option you left? You were left with the option 3 only, because these two, they are having the lone pairs actually. So they cannot be donated very much easily, right? So this is how you can answer this particular problem. Again, see, it's a theoretical problem and this is the intuition based question. You can solve such questions by your intuition, and your intuition comes from the experience by solving the more and more problems and by reading the problems again and again, different kinds of the problems again and again. Now moving to the next problem, what it says. Okay, let me reorient this. Okay, in that case, the question says the pi acceptor ligand which is separation is considered as delta O. See guys, again this problem is based on your ligand field theory. If you haven't learned the ligand field theory in the detail, I have made a detailed 4 lecture on the ligand field theory. You can go there and learn how you can then after learning that ligand field theory, you will be able to solve such kind of the problems. Okay, so in that case actually what happens, right? See, if you are for the pi acceptor ligands, right, the ligands vacant pi orbitals have higher energy in comparison to the metal T2G orbital. So metal T2G orbital, say for example, I am solving this one. You are having the metal, right, Mn positive I am writing, and it is having the T2G orbital. Okay, in that case, right, and your pi acceptor ligands, they will actually have very high energy. So if you see the energy is going in that manner, so this is the energy for the T2G orbital, and for pi acceptor ligands, energy is somewhere here. So this energy difference is quite large energy difference. Okay, so consequently what happens, the metal T2G orbital, right, they are which are lowered in energy, they are lowered in energy after the formation of the pi bond. So once they form the pi bond, so their energy actually goes down. Okay, so in that case your delta O will have the greater value in that case. Okay, and when delta O is having the greater value, that means it simply implies that the transfer is taking from transition is actually separation is given by the T2G to EG antibonding. So option B is looking correct option in that case. Okay, so see, if you see, once again you can listen properly. For a pi acceptor ligands, the ligands vacant pi orbitals have very high energy in comparison to the metal T2G orbital. Consequently what happens, the metal T2G orbitals are lowered in energy after the formation of the pi bond only, and when this happens actually delta O is now greater in the value, and when delta O is greater in the value, it corresponds to the this kind of transition T2G from EG, right? So electron will transfer from here to here. Okay, this is the option, but this is a theoretical question. Now moving to the next problem. Problem number 7, the temperature below which spins are aligned anti-parallel in the domain is known as, it's simply you see, when you solve this particular problem, it's a Neil point actually. So I can write here Neil point. I hope you know what is the Neil point. I have made the extensive lecture on the magnetic properties of the complexes also. You can find the Neil point there actually. Okay, so see, you can see if I want to draw a diagram from here, so it gives this kind of thing. See, this is your molar magnetic susceptibility. Okay, and this temperature is the Neil temperature, which I am writing as the Tn, right, and this corresponds to here, and it is actually for anti-ferromagnetic substance, anti-ferromagnets. Okay, so the anti-ferromagnetic compound shows the paramagnetic properties above the Neil point. Okay, so whenever you have the anti-ferromagnetic compound, anti-ferromagnetic complexes, okay, and there see if actually needle point crossed, if they cross the needle point, then they show the magnetic paramagnetism. So here temperature, actually temperature in Kelvin scale. So the antiferromagnetic compound shows the magnetic properties above the needle point. So your option D is looking in that case the correct answer. You can mark this one. Now moving to the next problem. For a complex with pi donor ligands, increased pi donation stabilizes. So again you guys see this problem is a theoretical problem, okay, and you can simply see this one. I have solved this particular problem in my last lecture, in my, see if I go back further, you can see here I have explained, right? So T2G when actually gives the electron to, they lower their energy. So actually this question is a more or less same kind of the question, and option A. So for a complex with pi donor ligands, the increased pi donation stabilizes the T2G level. Okay, now moving to the next problem. Again this value is based on your learning capacity, or based on your memory actually, right? And it's a very simple problem. Your mu B values can be calculated by molar magnetic susceptibility values actually, right? So basically it's a momentum and your magnetic susceptibility, how the magnetic susceptibility and the magnetic movement can be correlated. It's simply a Curie's equation basically. It's simply a Curie's equation. So if you know the relation between the Curie, if you know the Curie relation, then you will be able to answer that it is the part 1 actually, right? This is your Curie's equation. Again see, it depends on your memory. Now moving to the next problem. Types of the orbital might be seen in n double bond Cr2 bond of a Schiff base ligand. Okay, it is having everything actually, right? This is having everything. It is a double bond. You consider one double bond as sigma and other double bond as pi, and nitrogen is there, so lone pair is there. So lone pair, pi bond, sigma bond, all are there. It obviously your correct option is your option number C. Okay, now moving to the next problem. The ligand orbital symmetries that are matched with the metal orbital symmetry in the symmetries in the octahedral complexes are. So guys, this problem is based on ligand field theory. Okay, if you have learned that ligand field theory correctly, then obviously we will answer that your T1U would be T1U and T2G. They are ligand orbital symmetry in that case. Okay, so what it means actually, see, if you want to know, if I am saying that T1U, U stands for the ungyrate, so orbital which are not having the center of symmetry. So which orbital will not have the center of symmetry? Obviously your Px, your Py and your Pz. Okay, say wait, what I can do, I can delete them all. Say this is my Px, this is plus, this is minus. Okay, then this is my Py, this is plus, this is minus, and say this is my Pz, this is plus, this is minus. So it is they are not having the center of symmetry, that means they are the ungyrate one. First of all, you should remember this thing. Okay, and when I am saying that the T2G orbitals, so T2G orbital means dxy, dyz and dzx, they all are having center of symmetry, that is I. So quickly you can see here, say this is your dxy, so this is plus, this is plus, this is minus, this is minus. So if you move from here to here, so you are finding the positive, and again you are finding the negative. They are having the center of symmetry in that case. So your T2G actually is your dxy, dxz, dyz, and T1U your px, py and pz, and your T1G and T2U group, they are these groups of orbitals, for the ligands, they don't match with the symmetry of any kind. So basically, you see this and this, they cannot match the symmetry of any kind. So you can cross them all. Okay, this one, and T1G, T2, both are G-rad, not possible, and G-rad and G-rad, this is not possible. G-rad and G-rad, G-rad, this is not possible. So option C is the correct option. But again, see, it depends. It actually based on your memory. If you had learned the ligand field theory in detail, only then you will be able to answer such questions. Otherwise, it is very difficult to answer such kind of the questions for you. Now, moving to the next problem, what it says. Tetracarbonyl nickel complex, the sigma donation and the pi acceptance occurs utilizing the ligand's molecular orbital. Again, you see it's again the problem based on your molecular orbital theory, or you can say the ligand field theory. Again, see, it's a memory based question, and if you learn those things, then it is quite easy, right? It would be easy if you have already learned these things, right? So what happens? Later on I'll reply with the correct answer, or see, after giving a one statement you will be able to mark your own, right, the correct answer. The sigma donation takes place from the ligand's sigma orbital, right, ligand sigma orbital, and the pi acceptance takes place in the pi antibonding molecular orbital. So in that case, you can see this is looking the correct one. Okay, sigma donation, so this sigma bond, okay, filled sigma orbital, and see, pi acceptance whenever you having the empty pi antibonding molecular orbital. Okay, now moving to the next problem. In presence of pi donor and pi acceptor ligands, the energy of the metal T2G orbitals gets, okay, this problem I have already solved for you. Okay, in that case, the energy of the metal T2G orbitals gets, so whether increased or decreased, what happens in that case, right? So there may be the two cases. Say whenever you have the pi donor, that means in that case actually the metal's T2G orbital will increase. And in my few slides back I already told you, whenever your pi acceptor ligands are there, so metal T2G orbital donate electron to this one. Okay, and when this donation occurs, so the energy of the T2G orbitals gets lowered. I have solved this problem 2 times, right? So the energy of this decrease. So this should be decreased, this should be increased. Okay, so option A is looking the correct option in that case. Okay, I'm not going to draw the diagram for this one, but I am giving you the idea how to visualize the things actually. Okay, this cannot be your answer because you have learned this cannot be your answer, this cannot be your answer, you left with only this one. So at least if you don't know about your pi donor, okay, and then definitely for this pi acceptor you have idea when pi acceptance occurs through the metal T2G orbital, so the metal's T2G orbital's energy gets lowered actually. In that manner you can answer this particular question. Okay, but again it's a very important question. Now moving to the next problem, what it says, the power of the, okay, this question actually is from the kinetics. I don't know why it is here. So definitely it is there from the reaction mechanism part. Okay, and you can simply mark this option A as the correct option. The power of the reactant concentration in the differential equation. So this is the question of your kinetics actually, not directly from your coordination chemistry. Now moving to the next problem. The amount of energy delta O for an octahedral complex in pi donor ligand field. Again guys, you see, if you have learned that ligand field theory, then it is very easy to answer, otherwise it is quite difficult. So see, listen carefully what I am trying to explain in that case. Okay, see, it is not possible to possible for me to write each and everything here, but you can listen carefully what I am trying to explain actually, right? So basically the value of the delta O, okay, in an octahedral field, definitely when I am writing O, it is for octahedral field. Okay, so the value of the delta O for an octahedral complex in the pi donor ligand field is smaller, okay, than the value of the delta O in the complex of the only sigma donor ligand field environment. So you can have two environment, sigma donor ligand Okay, and then you are having next is your pi donor ligand. So you can have these two environment, pi donor and your sigma donor. So what will happen in case of the pi donor? So the ligand field is smaller. Okay, in that case this value is smaller. Okay, and see, in case of the pi donor ligand environment, the energy of the ligand orbital is lower. So ligand's orbital energy would be lowered. Okay, because these are the filled orbitals actually, that's why it is lowered in nature. Okay, and the separation between T2G antibonding and EG antibonding, they are very low also. So only this much I can write here actually, right? So based on these three things, you can blindly mark delta O is greater. No, I am not saying that it is greater. I already told you it is lower. Okay, so this cannot be your answer. C can be your answer, D cannot be your answer. So in pi donor ligand environment, delta O would be smaller than the delta O in the complex and sigma donor. So this actually option C is looking the correct answer in that case. But again, you see, this question is based on your theory actually. Now moving to the next one. Which of the following sets of the orbitals is responsible for the T2G symmetry? Guys, it's quite simple problem. So there is no need to waste much time in this. dxy, dyz, dzx. See, G stands for G-rad. G-rad means the orbitals must have the center of inversion or center of symmetry, that is I. And you know this, they are not having the I. They are also not having the I. They are not also having the I. But dx, dy, dz, they are having the I. See, I told you here. See, if I go back, somewhere I solved this, right? This example you can see here. Okay, this one I have solved you dxy, dyz, right? So correct answer is in that case is, sorry, right, this option D is the correct answer in that case. Now moving to the next problem, what it says, the reaction of the blue colored hexa aqua copper 2 ion with ammonia produces the octahedral complex more intense blue. Okay, this is simply a substitution reaction. It's simply a substitution reaction. Okay, and you know what happens actually. See, when you say, I can write the reaction here. Say you were earlier having CuH2O times 6, 2 positive is there, and you are reacting this with ammonia. So this ammonia will substitute one of the water molecule, 2 of the water molecule from there, sorry, 4 of the water molecule from there, and you will have Cu NH3 times 4 and 2 times of H2O, copper is in 2 positive, plus 4 of H2O. This is the complex actually, right? So, and this is the example of your substitution reaction, where actually 4 of your ammonia substituting 4 of your water molecule. Now moving to the next problem. The incorrect statement of the following is, okay, again the question is based on the ligand field theory and you have to identify the incorrect statement. So I can read the question fast actually. Increasing ligand field stabilization energy increases the inertness. Okay, definitely it's a true. This is true. When your LFSE increases, remember this point, okay, then the inertness of the nature will also increases. So this is the true. Complexes of the D10 ions are normally, no, this is false. See, whenever you are having the D10 ions, that means you are having 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So Eg orbitals are filled. When Eg orbitals are filled, then your complexes would be labile, but it is saying inert. So this should be your correct answer. Okay, option B is the correct answer. This is the incorrect statement. While you see the second and third row transition, they are actually they form the more inert complex due to the diffused d orbital size. D orbitals are bigger and diffused, and due to this actually ligand field splitting is quite high in that case. Okay, when ligand field splitting is quite high, ligands approaches more close to the metal, so they would pairing occur in the orbitals. In that case actually the inert complexes will result. So this is also true. And octahedral metal complex D3 is actually, see, D3 and D6 low spin. See what it means actually. Say this is where D3 low spin, 1, 2, 3, and it is where D6 low spin, 1, 2, 3, 4, 5, 6. So in both the cases Eg orbitals are empty. That means in both the cases they are inert. So it is also true. So the only incorrect statement is the option number 2, option B. Okay, now moving to the next problem. What it says, the correct statement regarding the thermodynamic stability and unstability, kinetic lability and inertness of the okay guys, you can see in that case, again you see what I am telling you in that case. Say for example you are having nickel 2 positive, Ni 2 positive, that means 26 electron which belongs to 3d8 system. Next is your iron which is in 3 positive. So you know the cobalt is in +2, nickel is in +2 and iron is in +3, and when iron is in +3 it simply means it is having the 23 electron, and when it is having the 23 electrons, the 3d5 system. And you know when it is the cyanide is the strong ligand in that case, right? Cyanide is the strong ligand. So in that case if you do the splitting, so you will fill the 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. So this complex is actually your labile. Kinetic labile means it will react faster. Okay, and this H2O, and it is the weak field. So when it is in weak field and you have to fill the 5 electrons, 1, 2, 3, 4 and 5. Again Eg having the electron, it is also labile. So both complexes are labile. So check this option whether it is given or not. Both the complexes are thermodynamic stable and kinetically labile. Yes, both are kinetically labile, right? And when both are kinetically labile, then you can blindly mark this as the correct option. There is no need to go further actually. Okay, so only see, if you solve only this much of thing, then you will be able to solve such kind of the question. And you know the thermodynamic stability is something different, which is based on the stability constant, right, and stepwise stability constant, and the data is not given for them here, and there is no need to learn it actually. This question is a tricky question, and you have to you will solve this question by only actually identifying the inertness, kinetically labiless or kinetically inertness or nature of the ligands. Okay, now moving to the next problem. The correct order of rate of water exchange reaction. Now this question is actually theoretical question, and I have solved this question in my previous lecture series also. So in that case you can see here you have been given the different options in that case. So first of all you have to mark the oxidation states. Say chromium +2, chromium +3, manganese +2, and it is in +2. Okay, only Cr3 positive is actually having the higher value in that case. Okay, so now what happens actually, see, listen carefully what I am saying actually. It is not possible to for me to write, right? See, whenever the water exchange reaction occurs in the octahedral transition complexes, The d electron configurations are very important in that case, because see, crystal field stabilization energy will affect, see in the simply you see CFSE affects reaction rates of water exchange reaction. Water exchange reaction, this you have to know, right? See, for chromium 3 positive ion, if you are having the chromium 3 positive ion, so it will have a very slow exchange. It will have a very slow exchange, right? Why? Because it's a 3D configuration, and 3D configuration means you are having 3 electrons here, right? No electrons in the Eg orbital, so it's inert one. When it is inert, so the for 3 Cr3 positive, the rate would be very slow. Now check in which option actually the slowest rate is given for. See, it is given for slowest rate for this one. This cannot be your correct answer. Okay, this could be your answer, this could be, but this could be your answer, this cannot be your answer. So you have to select between B and C, right? So now this is clear, I think. Now moving to the next one. See, basically the rate of the substitution reaction decreases across the series. For example, you are having chromium 2 positive ion and manganese 2 positive ion and your iron 2 positive ion, and if you see your chromium, manganese and iron, so it is 24, 25 and 26. So across the period, when you move across the period, right, so your substitution rate decreases. Your substitution rate decreases. Why it is decreases? Because the effective nuclear charge across the series increases. Okay, and when the effective nuclear charge increases, what happens actually? This bond will become stronger, strong bond, okay, due to this one. So you see, least for this one, and after that Cr2 positive would be there, okay. So after that, sorry, greatest for this one and this one. So after your this chromium 3 positive ion, there should be your iron, okay, and you see chromium 3 positive is here and iron is there. After that your manganese is there, okay. So option B is the correct answer in that case. You can mark the option B as the correct option, okay. Now moving to the next problem, what it says: which of the following electronic configuration is for inert octahedral complex? Okay, you can blindly mark this option D as the correct option. Why option D is the correct option in that case? I told you, whenever you are not finding the electrons in the Eg orbital, it simply means the inert complexes, okay. Now moving to the next problem, what it says, and probably this is my last problem, and in this lecture I have solved the 30 problems for you, 30 problems for you, and in the next lecture I will solve another 30 to 32 problems, and this will complete my 150 question series in the coordination chemistry, okay. So now my last problem is what it says actually. You see here, under strongly basic conditions, okay, you are having the strong base, the first step in the mechanism for the base catalyzed substitution of Cl negative by OH in this one, what it simply means actually, right? It's quite easy problem. CONH3 whole 5 Cl, and you have been given 2 positive over there, okay, and you are reacting this with OH negative, right, and definitely this is a strong basic nature, right. This reaction is going on actually. So what will happen? Substitution of see, in that case what will happen in the first step of the reaction? This one, chloride by OH substitution, you know, whether it is possible or not. No, it is not possible. I have explained this in the reaction mechanism part, okay. And then you can go dissociation of chloride. No. This penta, this is actually not possible. This penta carbocation and see, this pentavalent species does not form in this condition actually. Formation of, yes, this is quite possible in that case. What will happen actually, you see this OH negative which is there, it abstract one of the hydrogen from this one and get neutralized, and you will have NH2 negative in that case. This is the first step. I have explained these things in pretty much detail in my lecture series. Okay, you can go there and learn the things from there. So your correct option is looking here, option number 3. Okay, option C is the correct option. So basically, in the base catalyzed substitution of the chloride by hydroxide ion in this particular complex under strongly basic conditions, the first steps involve the removal of the hydrogen from the ammonia ligand, right? Because ammonia is actually, you see, it loses actually the proton actually. It's a base actually in that case, Bronsted acid, not base actually, right? And this will result in the formation of the conjugate base NH2 negative. Okay, so this is if you want then you can write in that manner, NH3 OH negative ऐसे बनाते हैं, right? And then NH2 negative plus H3O positive. Okay, so it's a proton donor, so it is acid. It's a proton donor. Okay, and it is acceptor base. So this is acid. No, this could be base. This is acid. So basically, conjugate acid base pair is forming, right? That means option C is the correct option. So this is how you can solve the problem based on this one. I hope you like the lecture. If you like the lecture, please share the tetrahedron chemistry classes with your friends also. If you are new viewer and watching video for the first time, please like the video and share with your friends this tetrahedron chemistry classes, and go through my playlist which I have made exclusively for the CSIR NET and the GATE examination. Okay, so that's it for this particular lecture. Meet you in the next lecture, guys. Thank you very much. Hello friends, welcome back to the tetrahedron chemistry classes. So guys, if you remember that from yesterday onwards I have started an extensive 150 question practice problem for your coordination chemistry, right, for the upcoming examination like IIT JAM and the GATE examination, right? So in my first lecture I have solved somewhere around 11 problem, and today I'm going to take some more problem in the same series, and these are the very important practice problem for your upcoming examination. I hope this will help you in your coming examination. So in the today's lecture I'm going to take first question, and in this series basically I'll discuss very general and very common questions, and which actually forms your basis actually, right? If you want to learn the coordination chemistry in great depth, then you should be able to solve the variety of the questions based on the organic chemistry. It doesn't matter whether the question is easy or question is difficult or it is of moderate level, but you have to take all kinds of the questions, right? So in this series I am going to take this very important question. Okay, and you can see here what this question says. When ferric reacts with the potassium ferrocyanide, a blue precipitate has been formed due to the formation of these four options are given. That means it generally says that when you have Fe3 ions, Fe3 positive ions, and when these Fe3 positive ion reacts with the potassium ferrocyanide, right, then a blue precipitate is formed. So what is the potassium ferrocyanide actually? So for this you should know the potassium ferrocyanide formula, and that potassium ferrocyanide is K4 Fe CN6. Okay, this is your potassium ferrocyanide. Fine, and this potassium ferrocyanide, when reacts with the ferric ions, Fe3 positive ions, okay, then what the question says? Question says it forms a blue precipitate. It forms a blue precipitate. Then what would be the formula of that? blue precipitate. So I'm telling you that blue precipitate is nothing, but it's a very common complex which is known as the Prussian blue. Prusssin, Prussian blue. Okay, and that Prussian blue is nothing but it is your this particular complex. If you react both of them, then you will find it will form Fe4 Fe CN6, right? This is known as whole thrice. Okay, this is known as ferrocyanide. Sorry, ferrocyanide. So if you want to know the structure of this one, so or if you want to name it, so here you can see the iron is in +2 oxidation state, and it's very easy to calculate the oxidation state. And if you ionize this particular complex, then you will find 4Fe, since the stoichiometric coefficient is 4 here and 3 is here. You know, during the formation of any complex or the salt, the valency interchanges those, so this 3 will come here actually, and plus you will have this complex ion, and you know it is present thrice, so you can write 3 Fe CN6, and you know 4 is there, so you can write 4 negative here, right? So it is see, this is ferric ions, so it is ferri, and if you calculate the oxidation state of iron, it would be +2 again, right? So it is ferrocyanide basically. IUPAC name is little different. Okay, so this this formation of the blue color, which is actually your Prussian blue, is due to the formation of your ferrocyanide, right? So this is ferrocyanide. Why ferri? Because it is +3 and it is +2. So what is happening in that case? Your oxidation of this particular Fe3 positive ion is actually happening here. So it is ferrocyanide, right? And what is the formula for this one? You can find here. What is option? Right. Option number D is the correct answer. This one, D is the correct option for this one. So this is how you can solve this particular problem, right? So because you know this, whenever you have this potassium ferricyanide salt, your potassium ferrocyanide salt, this one, it's a very easily undergo oxidation, right? And then it will produce this particular complex. Okay. Now moving to the next problem. And your problem is what? Okay, now this problem is actually a quite simple one. So generally they ask the color of this particular compound. So you know what is this? Sorry, you know this compound is what? This is actually Mohr's salt. This is Mohr's salt. And it's not a coordination compound, it's a double salt. It's a double salt. Basically, you can relate this with FeSO4. And it is very important to note that whenever you have this ferrous salts actually, so they form actually light green crystals. They form light green crystals. So for this, the correct option is this one, light green in color. Okay, so these two questions are very simple, but you have to solve any kind of the question. You should be able to solve any kind of the question. Okay, however, this question is more or less on the memory based. Now the part third actually, what says that chelates are. So in general, I am telling you what are the chelates. Complexes which have the ring structures. Complexes having ring structure, right? So how we can form the complexes? So complexes with monodentate ligand? No. See, since monodentate ligands are having only one side, one donor atom, so it cannot form a ring. You know, when you want to form a ring actually, so you have to have actually a ligand which is which have the denticity more than one. So this cannot be your option, right? You can strike out this one. Then second is complexes with the bidentate ligand. Yes, this could be the answer, right? And then complexes with the ligand having more than 2 donor atoms. Yes, this could also be your answer, right? So the correct, see, both of them are correct, and option D is seems more correct, right? Because it is having the both options, right? Bidentate ligand, and bidentate ligands are those ligands which have more than one donor, which have generally have 2 donor sides. So here in that case you are having the 2 donor atoms. So option D is the correct answer, right? Again, it's a very simple and very easy problem. And now your question number 4, and in this question number 4, what the question asks actually generally, identify the correct statement. So what is the correct statement? You have to identify that statement. Okay, EDTA is a tetradentate ligand. Okay, we'll check this one. Oxalato is a monodentate ligand. Okay, so for this what you have to do actually, you have to draw the structure of the oxalato and your say EDTA. So oxalato is what? COO negative, single bond, COO negative, right? So it is having 2 donor atoms. So basically this oxalato is bidentate. Oxalato is bidentate. Okay, so that means it can, option B cannot be your answer, and option D can also be, cannot see, it is not actually your answer because it is bidentate, but it has given here that it is tetradentate, and here it is monodentate, so this cannot be your answer. So now you have to select between A and C actually. So for this you have to actually know the structure of EDTA. So I'm telling you, say for example, EDTA is ethylene diamine tetraacetate or tetraacetic acid. So you will put CH2, right? And you will put nitrogen here, and then again you will put another nitrogen here, right? And when you do this, so here you are having CH2, COOH, okay? And again you are having CH2, COOH. Similarly, you can put these CH2COH here also, okay, just like that. So if you see here, so nitrogen is a donor atom, and this nitrogen is also a donor atom. So here it's a bidentate when you see the nitrogen only. But if you ionize this one, so say for example, if I ionize this one and I remove this, so it will get negative. If I ionize this one, it will get again negative, and again it will get a negative, again it will get a negative, and when I am putting negative over there, that means I have to remove hydrogens from there, okay, just like that, okay. And when I do that, okay, when I do that, so that means denticity 1, denticity 2, denticity 3, denticity 4, donor atom, sorry, not denticity, donor atom, and this is donor atom number 5 and donor atom number 6. So it is having the 6 donor side, so it's a hexadentate ligand. So that means your correct option is your option C. Option C is the correct answer, right? So this cannot be your answer. Again, it's a very simple problem based on your practice actually. If you have done or practice of all these structures, then it is very easy to find the answer. Now my next question is, complex formation could be identified. Okay, what is the meaning of that? That means you are doing a reaction in the lab, right? Say for example, if you are reacting a particular compound A and particular compound B, and you are forming a complex. So how you will identify whether the complex is forming or not? So you have given all of the options: change in color, change in solubility, and change in conductivity. So in general, it has been seen that in the various research papers, and in the case of the various complexes, whenever the complex formation takes place, all these parameters, all these physical properties changes, whether it is color, solubility or conductivity. So in that case, when all are changes, that means the correct option is option number D, right? So you can strike out first one, you can strike out second one, you can strike out third one, while all actually generally changes during the complexation. So option D is the correct answer. Okay, now I am moving to the next question. Now this is, you see what the question says. For metal complexes, ligands are. So what are the ligands? It is saying the cations, cations linked by the coordinate bond. Say for example, right, I'll come to the detail of this also. Say for example, I am having a particular cation A positive, right? And you know your cation are actually the Lewis acid. Cations are Lewis acid, but the eligibility for a group or a molecule for a ion is that it must have at least a pair of electron to donate. It should be Lewis base actually, right? But it is Lewis acid cation, so it cannot, this A cannot be your answer. Okay, now second one, anions linked by the coordinate bond to the central metal atom. Definitely, if you have any anion, say I am writing Y negative and it is an anion, then you should know anion will always have a lone pair to donate, right? And when it is donating a lone pair to the metal, it is forming a coordinate bond, so it is a ligand. So option B actually could be your answer. And then third one, molecules linked by the coordinate to the central atom or ion. Okay, fine, it is again the same thing. Say for example, I am having the neutral molecule like ammonia, okay, and this ammonia is having the lone pair, so this lone pair can be donated to the metal, right? So form a coordinate bond between metal and the donor atom. So this can also be true. So option C you can write. And ions or molecules linked by the coordinate bond. Definitely this is ion, which is anion, and this is molecule, which is neutral molecule linked by the coordinate bond to the metal atom. Then option D can also be your correct answer, right? So in that case, you see, B is fine, C is fine, D is also fine. So what you literally say that D is the more correct answer. You can strike out second one also, right? However, it is true, right? And it is also true, but these two combinations are given in the option D. So you will select this D as the correct option, but not B and C, and A cannot be your answer. But in the some cases, like say I am having this molecule NH2, this is hydrogen, and you know this hydrogen is having two lone pair over there. So this is actually what, a ligand actually. It is a ligand. So but if you put H positive over there, then it would become NH3 and NH2. Now this will have the lone pair, but this lone pair is used in the formation of the bond. So nitrogen will get a positive. So it is basically what, cation. Okay, but this cation is also having a lone pair, so it is also a ligand. It is also a ligand, right? So cations in some cases may act as the ligand, provided that after attaining the cation status, it should have, or it must have, the extra lone pair to donate. But in this question, it simply says the cations, but not the question not specify the particular cation. So you can strike out the option A, as cations are generally Lewis acid, and for a ligand, right, Lewis base character must be there, right? Again, a very, very important question. You can check this, right? And now moving to the next question, which is your question number 7. What it says that, you can check, identify the correct sets of the monodentate ligand. Okay, you have to select the monodentate ligand. So you can strike out the option D, because this is your oxalate, which I just see 2 slides back I have drawn the structure of this one. So it's a bidentate ligand. Okay, it's a bidentate ligand, and you have to select ambidentate ligand, right? Okay, sorry, ambidentate ligands are those ligands which have two donor sites, but it can coordinate through the metal atom by using only one site at a time. Okay, so what kind of the examples are there actually? So they are basically the monodentate. They are basically monodentate. Since it is bidentate, so you can strike out this one. Okay, now going to select the correct options. This is your nitrate ion, NO3 negative. Okay, so if you draw the structure of this one, say I am drawing in that manner, NOO negative, right? So it is having actually only one. It can coordinate only through this oxygen, but not through this nitrogen. So this cannot be your answer. Similarly, you can go for the H2O. If you draw the structure of the H2O, then in the water molecule, oxygen having the 2 lone pairs, so it can coordinate through oxygen only. So this cannot be your answer. And third, we have already strike out on the basis of the bidentate nature of this oxalative ion. Now what remains is the option C. So option C is the correct answer. How we can check? See, NO2, right? You are having NO2. So in this NO2, if you draw the structure, right, OO negative and a lone pair over there. So this nitrogen can coordinate through the metal, and also in another complex this oxygen can also. So ambidentate ligands are those ligands in which 2 different donor sites are available. So in NO2 negative, 2 donor sites, one is nitrogen and another is negatively charged oxygen is there. And same is true for the NCS, right? NCS, right? Negative charge is there, right? So if this negative charge is present on this N, so it can coordinate through nitrogen, it can coordinate through sulfur, right? So this NCS and your NO2 actually are the ambident ligand, because they can linked, or they can form the coordinate bond with the metal ion by using the 2 different donor atoms in the different complexes. Remember, they will actually donate electron from one donor atom at a time, right? So this is how you can solve this particular question. Now moving to the next question, my question number 8, and what it says that identify the correct example of the monodentate ligand, right? And again, it's a very, very simple question, and if you want to know, then you see this F negative, it is having only one donor atom, so it's a monodentate ligand, no issues. And if you have H2O, you have already seen that it is having only oxygen donor atom, it is also a monodentate ligand. And this NO2, of course it's a ambidentate ligand, but it is also a monodentate ligand, because at a time it can donate electron either through nitrogen or from oxygen. So it is also a monodentate ligand, bidentate but monodentate also. So all are the correct one. So you can very easily take this option number D. So your option number D is the correct answer for this one. Now moving to the next one, say question number 9. In that case, SO2 can act. Okay, this is very, very important question. Very important question. And for this, what you will do actually, you will write the electronic configuration of the sulfur. Sulfur, you know, it is having the atomic number of the 16. If you write the electronic configuration, then it would be 1s2, 2s2, 2p6, 3s2, 3p4, 6, 4, 10, to 12 or 14, right? So this is the p orbital, right? These are the p orbitals, and they are having the only 4 electrons. 1, 2, 3, 4. That means these p orbital can accept the electron from the metal, right? So if you draw the molecular orbital diagram of SO2, then you will find actually this 3p section, right? This is this 3p section. It will have actually sulfur centered LUMO. Sulfur centered LUMO. LUMO, you know, lowest unoccupied molecular orbital. If you draw the molecular orbital diagram of SO2, right? So what will happen? Your sulfur centered LUMO would be there, and LUMO are lowest unoccupied molecular orbital. So what can happen? Metal having d electrons, they can donate electron to the LUMO actually, right? So basically it forms a sigma bond. Sulfur forms a sigma bond. So it's actually the sigma acceptor. It is sigma acceptor. It cannot be your pi acceptor, because for pi acceptor you should have the vacant pi orbitals, whether bonding or the your anti-bonding pi anti-bonding orbitals it can have actually, right? And when option B is correct, then obviously C cannot be your answer, because it includes the A and B both, and none of them cannot be your answer, because first one is the correct one. So this is very important question, which is actually what your formation of your formation of your SO2 formation of your sigma acceptor, right? So this is how you can solve this particular problem. And see, one more important thing, you can add your armory. Say this SO2, right? This sulfur dioxide. In that case, your sulfur is sp2 hybridized, right? Sulfur is sp2 hybridized, right? And when it forms the complex, what will happen? See, say this is the metal, and the metal when donates the electron to the LUMO of the sulfur, so it will form a complex just like that, and actually the hybridization state changes from sp2 to sp3. Okay, so in that case you can see the 3 bond pairs are there and 1 lone pair is there, right? So it is see, lone pair you can put anywhere, so it is having the pyramidal structure. This complex will have the pyramid geometry, and you know these things I have explained in my Vesper theory lecture. You can go through and learn from there also. Okay, now moving to the next question. My next question says, in this particular complex which is given here, the coordination number and oxidation state of cobalt. Okay, so what you can do, you can write the complex again. CO En whole twice, and 1 water molecule is there along with the 1 Br, fine, and 2 of the Cl are there in the ionization sphere. So what you can do, you can put you can write the Cl in that manner. You know the Cl is having, the Cl negative is having the -1 formal charge, so automatically you will put 2 positive here. And I told you, anything present in the coordination sphere. Coordination sphere is the sphere which we generally write in the square bracket. Anything apart from the central metal, this cobalt is the central metal, anything from your central metal, all remaining things are your ligands, and ligands actually are the coordination number. So you can see this En is what? It is bidentate. You have seen earlier, this is bidentate. And I already told you, 1 bidentate ligand will be counted as twice. So it is, see, 1 counted as twice, but it is present 2 times. So 2 into 2. So 2 is for denticity, and 2 is the number which is given here, right? Plus 1 is H2O and plus 1 is Br. They are also the ligand. So this will give you the 6. So in that case, coordination number is 6. So if the coordination number is 6, then you can find the options here. Okay, in that case you can see the coordination number 6 here. So option A is the correct answer. There is no need to go further. Okay, but if you want to calculate the oxidation state of cobalt also, so you can calculate, say this is X plus ethylene diamine is neutral, that means neutral into 2, okay, plus H2O is neutral, no charge over there, into 1, and you know, plus your Br is -1. So you can write -1 here. This will give you 2 positive, which is given here. So your X would be +3. So coordination number is 6 and +3 is the oxidation state. So option A is the correct answer, right? Now moving to the next question, which is the question number 11. What it says that in this particular complex, right, tetracyanonickelate 2 ion is the IUPAC name, and in this particular complex, what is the oxidation state of the nickel? So you can count very easily, or you can not count, you can calculate very easily. You can put that 2 negative over there, okay, put X in place of this nickel. You know, cyanide is having formal charge of -1 and it is present 4 times, times 4. That means you will put the 2 negative over there. Then your X would be equals to 2 negative plus 4, that will give you the 2. That means nickel is in +2 oxidation state, right? And you can strike out option A, right? Because apart from some of the carbonyls, it is not possible that the metal would have the negative oxidation state. 4 cannot be your answer. So C, option 11, option C is the correct one, right? So in that case you can calculate. So again, it's a very simple, straightforward problem. Now moving to the next problem, guys. My next problem is the problem number 12. What it says that identify the hexadentate ligand. Okay, so there is no need to go further actually, and hexadentate ligands are very rare ligands, and you know I already told you EDTA. Earlier we have drawn the structure of this EDTA which were hexadentate, while this DMG is dimethyl glyoxime. So what is dimethyl glyoxime? You can write in that manner, say carbon, you can put one methyl here and say you can put another methyl here, and this is double bond. You can put nitrogen here, you can put OH here. Similarly you can go here, double bond, it is nitrogen, right? And you can put OH here. So one donor atom is nitrogen, another donor atom is nitrogen, and if you ionize this, then it will become O negative, another donor atom, oxygen here, another donor atom. So in that case the denticity is 4. That means it's a tetradentate ligand. So this cannot be your answer. Ethylene diamine, I already told you, is what? CH2, single bond CH2, NH2 and NH2. Okay. So one lone pair here and another lone pair here, it's a bidentate ligand, denticity is 2. So this cannot be your answer. If you want to draw the bipyridyl, I already told you in yesterday's case. So if you want to draw that, I can put nitrogen here, bipyridine, and you can put nitrogen here. Okay. So it's a 2,2 bipyridine. Again, it's a bidentate ligand, denticity is 2. So this cannot be your answer. So D is the correct option. None of these, right? None of this actually is the hexadentate ligand. This is how you can solve the problem. So in that case, you have learnt a lot about your ligands, right? Nature of the ligands. Now we'll move to the next problem. And what it says that precipitate of silver chloride reacts with the aqueous ammonia. Okay, it's a very simple, straightforward question. You have studied in your +2 also, right? Where you form silver mirror and all these things, like these reactions you have studied in your +2. So this is rather simply, see, this is AgCl, white precipitate of silver chloride, we all know, and when it reacts with the ammonia, okay, and what it says, it's aqueous ammonia. So whether you write the aqueous ammonia or you write the NH4OH, it will not make any difference actually, right? And this will form a complex in which your silver would be in the +1 oxidation state. So you can put Cl here and you can put 2 negative here in that case, NH3 whole twice, right? So this is the complex actually. AgNH3 whole twice Cl, you can check here, AgNH3 whole twice. So option C is the correct option, right? So if you ionize this, then it will give you what? AgNH3 whole twice and a positive over there. So this matches with this one, okay? So again, this is a very simple problem. Now the question number 5, what it says that the geometry of the complex is the two complexes are given actually, right? So see what you can do, you can draw the structures of these. So say for example, I am having I can rewrite the formula NiCN whole twice, then PPH OET 2 times, right? And it is present as thrice. Okay. So you can, what you can do, you can actually count the count its oxidation number, not there, but its oxidation number. Okay, so what is the oxidation number? So not oxidation, sorry, coordination number, not oxidation number, but the coordination number. So in that case, you can see coordination number 2 and coordination number 3. So 5, and you know, the for 5, what it will form? Only one possibility is there, which is TBP, trigonal bipyramidal structure. And you know what is a trigonal bipyramidal structure? So in that manner you can draw, right? In the center you can put nickel, and on the two axial positions you can put these two cyanides, right? And in the remaining position you can put 3 of these, that remaining part. So it's a TBP structure. Now find in the option whether the complex A is given as TBP or not. So here it is not TBP, you can strike out, it is not. Okay, this could be your answer, this cannot be your answer. So option A and option D, you have to, no, it is a square bipyramidal, no. Try option A and option C. You can select between these two because both are giving the same option for the first complex actually. Now go for the second complex. So what is the second complex given here? I can draw the structure of IR, Cl, CO, PPH 3 whole twice. It is just like that. Okay. So in that case, the coordination number is 4. 1 plus 2 plus 2, sorry, 1 plus 1, and it is present twice. So coordination number is 4. And when the coordination number 4, you have two possibilities, tetrahedral geometry and your square planar geometry. So two possibilities are there. Now you have to decide whether it is square planar or it is tetrahedral. Okay, you have to select in between two actually, right? So you know, in the tetrahedral structure, the bond angle is 109.5 degrees, and in case of the square planar it is 90 degree. So you may have the confusion that it may you may have the confusion that it may have the tetrahedral structure, but spectroscopically it is find that this is actually your square planar structure, right? It is square planar structure, and when it is a square planar structure, then you can strike out, or you can opt this A as the correct option. You can strike out this one, right? And see, sometimes it is quite difficult to actually know the geometry of the complexes by checking the bond angle and all these things. If you can recall, in the last class I actually explained the chlorine is the bigger ligand, so it will actually try to remain as far as apart, so it will adopt the tetrahedral geometry, forms the 109.5 degree angle. But here this complex actually completely failed, so it's a tetrahedral geometry, right? Because this iridium, right, this iridium is not having the d orbital, vacant d orbital to overlap, so it cannot undergo the dsp2 hybridization, rather it will undergo the sp3 hybridization, right? So this is how you can understand. So this problem is actually the memory based problem actually. If you have learned, if you have read that particular question, only then you can solve, you will be able to solve, otherwise. Okay, then now moving to the next problem. Problem number 6, which says that the correct set of geometries of these two complexes. So it's quite simple here. You see, this is CO, En whole thrice, okay, and 2 positive. You know your ethylene diamine is what? It is bidentate. It is bidentate. When it is bidentate, that means denticity is 2, and their number is 3. So 2 times 3 is the 6. That means coordination number is 6. And when coordination number is 6, the geometry possible is what? Octahedral. So check whether for the first complex it is given in the octahedral or not. Okay, so A is octahedral, so A could be your answer. B can also be your answer, but C you can strike out, and D you can strike out. Okay, now you have to select in between these two. Now go for the EDTA, this particular complex CO, EDTA and 2 negative. Okay, and again you know this EDTA is what? Hexadentate ligand. It is hexadentate ligand, and when it is hexadentate ligand, it simply says that coordination number is 6, and for coordination number 6 only one geometry octahedral is possible. So second one is also octahedral. So the correct option is the B, not A. So in that case you can solve this problem also. Okay, I hope this is clear to you. In this particular lecture we are having the very straightforward problems, but practice is important, right? That's why I am giving you all these problems. Now you see my next question. Okay, this is rather very important, right, for NET, GATE, IIT JAM examination and also for the JAM examination, right? So what it says that in room temperature only one signal is observed for this particular complex, which is FeCO5. Okay, so how we can solve this question? First of all, you can write FeCO5, tetracarbonyl iron. Since the coordination number is 5, it may have two kinds of the geometry. First, it may have the square pyramidal, How we can draw the square pyramidal? Put the iron in the center, 4 carbonyls in the 4 corners and 1 carbonyl here. This is square pyramidal geometry. Another possibility is TBP, which is trigonal bipyramidal. So put iron in the center, okay, just like that, and rest of the carbonyls, 2 axial carbonyls and 3 equatorial carbonyls. Okay, so this is TBP geometry. So at room temperature, at RT, Barry's pseudo rotation occur. Barry's pseudo rotation, right? When the Barry's pseudo rotation actually occurs, what it means that this geometry will quickly transform to this, and this geometry will quickly transform to this actually, right? So square pyramidal goes to the trigonal bipyramidal, bipyramidal goes to the square pyramidal, right? And basically it's a fluxonial molecule. So this I have explained in my organometallic lectures, right? You can check there actually in the coordination in the organometallic series, fluxionality in organometallic compounds. This is the title. You can find in the YouTube by writing in the search bar fluxionality in the organometallic compounds by tetrahedron chemistry classes. Then you will find the detail of this one, right? So fluxionality means when the one structure changes into the another structure, and this is happening at room temperature very quickly. So NMR instrument actually cannot predict this change actually. So it will observe that NMR spectrometer observe a intermediate geometry, and that intermediate geometry it observes all the carbons of the same kind, right? When all the carbons of the carbonyls the spectrometer observe the same kind, it will produce only one NMR signal, one 13C NMR signal. So so tetracarbonyl iron's fluxonial nature gives only one signal in NMR structure, right? So if you can change, if you check the answer, rapid interconvergence cis trans, no, there is no case of actually your cis and trans, right? Rapid interchange position of all CO within structures, no, all COs are not changing. All the CO are equally oriented, no, they are not equally oriented. Rapid interconversion of square pyramidal geometry to trigonal pyramidal, yes, trigonal bipyramidal geometry, it is fine. So option D is the correct answer, right? But this is again a very, very important problem, right? Now moving to the next. My next problem, what it says that, okay, so this problem is a little tricky, but again it's a very important problem. It's a very, very important problem, and it actually tells about the distortion, right? And that distortion you learn in the John Taylor distortion in coordination chemistry. But what it says that, see, it is having, in trigonal distortion of octahedral geometry. So you know what is the proper octahedral geometry. So you can put the metal in the center, okay, and then you can put all the ligands over there. So generally in that case all the metal ligand bonds are same, bond lengths are same. But when the distortion occur actually, right, when the distortion occur, and the distortion is the trigonal distortion. So during this distortion the geometry changes in that manner. See, earlier it is having this kind of geometry, just like that, okay, but when distortion occur it changes in that manner. Say I can draw the structure, right, these are the four, and say this is your fifth ligand, and somewhere here I can put your sixth ligand, right, and when I want to connect them, so how I can connect them, I can connect this from here to here and this here to here. Similarly this I can connect here to here, and this I can connect here to here, and then I can change this little bit, right. Then what it says that this will also connect here, right, and this will also connect here, this will go there, and this can also go there. So if you check, see, this is actually your trigonal face, one trigonal face, and this is another face. So when tetragonal distortion occurs, it occurs from the two different faces. This is say face 1 and this is the face 2. So from the opposite forces, opposite phases, this trigonal distortion occurs. Now see, in the trigonal distortion of the octahedral structure, distortion occurs through the axial bonds, no, and square plane, no, square planar is not changing. See, this plane is not changing. Yes, trigonal faces, it is the correct option, okay. Two axial and two equatorial, no, it is not possible actually, right, because four bonds are same, are of same type, and two bonds are of same type. So there is no meaning of changing only two bonds out of four. So D cannot be your answer. So correct option is the option number C. So you should remember, whenever the trigonal distortion occurs in the octahedral structure, it occurs from the trigonal faces, two different trigonal faces, right. This is how you can understand. Now moving to the next problem, right, and this is my last problem, okay, for this particular lecture, right. And what the problem says that the complex, this is a, okay, very important problem, very important problem, most important, right, for your upcoming examination. Very important problem. What it says that this particular complex is a spin triplet system, hence the geometry of the complex. Okay, now it is very important to understand the things. You have given this complex NiCl2 PPH3 whole twice, right, you have given this. Coordination number is what? 2 here plus 2 here, coordination number 4. And when the coordination number 4, you may have the two options. It may have tetrahedral geometry with sp3 hybridization. It may have square planar geometry with dsp2 hybridization. So you have to select whether it is, see, it cannot be your octahedral. It cannot be your octahedral geometry. Why? Because for octahedral you should have the coordination number 5. Similarly, it cannot be your trigonal bipyramidal geometry, because for trigonal bipyramidal geometry you should have coordination number of 5. Now it could be out of these two, A and B. You can go for the correct option. So what I'll tell you, write the electronic configuration of nickel 2 ion. You know, nickel 2 ion is having 26 electron over there. If you write the electronic configuration, basically it's a 3D8 system. I am not writing the entire electronic configuration, but I am giving you the idea. It is having the 3D8 system. So if you draw this structure, or you can draw the d orbitals, right? How many electrons are there? 8. You can fill those 8 electrons into it. 1, 2, 3, 4, 5, 6, 7, and say 8. Now you are having these 2 unpaired electrons, right? And you can see here what it is given here, spin triplet. It is giving the spin triplet. Spin, what is the meaning of the spin triplet, right? This is something very, very important. Spin triplet means 2s plus 1, that will give you 3. This is what the triplet means. And for the triplet, your see this s should be 1 actually. Say if you put 2 into 1 plus 1, only it will have the 3 value, right? So how we can get the value of s? You know, s is what? When you combine that plus half with the plus half, only then you will get 1. And you know, for this, spin is the plus half, and for this also spin is the plus half, and when you add these two, it will give you the 1, and this 1 when you put here, you will get the 3. That means spin triplet, and this is only possible when you have this D8 configuration. It is given here. You can see the spin triplet system is given here, right? That means d orbitals are not available for hybridization. Your d orbitals are not available for hybridization. When d orbitals are not available for hybridization, it cannot have dsp2 hybridization. Hence, the geometry cannot be square planar. The only option left is what? sp3 hybridization would be there. That means it will lead to the tetrahedral geometry. So, correct option is option number B is the tetrahedral geometry for this particular complex. It's a very important one, right? For your GATE or IIT JAM examination, it is very, very important. Sometimes they may ask the question in this form also. They will give in the spin triplet, spin doublet, spin quadruplet, and then you have to find the geometry. This is rather very, very important question. So we have discussed a lot of questions today, and few of the questions are really good for your examinations and for your practice point of view. I hope you like the lecture. If you like the lecture, please share the tetrahedron chemistry classes with your friends, right? And don't forget to like the video, right? And if you are new here and watching for the video for the first time, watching video for the first time, so kindly subscribe the tetrahedron chemistry classes, and I'll also giving you the link in the description for the coordination chemistry, so that you can have idea about the coordination chemistry in the detail, the video which I have already made or uploaded in the YouTube, right? So that's it for today, guys. I'll meet you in the next lecture with more problems. As I have promised to you before your upcoming examination, I'll complete at least 150 brand new practice problems for you. Okay, thank you. Thank you very much. Hello friends, welcome back to the tetrahedron chemistry classes. So guys, as you know, I have started a 150 brand new question series on coordination chemistry, and in this series I have already completed 2 lectures where I have solved somewhere around say 30 questions, and in today's class I am going to solve another 20 questions, brand new 20 questions on the various aspects of the coordination chemistry, right? And on this particular lecture I will be solving 20 problems actually, and this is my problem number 1. And if you read the problem, what it says that, okay, the problem says a coordination compound contains 5 ammonia molecule. That means a compound is having 5 ammonia molecule, okay, and 1 nitro group. It is also having 1 NO2 group, and it is having 2 of the chloride atoms, right? And 1 mole of this particular compound, which produces 3 moles in the aqueous ions. So in the solution you will have total 3 moles, okay? In the aqueous solution you will get 3 moles. To treat with this solution with excess of AgNO3, 2 AgCl has been precipitated. So this part is very, very important, right? This part is very, very important to solve question. And remember one thing, to precipitation of 2 moles of AgCl, right? That means if you want to precipitate 2 of AgCl, for this you will require 2 of the chloride ions in the ionization sphere. Okay, ionization sphere, you will require 2 of the chloride ion. And I already told you that whatever the ions are present outside the square bracket, they are actually considered in ionization sphere. So that means out of the 4 options which are given here, you have to select the option which is having actually 2 of the chloride ions in the ionization sphere. So if you check this, then you can straightforward write this particular example: cobalt along with 5 of the ammonia, 1 of the NO2. Okay, this is the coordination sphere, and outside the coordination sphere you are having the 2 of the chloride ion. So if you want to write, or if you want to understand, this is your ionization sphere, which I am writing as IS, and the part which is present within the bracket, it is your coordination sphere, and I am writing it as CS, right? And if you treat this with excess of AgNO3, you are treating this particular compound, 1 mole of this compound with excess of AgNO3, then of course you will have 2 of AgCl, because 2 Cl are present outside this bracket, and 1 of your this particular ion, which is the complex ion, NO2, and you put the square bracket over there, and then you will put 2 of the positive over there. So how many actually ions you are getting in the solution? 1 of this and 2 of this. So total 3 ions you are having, and this is what the actually your question says, right? 1 mole of this compound produces 3 moles of the ion. So these 3 moles are actually this one. Okay, and so if you want to select, then your option C is the correct answer. Option A is not having any chloride in the ionization sphere, right? And similarly option B is also not having any ionization sphere. All actually you can see the square bracket are there, and only this example seems to be correct, which is having 2 of the chlorine outside this sphere. So this is the correct answer. Okay, now moving to the next problem. What it says that a platinum complex is there, ethylene bis ethylene diamine dichloro platinum 2 ion is given. Okay, and what kind of isomerism it will show? It will show the geometrical isomerism, it will show the linkage, optical, or both, right? So for this, see guys, you have to actually draw the structure of this particular compound. So if you want to draw the structure of this particular compound, so what you can do, you can put, sorry, I can change the color. You can put platinum in the center, right? And then you are having this example. What you will do, you will put 2 of the chlorine trans to each other, and ethylene diamine you will put here, and you will connect it just like that. Then another ethylene diamine you will put in that manner. So if you check the structure of this compound, 2 of the chlorides are at 180-degree angle. Similarly, 2 of the ethylene diamine are also at 180-degree angle. So it's a trans isomer. It's a trans isomer. If you want to draw this structure again, so what you will do, right? Make this octahedral complex in that manner, and now place 2 of the chlorine at 90-degree, right? And when you have actually put it 2 of these chlorine at 90-degree, then obviously your ethylene diamine will go in the other positions, 90-degree, and here also they are at 90-degree, right? So this is cis isomer. Clear? So one thing is quite clear, it will show the geometrical isomerism. Okay, so geometrical isomerism it can show. Now check for your optical isomerism. Okay, so this is very important. I have already told you in my previous lectures. Transform is actually having the plane of symmetry, POS. right? Sigma plane it is having. When the plane of symmetry is there, then your compound would be optically inactive. And how we can say that it is having that plane of symmetry? So for this actually I can delete this circle from here and from here also, right? Now say I am putting my chlorine here. So if you put a plane here in the center, say I am putting a plane here, and this plane is bisecting this molecule into the two identical half. This half and this half, they are the identical one. That means plane of symmetry is there. That means no optical isomerism. No optical isomerism. But in case of the cis isomer, there is no plane of symmetry, no POS, right? You cannot actually put a plane in any manner which will bisect the molecule into the two identical halves. And this thing I have explained in detail in my coordination isomerism in the coordination compound, where I have explained all these things. You can go through and check what is the how actually we can identify. So when it is not having the plane of symmetry, so it can show the optical isomerism. Okay. So this cis form is showing the optical isomerism, while trans form is not showing the optical isomerism. So you can see your optical isomerism is another possibility. There is no question of the linkage isomerism in that case, because every time if you replace the position of the two chlorines, they are always connected with the two of the with the platinum atom. Similarly, if you change the position of the ethylene diamine, again they will actually having the same position connected with the same platinum. So there is no chance of this your linkage isomerism. So option D is the correct answer, because both geometrical and optical isomerism are possible. So if I omit the remaining things, right, then option D is looking your correct answer. This is how you can solve the problem. Now moving to the next problem, what it says that, okay, identify the structure of chromium 3 chloride with 6H2O if 3 moles of AgCl precipitated. Okay, now it is again a very simplest kind of the problem. And guys, you have what you have given actually, see in that case you have given CrCl3 dot 6H2O. Okay, and if you treat this with excess of AgNO3, it is giving you 3 of AgCl. What it means that you must have 3 of the chloride ions in the ionization sphere. So for this you can rewrite that particular structure, CrH2O times 6, okay, and Cl3 over there. So this is the correct structure. Only this compound can react with excess of AgNO3 to give 3 moles of the AgCl. So look this particular option, whether it is given or not. Yes, it is given. Option D is the correct answer. So in that case also you can see your option D is the correct answer. Now moving to the next problem. Okay, what the next problem says, these two cobalt complexes are given, and whether they will show the geometrical isomerism, linkage isomerism, optical isomerism, or ionization isomerism. So this problem is quite simple, right? So why the problem is the quite simple one? First of all, whenever you are looking for the different kinds of the isomerism, start from the basic ones, and the basic one is the ionization isomerism. And in the ionization isomerism, you can see here, this is the ionization sphere, which is having the nitro group, and in that case this is the ionization sphere which is having your chloride. So change in the ionization part will lead to the ionization isomerism. Okay, and since this compound is actually whatever the compound are given here, in that case they cannot show actually your other kinds of the isomerism, right? There is no question of the linkage isomerism, And again, since Ma4 type of the complexes are there, so you cannot you cannot actually this compound cannot actually show other kinds of the isomerism like geometrical and optical. So the correct option, you will write it as that option number D is the correct one, right? Both are ionization isomers, right? So these are the ionization isomers. So it is not isomerism basically. They actually the question asks in that manner. You have to find the isomers. Sorry, earlier I thought that we are looking for the isomerism, but the question asked the isomers. When the question asked the isomers, so these two are the geometrical isomers. Sorry, ionization isomerism, option D, as only ionization sphere is having the different ions. Okay. Now my next problem, what it says, the two complexes shown below, what they are actually. They are positional isomer, optical isomers, or they are actually geometrical isomers or identical one, right? So this question is quite simple. How? You can see here, this is your A, this is your A. That means both A, right? A and A, they are forming 180-degree angle. That means they are trans to each other. Okay. Now in the compound B, you will see this is A and this is A again. In this compound B also, both A and A, they are at 180-degree angle. Okay. Similarly, if you check this part, if you consider this as ring, so this ring and this ring, they are also at 180-degree angle, and in that case they are also at 180-degree angle. That means they are identical compounds. They are not geometrical isomers. For geometrical isomers you should have the trans one, but they are already, say this is also the trans and this is also trans, because both the ligands ethylene diamine as well as your A, they are 180-degree each other. So there is no question of geometrical isomerism, right? And if I actually delete this, okay, so both these compounds are having plane of symmetry, right? One plane of symmetry goes just like that, and another plane of symmetry goes just like that. So optically inactive. Similarly, if you put a plane here, so this is another plane of symmetry, and if you put a plane from here, so it is another plane of symmetry. So when plane of symmetry are there in both the molecules, it simply means that there is no question of the optical isomerism. And for the positional isomers, isomerism or isomers, the position of the ligands should be different, but the position of the ligands are also different. So the correct option is the option number D. Now moving to the next problem, what it says that AgBr has the highest solubility in. Okay, now this question is again quite a simplest one. There is no need to waste much time in this particular question. You have been given AgBr, okay, and if you react this AgBr with NaBr, so there would be no reaction. Why? Br is common, this is also monovalent, this is also monovalent, so there is no change of oxidation state also. This is not possible. And same if you react this compound with HBr, again there would be no reaction. Okay, but the only thing left is what? AgBr. If you react with this with AgBr with NH4OH, it simply forms a very stable complex, which is Ag NH3 whole 4 and the Br. This complex would form actually, and it's a very stable complex, right? And if you want to react with this water, excess of water, so the aqua complex of silver, aqua complex of Ag are not known or are not very stable, right? So your correct option is B, right? AgBr has the highest solubility in the NH4OH, as it forms actually your very stable complex. Now moving to the next problem, optical activity will be shown by, okay, you have to select the structure which is optically active, which will show the optical isomerism. So simply you look for the plane of symmetry. The molecules which will have the plane of symmetry, they would be actually optically inactive. So this compound, I am showing only one plane of symmetry. You can check for another plane of symmetries also. And if you don't know how to check the presence of plane of symmetry, then you can go through my channel, write say group theory by tetrahedron chemistry classes. Right, so you will have only 2 or 3 video there where I have explained all these things. I have not completed that group theory part completely. Okay, I'll complete that part later on, but obviously you will understand how we can check the elements of symmetry in the molecule in the very best way by watching those videos, because I have used a website which a symmetry turbine, which gives a better idea. No one can no other website and no one can give better idea than that. Right, so it is very important to go through those videos. So for example, if I put a plane from somewhere here, say I am putting the plane here. If you put the plane here, so this is the plane of symmetry. Why? Because when you put this plane, then this half, the top part and the bottom part, they are the same. So this is optically inactive. So I am writing OI, optically inactive. Now going for this particular one, again you can see if I put the plane here, so the two parts are same, it is also optically inactive. Okay, now moving to this particular problem. This problem actually you have seen in the last example also. If I put a plane here, this is plane of symmetry, this will bisect these two half identically. Again, this is optically inactive. So the option B is the correct option. In that case, you cannot put the plane of symmetry by any means. Say if you try to put plane of symmetry from the center, the horizontal line, so this is B, this is A, so they are not identical actually. So you can check the plane of symmetry, it is not having. So the option B is the correct option in that case. Right, rest see only option B is not having plane of symmetry, rest all 3 A, C and D are having the plane of symmetry. So your correct answer is the B one. Now moving to the next problem. Okay, what it says that rank the given complex ion with increasing order depending upon their Kf values. Okay, now this is again you can see very simple. Okay, so I am writing Kf. Kf is formation constant. Formation constant. And this formation constant is high for stable complexes. Stable complexes. Right? And generally the stable complexes are the chelate complex. Chelate complex. And chelate complexes are those complexes which have the ring structure, and ring structures are formed by the multidented ligands. Multidented ligands. Okay. So what ligands you have given? You have given ethylene diamine, it's a bidentate. Okay, and then you have been given ammonia, NH3, and that NH3 is monodentate. And then you have been given EDTA, it is hexadentate. Dented, it was monodentate. Okay, so this EDTA will form the very stable complex, most stable complex. So for this EDTA one, the Kf would be the highest Kf, and for this ammonia complex, the lowest Kf. So now we can check the options. In that case, you can see ammonia is having the lowest value of the Kf, and this EDTA complex, which is of nickel, all complexes are of nickel, it is having the highest formation constant. So option C is the correct answer in that case. Okay, and see, this actually cannot your correct answer. You don't confuse that by seeing that NIDT at the last position. You can also focus on this particular sign, right? This is the greater than sign, which says that the bis ethylene triamine is the most stable complex, more stable than this one. It is not like that, right? So your option C is the correct answer. Now moving to the next problem. What it says, the problem number 10, the complex that can form D and L isomers. So what is the meaning of the D, L and isomers? D and L isomers. It simply means optical isomers. Optical isomers, right? So now you can check which compound can show the optical isomerism, which cannot actually. So just earlier 2 or 3 slides back you have seen the trans isomer of MAAB2 type. So when you have, say I'm writing here, trans isomers of MAA whole twice B2 type, okay, they are inactive, optically inactive. So this trans is optically inactive, right? And another complex you are having, CO NH3 whole 4 Cl2, right? You are having this particular complex positive over there. So it's an octahedral complex. You can put the cobalt in the center and then all the ammonia here, NH3, NH3, NH3 and NH3, okay, and then you can put the 2 of the chlorine over there. So this compound, again you can see here, this is also having a plane of symmetry, right? This is plane of symmetry. So this cannot show the optical isomerism. If you want to make the cis isomer of this one, so for cis, cobalt in the center, put any 2 chlorines at 90-degree angle, and rest of the ammonia you can put in that manner. Say this is NH3, this is NH3 again, this is another NH3 molecule, and this is another NH3, right? You are having this one. So this is the trans one, and this compound is also having the plane of symmetry, right? How it can have the plane of symmetry? Say this is what your cis isomer, okay. And this compound, if I bisect this from here to here, or here to here, or here to here, this can be actually your option, right? You're putting it 90-degree, chlorine, no plane of symmetry. Here no plane of symmetry, in that case no plane of symmetry. So this could be actually your option, right? But this cannot be your option, because in that case the coordination number is 5. So when the coordination number is 5, so you can put cobalt in the center and 3 of the chlorine in the equatorial position. It's a trigonal bipyramidal geometry, okay, and put 2 ammonia over there, NH3. So it is also having a plane of symmetry. This is actually the plane of symmetry. So this cannot be your answer, this 5 one, okay. The only option left is this one. This cis is optically active, as I have shown you, and this may also be your optically active, right? But in the answer key it is given that only this is this will show the optical isomerism, right? That means non-superimposable mirror image for this one. So I am not solving this particular one, how it is actually showing, whether it will show the optical isomerism or not. You please try to solve yourself. If you don't find the answer, then definitely in some other lecture I'll try to solve this particular part. Okay, but correct option in that case, then the answer key is given that this is actually the correct answer, right? And you can look for this one also. If you are not able to find, then you can ask me. Okay, now moving to the next problem. For the formation, okay, so this is this question. See, again, it's a very simple question, not that difficult. For the formation of this particular complex from the tetra-aqua copper 2 ion, upon reacting with the ammonia, the formation constant K1, K2, K3, K4 are given respectively for replacing one water molecule in each step. Calculate the formation constant for this complex. Okay, what it says that, see guys, sorry, you have given this complex Cu H2O times 4, okay, 2 positive, and you are reacting this with, say, ammonia, NH3. And for this, K1 is given, and that value is 1.9 into 10 with the power 4. And when this reaction happens, it will form, see, one of the ammonia will replace one of the water molecule. So whole thrice I can write here, and then I can put NH3 over there, positive charge here, and one of the water molecule will be replaced. And in the second step, again, say you are reacting this with NH3, and in that case K2 is given, and that K2 is having the value of 3.9 into 10 is the power 3, and then it will form CuH2O. Another water molecule would be replaced, so we'll have only 2, and then you are having the 2 of NH3, just like that. Put positive over there, and they have asked this, calculate the formation constant for this one. So formation, how we can calculate the formation constant? So I can write that formation constant with beta. This would be nothing but K1 multiplied by K2. K1 is 1.9 into 10 is the power 4 multiplied by K2, that is 3.9 into 10 is the power 3. Okay, and if you multiply, then the power would add up in that case. So 10 is the power 7. So there is no need to solve further. Check for the options where actually 10 is the power 7 is given. So only this particular option. So option D is the correct answer for this one. If you multiply 1.9 and 3.9 also, then it will give you the 7.4. So this is how you can solve the problem. Now moving to the next problem, what it says, problem number 12. What it says that blue color of copper sulfate solution becomes darker upon reacting with the ammonia, and you have been given 4 options. So it's quite simple actually, right? Say you are having, so I can write it here. You are having CuSO4 whole twice. It's a simple salt, and when you dissolve it in water, it will form Cu H2O times 4. Okay, say I'm putting 2 positive over there, assuming that it is in 2 positive, and when it reacts with the ammonia NH3, this complex changes from aqua to the amine complex, whole 4, 2 positive. It is stable, it is less stable. So your correct option is what? Ammonia forms a stable complex. So option C is looking the correct option in that case. Okay, now moving to the next problem. Okay, this problem is important and you have to learn how to solve such kind of the problems. The number of moles change in the reaction of 1 mole of this aqua complex, hexa aqua complex given with 2 moles of the ethylene diamine. So now it's quite easy, guys. It's not that difficult. So you have been given M H2O times 6, 2 positive over there, okay, and then you are reacting it with 2 moles of EDTA. No, not EDTA, ethylene diamine, 2 moles of EN. Okay, so you know it's a bidentate ligand, ethylene diamine, and that water is monodentate. This is quite clear. What it means actually, it means that 1 mole of ethylene diamine will replace 2 moles of water. Okay, and since you are reacting with 2 moles of ethylene diamine, that means it will replace the 4 moles of the water. So what your product would be like that? So you can write M En whole twice, and 4 water molecule would be replaced. Then you will left only 2 water molecules in the ionization sphere, sorry, in the coordination sphere. 2 positive was already there, and plus 4 of water molecule, H2O. And what is change in moles? Delta moles I am calculating. So delta moles is nothing, moles of products minus moles of reactants. Okay, so products, 1 mole of, you see 1 mole of this, 4 mole of this, that is 5. Reactant, 1 mole of this plus 2 moles of this, that is 3. It's simply 5 minus 3. Okay, so what you do, you put 5 here, minus 3 equals to 2. So change in moles is the 2 of a change in the moles, that is 2. So option B is the correct option, right? So this is how you can solve the problem. And don't look the problem in that manner that ethylene diamine is actually bidentate, so it will replace the 4 water molecules, so the change would be 4. It is not like that. You simply write the equation and then change, then calculate the change. Okay, so this is how you can solve the problem. Again, it's a very easy problem, not that difficult problem, but you have to apply a little brain before solving such kind of the problems. Okay, now my next problem, and this problem is actually the theoretical part. So if you have learned this particular problem, then it is easy to solve. If you haven't learned, or if you haven't read that particular problem is somewhere, then it is quite difficult to solve such kind of the problem. But this problem is quite simple. I told you, see, iron, that is Fe, is in +2 form in blood. Okay, and when it reacts with the EDTA, so it forms a stable complex. It forms a stable complex that can be eliminated from the body. So that means complexation. And you know this EDTA complex with iron. So I can write iron EDTA complex. Iron EDTA complex. Since it is hexadentate, it's a chelate or chelating complex. So iron, in excess iron in the body can be removed by the chelation process. Okay, so option C is the correct answer. Chemotherapy is used for the cancer, right? Precipitation reactions are different, which cannot be actually used in the body. and blood irradiation therapy is something different, right? So it's a theoretical question, not that technical. Now moving to the next problem, what it says? It says that the hybridization, the geometry of these two complexes. Okay, two complexes are given and you have to identify the hybridization and the geometry. So for this, guys, you can see here coordination number is 6 in that case. 6 cyanides are there. So it would have the octahedral geometry. So check the options where the first complex is having the octahedral geometry. So this complex is having octahedral geometry. Okay, in all the cases, first it is having the octahedral geometry, right? So you have to look whether it is G2sp3 hybridization or sp-D2 hybridization. Okay, so what it means actually, right? What is the meaning of that? In that case, you can see the iron is in +2 oxidation state, and iron is in +2 oxidation state is actually your 3D8 system, I suppose. 3D8 system. Let me check whether it is 3D8 or not. Okay. Iron 26, remove 2 electrons from here. It will form iron 2 positive, then it will form 24 electrons. And for 24 electrons, it is 1s2, 2s2, 2p6, 3s2, 3p6 and 3d6. Okay, it is 3d6 system actually, right? It's a 3d6 system. Okay, and this cyanide is a strong ligand. This cyanide is a strong ligand, and this strong ligand will force d electrons to pair up. And when the electrons are forced to pair in the d orbitals, that means you will have vacant d orbitals. And when you have the vacant d orbitals, the hybridization would be D2sp3. Okay, and remember, this is a trick also. However, I have solved very sequentially, but you remember, whenever your strong ligands are there, as in case of the cyanide, your actually low spin complex will form. Low spin complex means D2sp3 hybridization. Now check for the options, in which option actually the D2sp3 is given. So this is D2sp3, this could be your answer. This is sp3d2, this cannot be your answer. This is D2sp3, this could be your answer, and this is sp3d2, this could not be your answer. So you have to select between A and C. Now looking for your next complex, which is what? NiCl4 2 negative. So there are two ways of explaining this one. First of all, you can understand this Cl is bigger in size. So when, say, if it is forming a square planar complex, then the bond angle would be 90° between the two chlorine atoms. 90° bond angle between the chlorine and chlorine. If it forms tetrahedral structure, then the bond angle would be 109.5° between the chlorine atoms. So since there is electronic repulsion between the two chlorines, so these two chlorines are actually stiff as far as apart as they can actually. So they will increase the bond angle, right, to minimize the repulsion. So it forms the tetrahedral geometry. So look for the in which option it is given that tetrahedral. So if you check here, so in the first case it is given the tetrahedral. So it is looking like that your option A is the correct option in that case, right? This is the one way of explaining this one. And another way, if you want, then this cannot be your answer, right? If you another way, if you want, then nickel, in that case you can see here nickel is in +2 oxidation state, and when the nickel is in +2 state, it's a 3D8 system. It's a 3D8 system, right? And Cl is the weak ligand. Okay, when it's a weak ligand, that means no pairing of electron, because weak ligands cannot force the electrons to pair up. in the d orbitals, no pairing of electrons. When pairing is not there in the d orbitals and 8 electrons are there in that manner, 1 2 3 5, 1 2 3 4 5, and then you can put 6 7 and 8 electrons. So no d orbitals are available. When d orbitals are not available, the only option left is what? sp3, which leads to the tetrahedral geometry. So this is how you can solve this problem. Now moving to the next problem, what it says, question number 7, the correct set of outer orbital complexes. So this is something very important, how we can solve this one. So for this to solve, right, you can see, so first of all what I'll do, I'll write the oxidation state here. Iron is in +3 oxidation state, cobalt is in also +3 oxidation state, chromium is in also +3 oxidation state, and again cobalt is in +3 oxidation state. Iron we have already done. In that case iron is in +3, cobalt is in +3, and titanium is in +3. Okay, so this question is actually quite a good question, and it will take 5 minutes at least to explain. So if I write for this particular complex, sorry, Fe H2O whole 6, 3 positive, and iron 3 positive is 3d5. It simply means 5 electrons, 1 2 3 4 5, and water is weak ligand, that means no pairing of electrons. When pairing would not occur, that means no empty 3d orbital. So it will form, it will use outer d orbital, and the hybridization would be sp3 d2, but not d2 sp3, as inner d orbitals are not available. So this iron is your outer orbital complex. Now if you want to solve for this one, so here I am giving you the very important trick. Cobalt in +3 oxidation state, okay, in that case your ammonia would be the strong ligand, right? And you know it's a cobalt 3 positive is what? It is 3d6 system, but strong ligand ammonia would behave as a strong ligand, so the pairing would occur, pairing of electrons would occur, and when the pairing would occur, that means inner d orbitals, 3d orbitals are available for hybridization. That means d2 sp3 hybridization would occur. So it's a inner orbital complex. It's an inner orbital complex. So option A cannot be correct, because you have to find the correct set of the outer orbital complex. Now moving to the next one, say you are having this chromium complex. So it's quite simple. It's a 3d3 system, right? Chromium 3 is 3d3 system. That means 1 2 3 5, 1 2 3. 2 orbitals are already available, so these two would be used in the hybridization. Again it would be d2 sp3. So this is also inner orbital complex. So this cannot be your correct answer. Now moving to the next one, for iron we have already done, it is outer orbital complex, okay, and same is true for your this. If you see, in that case iron is 3 positive, okay, and in that case iron is 3 positive. It's a 3d5 system. Here again it is 3d5 system, and this F is the weak ligand, and no pairing of electron would occur. That means the situation will remain as such. D orbitals are not available, and when inner d orbitals are not available, it will undergo the outer orbital. So option C is the correct answer. It is looking like that the option C is the correct answer, right? And similarly you can go for the titanium here. If you want titanium 3 positive, and titanium 3 positive is it is 3d1 system. When it is 3d1 system, only one electron is there. That means all the d orbitals, 3d orbitals are available. So hybridization would be d2sp3. So d2sp3 will form inner, and sp3d2 will form outer orbital complex. So the correct option is actually your option number C. This is how you can solve the problem. Now moving to the next problem very quickly, what it says: according to the crystal field theory, the d electronic configuration of the complex is given. Okay, so these two complexes you see here. I'll write here actually. Fe H2O times 6 and 2 positive over there. Iron is in +2 oxidation state. When iron is in +2 oxidation state, it means it is 3d6 system, right? And when the crystal field splitting would occur, okay, this is T2G, sorry, this was Eg, this is T2G, right? And you have to fill the 6 electrons in it. So how you will actually fill these electrons? Since this is the weak ligand means this would be low, right? And pairing energy would be high. So electron will not pair up here, and you know the weak ligand will form the high spin complexes, and high spin complexes means first you will fill the electrons in all the available d orbitals. If the electron left, after that only then you will do the pairing. So how I can fill the electrons in it? Electron number 1, electron number 2, electron number 3, electron number 4, electron number 5, and electron number 6. So what the configuration you are having? You are having T2G4 and Eg2. Okay, now write the configuration for this one. COF6 3 negative, it is given. That means cobalt is in +3 oxidation state. Okay, when cobalt is in +3 oxidation state, it is another 3d6 system, and F is the weak ligand. Weak ligand means again the same situation. So the configuration for this would also be T2G4 and Eg2. Now look for the option where both the complexes are having the same configuration. See here you can see T2G4 Eg2, T2G4 Eg2. Okay, this is the correct one. So option A actually is the correct option in that case. This cannot be correct actually, because all the electrons are paired here, and this pairing in the T2G set will occur only when we have the strong ligand actually, which is not having here. This first one is fine, but second one is wrong, so this cannot be your answer. And similarly first one is fine, but second one is wrong, so this cannot be your answer. So this is the option A. This is how you can solve the problem. Now moving to the next problem, what it says. Okay, in the square planar ligand environment, the energy of the metals p orbitals raised. Okay, so what it means actually, say first of all you are having these 3 orbitals, px, py and pz. Okay, and say your complex is square planar. You are having your square planar complex. For square planar complex you are having dsp2 hybridization. That means out of the 3 p orbitals only 2 will have the higher energy, and which 2 will have the higher energy we'll see here. Say for example in the center I am having my metal, and these are the ligands, and dsp2 hybridization is actually occur in that case. So if you see here, this is my plane X and this is my plane y. Now your metal's d orbital, say this is px of the metal and this is py of the metal, and ligands are also, see, ligands are also approaching from the x and y plane. So these ligands in the xy plane, they will exert more repulsion on this px and py, and due to this repulsion the energy of the px and py would be raised. So your correct option should be px and py would have the higher energy. Okay, now looking for the options. Okay, option B is there, which is the correct one. Okay, this is how you can find the answer. Now moving to the next problem, and what it says, okay, again it's a theoretical part. If you have learned the valence bond theory, read the valence bond theory, shortcomings of the valence bond theory, then it is easy to find the answer. And if you haven't learned this valence bond theory, then it would be difficult for you. Okay, so we can check which one is the correct. VBT explains the mixing of orbitals. Yes, VBT says hybridization scheme. It use hybridization, and when it uses the hybridization, definitely the mixing of orbitals would be there. So this is the correct. So I can write C for this one. It fails to predict any distortion in the shape of the complexes from the regular geometry. Okay, it fails to see which incorrect statement actually, right? Incorrect statement I'm talking about. It fails to predict any distortion. Yes, see, this is also correct, because VBT actually explains the geometry on the basis of the hybridization, like sp3, dsp2, d2sp3 or sp3d2. Okay, so they give the regular geometries, but any kind of the distortion it cannot predict. So it is also the correct one. Third, the metal ligand bond in the coordination complexes is considered as the coordinate covalent bond. Yes, since we are actually considering the hybridization, so it will have the covalent character. This is also the correct one. So these are the correct statement, A, B and C. D, it satisfactorily explain the color of the, okay. So you know the VBT cannot explain the color of the complexes. Color of the complexes can be explained on the basis of the crystal field theory. So this is the false statement, and you have to look for the false statement also. So your option D is the correct answer in that case. Okay, now moving to the next problem, and this problem is what? Which of the following is not a square planar complex? Okay, so you know, for a square planar, complex you have to have dsp2 hybridization, and for dsp2 you should have inner, or you can say the 3D orbitals, and 3D orbitals would be available when ligands are strong, in case of the strong ligands. Okay, so in that case you see cyanide is the strong ligand, so it will force the electrons to pair up in the d orbitals, and the 3D orbitals are available. It will undergo dsp2 hybridization, and it is a square planar. Okay, then moving to the next problem. Okay, see, these are the platinum complexes. So remember one thing very important. See, it doesn't matter whether you are having the weak ligand or the strong ligand, but if you have the say 4D and 5D metals, it's a trick. They actually form the square planar complex, because due to the bigger size of the 4D and the 5D metals, they stabilizes the square planar structure better than the tetrahedral structure. Okay, so this cannot be your answer. These two cannot be your answer. The only option left is this one, and this problem I have already solved. I have already explained in my earlier slides. Okay, nickel 2 negative, nickel 2 positive ion. Chloride is a bigger ligand. You can use any of the trick, like bigger size of the chlorine. According to the Vesper theory you can apply, or you can go for it's a weak ligand, so there is no pairing of the electrons in the d orbitals, so d orbitals are not available, so obviously it will choose sp3 hybridization, and for sp3 hybridization it would be tetrahedral. So option D is the correct answer in that case. Now moving to the next problem, And this is my last problem, and this is my 20th problem. And what it says, the complexes with halide ions mostly are, okay, this is quite simple. They form the actually usually the halide ions due to their greater size, right, and greater size and their weak ligand nature. So halide ions are weak ligands. So when the ligands are weak, they cannot force electrons to pair up in the d orbital. Okay, so they form the high spin complexes. So option A is the correct answer. This is, again, you can see it's a theoretical part. So these are the 20 problems on coordination chemistry, and this was the part 3. If you like the lecture, please share the tetrahedron chemistry classes with your friends. Don't forget to like the video, and if you are a new viewer here and watching this video for the first time, so kindly subscribe the tetrahedron chemistry classes and go through the playlist of the tetrahedron chemistry classes, which I have exclusively made for the CSIR NET, GATE and IIT JAM examination. Okay guys, so that's it for today. Thank you very much. Hello friends, welcome back to the tetrahedron chemistry classes. So guys, if you remember, I have started that 150 practice problem series on coordination chemistry, and it is my 4th lecture, and today I'll solve 20 brand new problems based on the various aspects of the coordination chemistry. And this is my first question, and this question says that identify the correct order. So this this question is asking about the correct order, and this question actually is based on your spectrochemical series. Spectrochemical series, right? And you know the spectrochemical series deals with the ligand field strength. Ligand field strength. Okay, and you know on the left hand side you are having halogens, and on the extreme right you are having nitro and cyano group. So they are the strong ligand on the right hand side, and on the left hand side you are having the weak ligands, weak field ligands. I have made a mnemonic device to learn the spectrochemical series also. You can search in the YouTube, right, in the coordination chemistry section of tetrahedron chemistry classes. So if you check the option here, you will check whether the cyanide, in which option actually cyanide is having high field strength. So this cannot be your answer A, because in that case your fluoride is actually having high strength, right? Similarly, oxalato is given here. This cannot be your answer, so you should opt from B and C. In both the options you can see the cyanide are these cyanides are having in both the option high field strength. So either of these two could be your answer, right? And then you see here in the next option here a nitro group is given, and this nitro group is actually your better or the strong, having the strong ligand field when compared to the oxalato, right? And one more thing here you can notice that your chloride is a better chloride is actually the poor having the weak ligand field strength when compared to the fluorine. It is given in the your spectrochemical series. So it seems that your option C should be correct in that case. So you will mark the option C. Okay. Now moving to the next problem, what it says, in an octahedral field, the d orbitals that feel the most strong repulsion. Okay. Now this question is quite simple. You can draw, first of all, you can draw the octahedral complex, right? This is your octahedral complex, and you are having the ligand. Say this is L1, L2, L3, L4, L5 and L6, and in the center you are having the metals d orbital. And you know the metals d orbitals actually having two groups. First three you can call it as T2G, and last two you can call it as EG, doubly degenerate, and T2G is the triply degenerate. This T2G group is in between the axis, and the EG, they are actually along the axis, So if you put the axis here in that in this particular complex, say for example this is your, say y-axis, and perpendicular to it you are having your x-axis. So this is say your x coordinate, this is your y coordinate, and you can see the ligands are approaching along the axis L1, L2, L5 and L4. These ligands are approaching along the axis. When the ligands are approaching along the axis with the electron pair, you know the ligands are having the electron pair, so they will exert repulsion on the electrons which are present on the d orbital, and those d orbital which are directed towards your these ligands will be affected more. You know this Eg orbitals are along the axis, so the most repulsion would be field by dx square minus y square and dz square. So this should be the correct answer. This is the very easy and the basic problem of the coordination chemistry. If you select the options, then you can see this A, dx square minus dash square and dz square, they will feel the more repulsion in the octahedral complex. It's a very straightforward and easy question. Now moving to the next problem, the problem number 3, what it says, which of the following has the highest crystal field splitting? So again, you can see this question is based on the spectrochemical series. Spectrochemical series. Okay. A strong ligand gives high crystal field splitting, and you have been given only three ligands, H2O, NH3 and your cyanide, and among all these, according to the spectrochemical series, this cyanide is the strongest one, okay, and this water is the weakest ligand, while this ammonia is of moderate strength. So check the option where the cyanide is given, and if you check these option, then cyanide is given in the option 3. You can blindly mark option D. You can blindly mark that option 4 is the correct option. And one more thing, you see, you may have different transition series 3D, 4D and 5D series, right? And these 4D and 5D series, they have high crystal field splitting due to diffused 4D and 5D orbitals. Okay, so that's why the correct option should be just like that, because these d orbitals 4D and 5D are very diffuse, so metal will actually approach more close, see, ligands will approach more close to the ligands and the splitting would be high. So in that case you can mark that option D is the correct option. Now moving to the next problem, what it says that if a complex solution gives the intense charge transfer band at 569 nanometer region, then how one could detect the comparatively weak DD transition. So guys, you see weak DD transition. So it generally happens when your actually signal is not sharp, actually you are getting your weak signal. Then to enhance that signal strength, what you generally do, you use the more amount of the compound. That means you will prepare the more concentrated solution. So this is the very straightforward answer. You can mark option D as the correct option. You use the more amount of the your complex. That means you will make the more concentrated solution. Then you can also observe the weak DD transition. Okay. Now moving to the next question. Question number 6, and what it says that CFSE for this MnH2O6 3 positive is given as 21,000 centimeter inverse, and the pairing energy is given as 28,800 centimeter inverse. Identify the nature of the complex, whether it is high spin, low spin, or it is a spin crossover, or it is none of them. So for this you should know some important point, and that important point is what? When you are having say MnH2O6, you are having this one, 3 positive is over there, that means manganese is in +3 oxidation state. When manganese is in +3 oxidation state, it's simply your 3D4 system. Okay, it's simply your 3D4 system, and say it is an octahedral complex. So if you draw the weak field and the high field, and that means low spin or the high spin complexes in the crystal field splitted diagram. So you will get the diagram in that manner. Okay. Say first one I am saying that it is for high spin, and second one I am calling it as low spin. And when it is high spin, that means you have to fill 4 electrons in that manner, 1, 2, 3 and 4th. And if it is low spin, then 1, 2, 3 and 4. Okay. So you see I have drawn the two splitting pattern for high spin and the low spin complexes. Now we can calculate the crystal field splitting, right? For the two complexes, I can calculate the CFSE. So CFSE for this particular complex would be calculated by negative of 0.6 of delta O, right? And what it means? It means negative 0.6 multiplied by the value is given 21,000 centimeter inverse. This value is given, and if you solve this particular value, then it will give you negative 12600 centimeter inverse. This is for your high spin complex. Now you can calculate for the low spin complex, right? CFSE for low spin complex, and for low spin complex it would be like that, negative 0.4. Okay. See, formula is what? 0.4 of delta O plus pairing energy. Okay. So negative 0.4 you can write as such, and delta O is given 21,000 centimeter inverse, plus pairing energy is also given, because in that case you can see in the low spin complexes we are forcing electron to pair up in the T2G shell, so we will require that pairing energy, and that pairing energy value is 28800 centimeter inverse. And if you solve this particular value, then this will give you minus 4800 centimeter inverse. Okay. Now if you compare the two energies, right, that means energy of the high spin complex with the energy of the low spin complex, then you will find that for a high spin complex it was negative 12600 centimeter inverse, right, and for low spin complex it was negative 4800 centimeter inverse. Since the value is in the centimeter inverse, you can convert them into the energy by the reciprocal relation. Then you will clearly find that this particular value is lower. High spin, for high spin it is lower. You must know that E is equals to SC by lambda. So this is the inverse relationship, and if you convert that, then actually your higher value of this will correspond to the lower energy. That means the energy is lower for this one, and you know that we generally prefer the lower energy processes. So your complex would be high spin complex in that case. So correct answer should be A, option A, high spin complex. Okay, now moving to the next problem, and my next problem, what it says that the absorption band of COF6 negative shows the two maxima because of its okay, fine. See, in that case what you can do, say this is the question number 7, and you have been given COF6 negative. When it is in 3 negative, that means cobalt is in +3 oxidation state. You can calculate oxidation state by your own, and you know this is a weak field ligand. Fluoride is the weak ligand, and fluoride, if the fluoride is the weak ligand, then this particular complex would be high spin complex, and cobalt is in +3 oxidation state, is clearly your 3D6 system. Okay. And now what will happen in that case, you can see how we can solve this particular problem. Say if you draw the configuration, right, if you write the splitting in that pattern, in that manner, right, say this is the ground state. Ground state means lower energy state when there is no absorption of any kind of radiation, and you have to fill how many electrons? 6 electron in that case. So we will write 1, 2, 3, 4, 5 and 6 because it's a high spin complex. So we will fill a single electron in all the available orbitals, right? And then only then we will do the pairing as I did in here in the T2G shell, right? And in that case you can see this is the EG orbital, okay? And when EG orbital is having the electron, that means in that case John-Taylor distortion would occur, JT distortion. JT distortion. Now if you draw the excited state for this particular complex, so what will happen in the excited state? You can fill the electrons. See what will happen during excitation. One of the electron which is present here, it will go up actually, right, in that particular state. So what configuration you will have in that case? 1, 2, 3, 4, 5 and 6. So this is actually your excited state. Excited state means higher energy state when the system absorbs energy. Again in that case you can see in the EG orbitals there are electrons, 3 electrons are there. So again John-Taylor distortion would occur, John-Taylor distortion. And whenever the John-Taylor distortion would occur, in that case actually in the UV spectrum you will get 2 energy maxima. One is this one, other one is this one. So the correct answer for this particular option is John-Taylor distortion. So option B in that case is the correct option, but this question is actually a very good question and very helpful in the GATE and in the IIT JAM examination along with your CSIR NET. Now moving to the next problem, what it says, okay, identify the magnetic properties of the two complexes given, whether they are both are diamagnetic, both are paramagnetic, and say one is diamagnetic, other is paramagnetic. Okay, see this is actually a very good question. It's a very good question, very concept builder actually, right? This is very important question. So for this what you will do actually, I am giving you the trick actually. In the first complex you are having this one, whole twice Br2, okay, and your second complex is Ni En whole twice SCN whole twice. These two complexes are given, and in both the cases where nickel is in +2 oxidation state, and when nickel is in +2 oxidation state, it's simply a 3D8 system, nickel +2. And when you have the 3D8 system, so see due to this 3D8 system, in that case actually your John-Taylor distortion would occur, John-Taylor distortion, and when the John-Taylor distortion would occur, then you will have the tetragonal distortion, right? This you have to remember. Now trick is that in solving this particular problem, you compare the strength of ethylene and Br, ligand field strength, based on spectrochemical series, based on spectrochemical series. So their strength are very different, very different strength. And whenever you are having a complex which is having actually two different kinds of the ligands attached with it, right? Then and if the difference in their strength is too high, so in that case your complex would be your low spin complex. So it would be tetragonal. Why tetragonal? Because it is nickel 2 positive 3D8 system, so John-Taylor distortion would occur. So tetragonal distortion would occur in that case. And whenever the difference between the ligand field strength is very much, very actually, see very big difference between the ligand field strength, in that case low spin complex would form, low spin complex. So this complex is your low spin complex. So what is the meaning of the low spin complex? You can straightforward do the splitting in that case, since they are the octahedral complexes, right? Ethylene diamine is a bidentate ligand. So you will count ethylene amine twice. So 2 ethylene diamines are there, 2 2s are 4 to 6, and you are having 8 electrons to fill here. And I am doing for your low spin complexes. So 1, 2, 3, 4, 5, 6, 7 and 8. So it's a low spin complex, and whenever this complex is the low spin complex, you can see it is paramagnetic in nature. It is paramagnetic. So check the option where your first species is given as your, sorry, let me check whether it is 3D8 system or something else. Nickel is, yes, it's a 3D8 system, 2 to 4 to 6 to 8. So this should be actually your paramagnetic. So let me check, did I make any mistake in explaining this one? This is the low spin complex, tetragonal, use difference, then it should be diamagnetic. Okay, let me check what mistake I did here. Okay, so no problem. So I actually did a mistake here in that case, so I can delete that mistake from here, since we are considering the John-Taylor distortion. Okay, so it is very essential that we should take the John-Taylor diagram for this one, right? So if I am taking the John-Taylor diagram for this one, for this particular complex, so initially the position would be just like that, T2G, and this is EG, right? This is without distortion, EG orbital, and this one is the T2G orbital, right? And you know, under John-Taylor distortion, this will further split, and this will give you, actually say this one is dx z, and this one is dyz, and this one is your dxy. Okay, so this is how they split actually, and this will also split in that manner. This is dz square, and this one is actually your dx square minus y square. Okay, now you have to fill the 8 electrons in it. So how you can fill the 8 electrons in it? 1, 2, 3, 4, 5, 6, 7, 8, right? So it is looking that diamagnetic. So this should be your diamagnetic. Okay, now check here actually. Now in that case you can compare the strength of the ethylene diamine and this thiocyanate ligand. If you compare their strength, so there is not much difference between the ligand field strength. So comparable ligand strength, comparable ligand strength. When ligand strength is comparable, then in that case high spin complex would form, high spin complex. Now if you fill the electron according to the high spin, so what will happen in that case? So there would be no change in this particular pattern, but this thing will change, that dz square, and this is your dx square dash y square, and you have only 2 electrons to fill. So what you will do, you will fill 1 electron here and another electron here. So this should be paramagnetic. Okay, this should be paramagnetic. So this one is paramagnetic and this one is diamagnetic. So check the option where complex 1 is diamagnetic and complex 2 is the paramagnetic. So you see complex 1 is diamagnetic here and complex 2 is the paramagnetic. So option C is the correct answer in that case, and it's a very good question. You have to apply a lot of knowledge into it. First of all, ligand field strength you have to apply, then you have to think about the further splitting of the d orbitals under tetragonal distortion, and only then you can decide the magnetic behavior of these species. But nonetheless, this was a very good question, very good problem. Now moving to the next problem, what it says, my next problem is identify the electronic configuration of this complex and this complex, right? What they are actually. So I already told you in my earlier classes, cobalt is in +3 state. When cobalt is in +3 state, your ammonia in that case would be a strong ligand, right? In that case, your ammonia would be the strong ligand. Okay, and if the ligand is the strong, it simply means that it is your low spin complex, okay. And if you check this particular complex, again the same thing, your cobalt is in +3 oxidation state, okay, but here you can write in that manner, okay, and your water is the weak ligand. This water is weak ligand. When the ligand is weak, that means the complex would be high spin complex, okay, high spin complex. Now now fill the electrons. Cobalt, in both the cases, cobalt is in +3 oxidation state, and +3 oxidation state of cobalt means it is having 3d6 system. That means 6 electrons are there. So now now draw for this one. Here you can see, right, in that manner. How many electrons? 6 electrons you are having, and you are making the low spin complex. 1, 2, 3, 4, 5, 6. So the configuration is what? T2g6 Eg0, because there is no electron in the Eg orbital. Now if you make the, for this particular complex, here just like that, okay, and now you have to fill 6 electron in it according to the high field. This is 1, 2, 3, 4, 5 and 6. The configuration is T2g4 and Eg2. So check this option. For the first complex you must have this T2g6 Eg4. So this is T2g6 and T2g6 Eg0, and in the second case you are having T2g4 Eg2. So option C is the correct option, while rest other options you can very easily omit from here. Now moving to the next problem, what it says actually, the problem number 10, a complex showing the molar extension coefficient in the range of this during transition, identify the probable geometry and the type of the transition. Now this question is quite tricky, and it involves the lots of theory, lots of concept, and by solving this particular problem you will be able to learn very large number of the concept in it. Very important problem, and in fact it's a very nice problem. So I'm telling you, whenever your LMCT would occur, whenever your LMCT means ligand to metal charge transfer band, in that case actually this epsilon is your molar absorptivity, or molar extension coefficient, and you have learned about this in your Lambert-Beer's law, right, in the UV spectrum. And whenever ligand to metal charge transfer would occur, the value of epsilon would be very high, up to 10 raised to the power 5. But you are finding that the range is given 100 to 1000 liter per mole per centimeter. So it cannot be your LMCT kind of the transition. So you straightforward cross the first two options, because for them actually the value is very, very high, right? And see, if you have for example, if you are having that octahedral complex, and in this octahedral complex, if DD transition is happening, and you know, in the octahedral complex, due to the center of symmetry, presence of the center of symmetry, it is LAPORTE forbidden. Due to the center of symmetry. In that case actually, when this happens actually, then this molar absorptivity ranges from 10 to 100. Unit is same, liter mole inverse and centimeter inverse. I am not writing the unit again and again, right? So what you can do, you can also cross this particular option. That means octahedral and LAPORTE forbidden, because for octahedral and LAPORTE forbidden DD transition, your epsilon value would be this one. So naturally your correct answer would be the last one, okay? See, in tetrahedral, see what will happen. if your sp3 hybrid, sorry, if your sp3 hybridization is there, in that case sp mixing would occur, and when the sp mixing would occur, then LAPORTE selection rule is partly allowed, okay, but not in the perfect tetrahedral structure, but it should be your distorted tetrahedral structure, distorted, because distorted tetrahedral structure would not have your center of symmetry, but perfect tetrahedral structure would have. So the correct option would be distorted tetrahedral and partially allowed LAPORTE selection rule, right? So option D is the correct one, but it's a very important question. Now moving to the next problem, what it says that the coloration of HgI2 and this usually comes due to, now this problem is again a very nice problem, very good problem, and how we can solve this problem, you can see here, your mercury in that case is in +2 oxidation state, and you are also having the 2I negative in that case. I am writing in that manner, but don't forget this compound is just like that, not 100% covalent, not 100% ionic. So definitely it will have the vacant d orbital, because mercury is in +2 oxidation state, and this is having the extra electron pair in the form of the negative. So here you can see this ligand will transfer electron to the metals d orbital. So basically in HgI2 it is your LMCT, right? So check the option where in the first, for the first option where actually the LMCT is given. So DD transition not given, first option MMCT not possible, but third option, yes, this could be your correct answer. You can write it, you can mark this as such and cross this one, because you have seen that it is actually happening the ligand to metal charge transfer complexes. So there is no need to check for the second option, but if you want, then also you can check for this particular one. So I can write here only, this is positive, okay, and in that case it is 2 positive, iron is 2 positive, and if you calculate the oxidation state, then this iron would be 3 positive. So in this particular complex, what you are observing, one iron is in +2 oxidation state, okay, and another iron is in +3 oxidation state. So what will happen, from this metal the electron will transfer to this metal. It is simply your MMCT, metal to metal charge transfer band. So this is the correct option, option C is the correct option, but it's a very important problem, very nice problem. Now moving to the next problem, what it says that you can see here, an octahedral complex absorbs in the 545 nanometer, then its respective tetrahedral field splitting. Okay, now again it's a very important question, very good question. And how we can solve this particular question? For this you have to learn some of the relation. If you want to calculate tetrahedral field splitting, so I am writing this for delta TET, that would be equals to 4/9 of delta octahedral, right? If you know this particular relation, then you can calculate. 4 is constant, 9 is constant, you need delta octahedral. So delta octahedral is what? It is basically a kind of energy, and we can calculate this by using hc by lambda. Okay, this is how we can calculate it. So if you calculate this, so what will happen? H is the Planck's constant, and that Planck's constant is having 6.626 into 10 raised the power minus 34 joule into second. Unit is very, very important. You can write it as such. Then your speed of light, that is 3.0 into 10 raised the power 8 meter per second divided by your wavelength, which is given here 545 nanometer. Since we are using speed of light in the meter, so you will convert that nanometer into the meter. So you will write 10 raised the power minus 9 meters. Now you will cancel the units, second and this second will cancel out, and this meter and this meter will cancel out, and whatever the result you will get in the joule. If you solve this particular relation, I have already solved this particular relation, and I got this value 3.65 into 10 raised to the power minus 19 joule, right? This is the value of the delta O. Now it's very easy. You put the value here, 4 by 9 multiplied by 3.65 into 10 raised to the power minus 19 joule. Okay, if you solve this particular relation, then definitely your answer would be 1.60 into 10 raised to the power minus 19 joule. So this is the numerical problem, very important one. And if you check the option, then it is given here 1.6 into 10 raised to the power minus 19. Option C is the correct option for this one. Now moving to the next problem, what it says, question number C, you see many coordination compounds. Oh, it's a straightforward question. There is no need to waste time in that question. Generally in the coordination complex only DD transitions are there. Okay, and these DD transitions are responsible for the color of the complexes. You can simply write the DD transition here. You can check here. Yes, option B is the correct option. Electronic transitions in the d orbitals, that is the DD transition. It's a very simple question, very straightforward question. Now moving to the next problem, the problem number 2, what it says, again it's a very simple problem, guys. It says that the increasing order of CFT in the octahedral field. Then this question is based on the spectrochemical series. Spectrochemical series, right? And the ligands which you have been given, one ligand is the chloride and another ligand is the ammonia and last ligand is the cyanide. You know the cyanide is having highest strength. That means it is the strongest ligand, and when the ligand is the strongest, that means crystal field splitting energy CFSE would be highest for this one. So check the option, and for this actually the CFSE would be lowest CFSE. So check the option where the first is having the lowest and second is having the highest. Cyano complex is having the highest one. So if you check here, this cannot be your here you can see this cannot be your answer, but this could be your answer and this could be your answer. This cannot be your answer. Out of these two, anyone could be correct, but option B is looking more correct because ligand field strength follows this particular order. Okay, so option B is the correct answer in that case. Again, it's a very simple, straightforward problem. Now moving to the next problem. See, it's a theoretical problem, and you should remember some of the theory to solve this particular question. And you have been given the pink color of the ruby. So ruby is nothing, it is the crystal of Al2O3, right? And it is having the impurity. Impurity means dopant of Cr3 positive. So check whether the ruby crystal is given. In that case, presence of doped Cr2O3 into the crystal, this could be your answer, right? Because this is the crystal, as I have already told you. Impurity or the dopant is what? Cr3, this could be your answer. Presence of the doped Al2O3, no, doped Al2O3 is cannot be your answer, because Al2O3 is not the dopant. Dopant is actually this one, so this cannot be your answer. And then DD transition in the octahedral environment. Okay, since it is chromium 3 positive, and what is the meaning of the chromium 3 positive? That means it is having the 21 electrons in it, right? So it's a 3D system, and in the 3D system the DD transition would occur. Okay, in that case DD transition would occur. So this could be the correct option. Okay, and there is no question of the ligand to metal charge transfer complex. There is no like that. So option first and third are correct one, and check in which option it is given. It is given in the option A. So in that case your option A is the correct answer. Okay, now moving to the next problem, which is if a complex absorb in the 640 nanometer wavelength region, the complex will be okay. So for this you have to have an idea about the color wheel. So for example, say this is your color wheel, just like that, and I am drawing it in on my way, and you can do by yourself also. You can have your trick also. So I am starting with the lowest wavelength from here, that means Vibgyor, VIB GYOR, right? And this R will have the highest, this will have the highest lambda, and this will have the lowest lambda. I already told you this thing actually, VIBGYOR. In that case, lowest lambda, and it goes on increasing, and it is having highest lambda. Okay, and for this you should actually remember some of the data also. For violet or the blue, the range is actually 400 nanometer. Okay, and for actually say 400 for this one and 475 for this one. Green is on little higher side, that is 510, and yellow is another, you see, higher side, 570, and orange is 590, and this is somewhere around 650. Okay, so you can see here what it is observing. It is observing 640. That means absorption of 640 means, that means absorption of red light. So absorption of red light, and whatever the color would be there for that particular compound, that would be complementary to this one. So if you check the range, actually this 640 is in between 590 and 650. Complementary of red is green, because red is absorbed, so it should appear green. And if you check this range actually, so orange is there in the absorption, so complementary is actually blue, so you can write blue here. So your complex would be blue green in color. Check whether this option is given or not. Yes, option C is given here, which is blue green in color. This is how you can solve the problem. Now moving to the next problem, what it says, question number 5. The transition between complex of this and this are, okay, again it's a very, very important problem, very nice problem, and you have to learn lot about this particular one. Say for example, I'll write nickel H2O 6 2 positive. Okay, and it simply means when nickel is in 2 positive, so here it is in 2 positive oxidation state, and when it is in 2 positive oxidation state, you can write it as 3D8 system. There is no problem in that. Okay, and this water is the weak ligand. Okay, when water is weak ligand, then definitely it's a high spin complex. And for high spin complex, if you draw the crystal field splitting in that manner, then you will fill the electrons in it. That means 8 electrons you have to fill, weak field. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now you see the transition. If the transition would occur in that case, say it is the ground state, say for example, and if the system absorbs energy, so what will happen? One of the electron will jump from here to here, and when it jumps from here to here, then you will have this configuration, just like that. So you can fill the electron 1, 2, 3, 4, 5, 6, and one has jumped over there. एक यहाँ आ गया, right? Over jump. Now in that case you can see 2 unpaired electrons. In that, see, this was your excited state. In that case, one is this one. One is this one, and see 6, 7, 8, and then it is having 2. Wait a minute. Okay, sorry, I forgot to put one more electron here. Okay, that's now it is 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so another two unpaired electrons are there. So 2 unpaired electron here, 2 unpaired electron here, that means spin allowed transition, spin allowed. So in that case it is spin allowed transition. Now same thing would be for this complex also. If you write that NiCl4, 2 negative over there, that means nickel is in +2 oxidation state, that means it is 3D8 system and it's a weak ligand. So the complex would be high spin complex, and when in the high spin complex the configuration would remain same in the ground state as well as in the excited state. For this also here spin allowed transition is there. So in both the cases, whether you are this complex or this complex, spin allowed transition would be there. Now check the options. Spin allowed, okay, fine. Spin allowed, fine. So this could be correct answer. Spin allowed, this could be correct answer. Spin allowed, this could be correct answer. Spin forbidden and no, spin forbidden, so this cannot be your correct answer because you have checked already that both are spin allowed actually, right? Now check the geometry. You see here this particular one is octahedral complex, and in the octahedral complex, due to the presence of the I, that is center of symmetry, the transition would be LAPORTE forbidden. So I can write it here, LAPORTE forbidden. So it is LAPORTE forbidden. So in that case, you see your ABC could be the correct answer, but in the first case you are having the LAPORTE forbidden. So this is say this one is saying LAPORTE allowed. So if it is LAPORTE allowed, then this cannot be your answer. Now you have to check between B and C. So both the options are correct in this case. Now check for the next complex actually. So this complex, you know, already I told you this is actually your sp3 hybridization with tetrahedral geometry, and whenever the sp3 hybridization would occur due to sp mixing, LAPORTE selection rule is partially allowed. We have solved a problem just like this earlier, right? So it is partially allowed. So second case actually LAPORTE allowed. So spin allowed and LAPORTE allowed. So that means your option C should be the correct answer. So option C is the correct answer, because in the option B it is given LAPORTE forbidden, but in the tetrahedral structure due to the sp mixing, LAPORTE is little allowed. So this is how you can solve the problem, but it's a very important, very nice problem to solve actually. Now moving to the next problem, what it says, this says that the question number 6, which of the following is not a pi acidic? So it's a simple question based on the molecular orbital diagram, and I'm telling you your C2H4, it is actually what, CH2 double bond CH2, it is having empty pi orbital, and whenever it is having the empty pi orbital, it can accept electron from somewhere. So it is actually pi acidic or pi acceptor, same. And carbonyl, you know, it is what, it is actually carbon triple bond oxygen, just like that. So it is also having the same condition, so it is also the pi acidic. Whenever you will find the multiple bond present in it, then you blindly say that okay, it is actually the pi acceptor, okay. And similarly your nitrogen is also having the triple bond, right? So it can also have the empty pi orbitals, right, whether empty pi anti-bonding orbitals. So it is also the pi acidic one. So option left is what, only this one. So B is the correct answer, and you should know it is this oxygen is actually 2 negative. That means 2 extra negative are there, and they will occupy the pi orbital. So that means pi orbitals are not empty, so it cannot accept electron from somewhere. So that's why it cannot be considered, it cannot considered as the pi acidic or the pi acceptor. Actually it is a pi donor actually. So it's a donor. Option B is the correct answer in that case. Now moving to the next problem. What it says, the bands observed in the visible region for the complex of this, okay, this question again, very nice, very important problem based on Orgel diagram, guys, okay. And to solve such kind of problem, first of all you will see what is the geometry of this complex? This complex is actually tetrahedral. Coordination number is 4 and it's a weak field ligand, and the weak field ligand you will see generally the low spin complex will form, and that means it would be a tetrahedral. Okay, and cobalt in that case is in the +2 oxidation state, and when your cobalt is in +2 oxidation state, it simply means it's 3D7 system, right? It is 3D7 system. So what you can do, you can make the weak field complex. This is T2G and this is Ag, and now you have to fill the 7 electrons in it. 1, 2, 3, 4 and 5, since it is a weak field, 6 and 7. Okay, so now you can calculate the spin for this one, and spin is what? 2 small s plus 1. So 2 into how many unpaired electrons? 1, 2 and 3. That means 3 by 2 plus 1, 2, 2 cancel, 4. That means 4 is there. Fine. And we'll use that 4 again in that case. And it's a tetrahedral D7 system. And if it is the tetrahedral D7 system, then you simply actually draw the Orgel diagram, if you remember. So I am drawing just like that. Say this is the center, and here this is first one. Say this line is going just like that, and other one is coming just like that. Splitted terms. These are the splitted terms, and second one is going that in that manner, and say third one is coming in that manner. Okay, and this is actually your tetrahedral D7. Okay, this trace, this left hand side trace. Okay, and splitted term for this particular, see, if you have these number of the electrons, then you can calculate the ground state and various terms possible, and then you can put those terms in this particular Orgel diagram to get the details. So different terms for this one would be just like that. This would be A2, and multiplicity, you see, I have actually calculated here. You can write 4A2 actually it is. And second one is your, this is another term which is 4T2, and this is another term which is 4T1, and lastly it is the T1 due to the p orbitals. This is p, right? So if you want to know the transitions, how many transitions would occur in that case, so for this how many transitions are possible? First transition you can see from here to here, which would be from AT2 to 4T2. Second transition from 4A2 to 4T1, and third transition is from 4A2 to PT1. So transition is actually starting from the 4A2. Now check the options. This could be your correct answer because transition is starting from A2, but this cannot be your correct answer because in this case this option is showing that transition has started from T1, but it is not like that. Similarly, on the same ground you can cross the option D also, because they are also showing the wrong transition, but these two could be correct. And theoretically you can see what I have, the first transition A2 to T2, A2 to T2, very fine, then A2 to T1, very fine, then A2 to T1P, very fine. So this is looking the correct option. And but you should remember a very important, very theoretical term. You can see this is, if you calculate the energy difference between the two, actually this is the energy which is going in that manner up. Okay, so if you calculate the energy, this is the very low energy transition. This is very low energy transition, and due to low energy, its wavelength is very high. Lambda is high. It is so high that this particular transition falls in IR range. This transition falls in IR range and it is not visible or not observed in the UV range. Okay, so we cannot observe this particular transition. So we can omit this transition. We will have only two transitions actually. 4A2 to 4T1 and 4A2 to PT1. So you see two transitions are there. In that case, we can observe two transitions, 4A2 to 4T1 and 4A2 to 4T1P. So correct option is the option C. Okay, this is how you can solve the problem, and it was a very, very important problem, very fine problem to solve. Okay, now moving to the next problem, what it says, the combination of S value and L value. Okay, now you can see here, if I can write, say I am having 3P, say I am having this this is known as the term. Whenever you have the S value along with this L value, then this combination will give you the term. So you can see here, this was S value and S value, their combination would give you the term. Okay, so correct option would be what? Option number D. Option D is the correct option in that case. It will give the term actually. Okay, now moving to the next problem, and probably this is my last problem, and another simple problem actually, right, in that case. So a number of microstates for a given term. So I already told you, if I have been given this term 3P. So for 3P, you know, this is the value of S, and capital S is calculated with this formula 2S plus 1, as I already told you in one of my problem earlier actually. And P is actually your L value, capital L value, and which is calculated by 2L plus 1. Okay. And if you have been given the term, so you will calculate the microstate by using this formula 2S plus 1 and 2L plus 1. So correct option is 2S plus 1 and 2L plus 1, and that option is given here in that case, option number C, right. This is how you can solve the problem. Okay, so these are the 20 problems which I have solved in my lecture 4. I hope you understand the problem, you are grasping the things, right. And if you are really liking the video and explaining something from me, right, so please like the video, share the tetrahedron chemistry classes with your friends also, and if you are a new viewer here, please subscribe the tetrahedron chemistry classes and go through my playlist which I have exclusively made for CSIR NET, GATE and the IIT JAM examination. Okay, so that's it for today. Thank you very much guys. Hello friends, welcome back to the tetrahedron chemistry classes. So guys, in today's lecture I am going to solve another 19 question based on your various aspects of the coordination chemistry. Okay, and my first question you can see here, what is written here over there. You have been given this particular complex, that complex is your titanium complex, right? And you see the absorption maxima due to DD transition is given, and for this particular transition you have been given the energy in this particular form, in the form of the wave number, and that is 20,000 centimeter inverse, and you have to calculate the crystal field stabilization energy for this particular complex. So how to solve such kind of the problems? You see, you have been given titanium complex, and in this titanium complex you are having titanium in 3 positive oxidation state, which simply means it's a 3D1 system. Okay, when it is in 3D1 system and it is an octahedral complex, so the splitting would occur in that manner. Above you will have your EG set of orbital, and below you will have your T2G set, right. So this is your T2G, okay, and this is your EG, and it is having only one electron. So this electron can jump from here to here. This is called the DD transition, and you have to calculate the energy. So you have been given actually 20,000 centimeter inverse, and that 20,000 centimeter inverse is actually what? It is your 10 of dq. So whether you can write as delta O or 10 of dq, it will not make any difference, but it is better to write 10 of dq. It is given here, and that value is given actually for this particular transition, right. Delta O is given for this one, and the value of this is actually your 20,000 centimeter inverse. Okay, so if you want to calculate the delta O or the dq, so it simply means you will divide that 20,000 value by this 10, and then you will have your answer, that is your 20,000 it is given here, and that will give you here 2000. Okay, so this 2000 centimeter inverse is the value of the dq. And you know, if you want to know the CFSE, crystal field stabilization energy, then you can have very straightforward question for this, that is -4 of dq or delta O. -4 is already there, okay, and you are having your 2000 centimeter inverse. Okay, and if you solve that value, it will give you negative of 8000 centimeter inverse. So this would be your correct answer. Okay, now check whether the okay, it is given that option B is the correct one, and option C is also given in the form of the 8000 centimeter inverse, but you have to know the actually relation to find the value actually, that is -4 of dq or simply -0.4 of delta O. You can use any of the formula for this one. So you have the variety of the things. I have solved these problems in my lecture series also. Now the next question, what it says that, and this question is quite simple. You see, the color observed for the complexes permanganate ion and the CDS cadmium sulfide. Okay, so what it means actually, if you if you are having this magnesium, permanganate MnO4 negative, if you calculate the oxidation state, so your manganese is in +7 oxidation state, and when it is +7 oxidation state, it is having empty d orbitals. Empty d orbitals it is having. Okay, and your permanganate ion is given, that means oxygen negatively charged is given here. So what will happen, this ligand, this oxygen ligand will give the electron to the metal d orbital. So basically it's a ligand to metal charge transfer band. So this transition is ligand to metal. Okay, now if you calculate your cadmium sulfide, your CDS, okay, that means cadmium is in +2 oxidation state and sulfide is in 2 negative oxidation state. It simply means that your cadmium actually will have your 5s of the electrons, and again the electron will transfer from your ligand to metal. So it is also your LMCT, ligand to metal charge transfer band. So you have to choose the option where both are having the LMCT kind of the transition. And if you check, so your option D actually seems the correct option. Okay, and you should know the very important point, due to this particular transition, your cadmium sulfide, what is the color of the cadmium sulfide? It appears actually yellow due to this LMCT. Okay, and permanganate ion, you know, it is intensely purple, intense purple you can write. Okay, so this is how you can solve the problem based on this. Now moving to the next problem, what it says that, you see, for MLCT transition, transfer of electrons occurs from where to where. So basically this question is based on your ligand field theory, right? And but it's quite simple to explain such kind of things. See, if you what it says, what the question says, you are having that MLCT, that means metal to ligand. For this, metal should be rich, electron rich. Metal should be electron rich, and when you consider d orbitals, okay, when you consider the d orbitals, it should have electrons. It should have electrons, right? And this will transfer electron to the some other orbital. So generally what happens, you see, if you do the crystal field splitting in that manner, okay, so you will have your T2G set here or EG set here, and if it is tetrahedral, then this order would be reversed. That means EG will come down and your T2G will go up. So this T2G set may have the electron, this EG may have the electrons. So the transfer basically of the transfer of electrons occurs from either from T2G or from EG metal orbitals. Metal orbitals. So first check options. EG and T2G sets on metal, yes, it is possible. EG and T2G sets on metal, yes, it is possible. Filled pi orbital ligand, no. Ligand to ligand, it is not possible. So you can cross the option third. and then Eg sets of metal to so this could be your answer. Okay, but this metal to ligand charge transfer bands or the complexes, the necessary condition is that your ligand should have empty pi antibonding orbitals. So, a transfer of electrons would occur either from T2G or Eg to the low lying pi antibonding molecular orbital. So, your correct option would be in that case, if you check all the options, okay, this option A is the correct option. So, this is something very, very important. Whenever the metal to ligand charge transfers occurs in the complexes, right, it occurs due to the transfer of the electrons from the molecular orbitals of your metal like T2G or Eg to the low lying, which is this one, pi antibonding molecular orbital, okay, which it should have this character actually. Now, moving to the next problem, what it says, the free ion term symbol for 3D3. Now, this question is quite simple, guys. There is no need to worry about this. You have been given this system 1, 2, 3 and 5. How many electrons? 3 electrons are there, and it is not and you see you will put 3 electrons in that manner. Why I have been given the 3 parallel spins of all the 3 electrons? Because it says that free metal ion. So, in the free metal ion there is no concept of your high spin, low spin, and it is a D3 system. So, it does not matter whether it is high spin or the low spin. So, you will put the electron in that manner. Now, what you do, you calculate the spin. Okay. So, spin is what? 2s plus 1. Okay. So, 2 is constant, and you know s 1, 2, 3, 3 electrons are there, 3 times 1 by 2 plus 1. Okay. What it will give you? That is 2, 3 by 2 plus 1, 2 gets cancelled, that is equals to 4. That means you will choose that option for which actually spin 4 is given. So, see here only for this particular option, that is option C, 4 is given here. So, blindly you can mark this option C as the correct option. There is no need to solve further. This question is based on a very simple way of calculating the total spin actually. However, I can solve the entire problem how to get actually the D and the F values, but I am not going to solve that much of things here. I am not going into that deep, because I have solved these examples in my lecture series extensively. If you don't know how to calculate, then you can go for the Russell-Saunders coupling by tetrahedron chemistry classes or LS coupling by tetrahedron chemistry classes in the YouTube. You will find the results. Okay, I have explained these things there in the very detail, right? Now, moving to the next problem, what it says, okay, my next problem says the number of the microstate for the P2 configuration. So, you have been given this P2 configuration and you have to calculate the microstates. So, how you calculate the microstates? So, for microstates actually p orbital is given, and you know whenever you are having the p orbitals px, py, pz, so it can accommodate 6 electrons. Okay. So, total capacity of the p orbitals is to accommodate the 6 electrons. So, you will write factorial of the 6, okay, then divided by how many electrons are there? 2 electrons are there. So, what is the difference between the fully occupied p orbital and the electrons are present in the right now in the p orbital, that is 6 minus 2, that is 4. So, in the denominator you will write the factorial of 4 here, and this should be multiplied by how many electrons are there? 2 electrons are there. So, you will put 2 here, factorial of 2. So, if you solve this particular problem, then you will find 5 factorial, okay, and then 4 factorial, then 3 factorial, and after that you have 2 factorial divided by 2 factorial into 4 factorial. So, this 4 and 4 gets cancelled, 2 and 2 gets cancelled. So, 5 3 is a 15. So, basically you will have the value of the 15. So, 15 microstates are possible for this one. So, you can correct, you can mark this option B as the correct answer. Now, moving to the next problem, what it says that the energy order for the ground state D2 ion is, okay, see guys, this thing is quite simple, and this problem is quite simple because in all the options in the A, B, C, D, you are having only the ground state, see the value of actually L is F. So L value is given in that case, and that value is F, right? It goes to F actually. How? You see S, P, D, F, and for this your L value should be 0, 1, 2 and 3. Okay, so in this way you have been given, and you have been given the D2 system. So for D2 system, if you write, so you will have how many electrons? 1 and 2. You know it is plus 2, it is plus 1. Okay, so that means the L value is 3, 2 plus 1. So I can write 2 plus 1, that will give you the 3. When it is 3, it belongs to the F. So this is how you can calculate the F. And if you want to calculate the spin, so again it is quite simple. You see 2s plus 1. Okay, so 2 is here and 2 by 2, because total see half spin of this one, half of is this one, that means total of 1 spin, right? So this will get cancelled. Okay, so 2 1s are 2, 2 plus 1 3. So in all the options you are having the 3 and the F value. Now you have to go for the J value actually. So you know, whenever you have given this term, actually S spin is over there, this is L value, this is J value. So S you have 3, L you have 3, you have to calculate the J value, and to calculate the J value we have the options whether the your D subshell is half filled or more than half filled. So it is less than half filled. In that case it is less than half filled. I am not going to calculate actually the J value, but I am giving you the trick, right? And the trick is that whenever your F subshell is the half filled, then your lower energy state will have the lower J value, right? Lower J value will have actually lower energy, will have low energy. When less than half filled, less than half filled d orbitals are there. Okay, so now you can see here the J value, which is the lowest J value in that case. So you have been given J value in that manner, 2, 3 and 4. You know that 2 is the smallest and your 4 is the highest. So in that case you can mark this option D as the correct option. Okay, so this is how you can solve this particular problem. Now moving to the next problem, what it says, and my problem is what? Absorption band of vanadium 2 positive ion gives the transition band of 12,300 centimeter inverse, 18,500 centimeter inverse and 27,900 centimeter inverse. Identify the transition corresponding to the 12,300 centimeter inverse. Okay, this question is based on the Orgel diagram. Okay, so how you solve this particular problem? You have been given vanadium 2 positive. Okay, vanadium 2 positive. See, vanadium 2 positive means it is having the 21 electron. When it is having the 21 electron, it's simply a 3D3 system. So you have to draw the Orgel diagram, or say Orgel diagram for the D3 system, or you should know actually the transitions which are possible for your D3 system. So what you can write, say I am drawing in that manner. Okay, and this is here, say. So this actually is your 4p state and this is your 4f state. Okay, and if you calculate the spin for this one, 2s plus 1, okay, or it will come 2 into 1 by 2 into 1 by 2 into 3, because 3 unpaired electrons are there, plus 1. Okay, and what it will give you? It will give you the value of the 4. Okay, that's why this 4 is written here. So the splitted term would be like that: 4 A2G, and here you see 4 T2G, and next is 4 T1G, and it is also your 4 T1G, but it is of p character. Okay, so the transitions which are possible in that case: First transition is from 4A2G, 4T2G. Second transition is from 4A2G to 4T1G of P character, and third transition would be from 4A2G to 4T1G of P character. Now check the options. Whether a transition is happening from T1G, no, it is not possible, so this cannot be your answer. And similarly, you can see here the transition is not happening from T1G, this cannot be your answer. But you see the ground state in that case, in both the cases it is actually 4A2G, so these two could be your answer, right? But I am telling you, whenever you are dealing with the low energy transition, so the lowest energy transition would be from 4A2G from T2G, because this corresponds to the lowest energy actually, right? This one and this one. So the transition which is responsible for this one is 4A2G to 4T2G. So this is the correct option, and that option is given in the option number C. Okay, so this is how you can solve this particular problem. Now moving to the next problem, what it says, the combination of S, L, J and MJ value. It's quite simple, guys. If you have seen my lecture on Russell-Saunders coupling, basic aspects of the Russell-Saunders coupling, then you can straightforward mark this as state, right? So whenever you have this L value, whenever you have this L value here, J value here, okay, and your S value here, it is actually called the term symbol, okay. And if you have only S value and N value, see, this is your term, okay, and this is your term symbol. Microstate is something different. When you include actually the magnetic quantum number in it, so it will give you the state, right? So it's again a very important question. So you can mark option D as the correct option, right? And now my next problem, which is the problem number 6. What it says, the identify the order according to the Russell-Saunders coupling. And you know that your Russell-Saunders coupling is nothing but it is your LS coupling, where your azimuthal quantum number, orbital quantum number and your spin quantum number interacts to actually give some terms actually, okay. So for this actually Russell and Saunders both actually assumed that your spin-spin coupling value would be the highest. So what they actually what they assumed actually, the highest would be spin-spin coupling, okay. And then after that they assume that lowest is your spin orbit coupling. Spin orbit coupling would be lowest, spin and orbit coupling would be lowest. So check the option where your SS is having the very highest value. So in that case you can see, okay, the option is given in the very different manner. Spin orbit is, in that case it is maximum, so this cannot be your answer. Again you see this is the lowest, this is, see, spin coupling is the actually you can see it is the highest, okay, fine. And spin orbit, you see spin orbit is the lowest, it is fine. So this could be your answer, okay. And third, spin orbit is greater, no, it is not possible. And in that case spin, this is also not possible, because this option says that the orbital coupling is greater than the spin coupling. So it's a theoretical part. For this you have to learn this thing. So what you can do, if you are watching the lecture, then you can write this question in your notes also. It's a very important question, okay, based on the theoretical concept of the LS coupling. Now moving to the next problem, what it says, among the following couple has the couple has not belongs to the same Orgel diagram. Okay, again this question is based on the theoretical knowledge of the Orgel diagrams, how to construct the Orgel diagram. And if you have studied properly the constructions of the Orgel diagrams, then it would be very easy for you to find the answer. Otherwise it would be difficult for you, right? But it's a very straightforward question, and I'm telling you, actually this, you see this D1 and D6, right? And D1 D6 actually they forms the one Orgel diagram actually, okay. See, one in octahedral and other one in the tetrahedral. So this is the correct, okay. D4 and D9, okay, this combination is also there, there is no problem in that. And see, they are actually the Orgel diagram type 1, Orgel diagram type 1, and D2 D7 is also there, but D4 D8 they cannot see, since actually D4 and D9 have already made a combination here, so it cannot make the combination with the D8. So correct option is this one actually. So this is not a couple, and the question is asking about not a couple actually. So option D is the correct one, while all are the couple diagram, right, in the orgel. You know, in the orgel diagram actually you draw the two parts actually. First is octahedral, second is your tetrahedral, and you use the whole analogy and all these things, right. You can go through the details of the orgel diagrams in my coordination chemistry lecture. Okay, now moving to the next problem. What it says, okay, Tanabe-Sugano diagram is useful to analyze. Okay, again this question is based on this is the theoretical question. If you have studied the Tanabe-Sugano diagram, then you would be very easily say that it is used to actually analyze your UV visible spectra. So what in Tanabe-Sugano diagram we do, we actually analyze the UV visible spectra, and with the help of this UV visible spectra, we will actually assign the bands present in it, and once we get the bands in the Tanabe-Sugano diagram, then we can calculate actually your delta O value. So you can calculate actually crystal field splitting or the ligand field splitting, right, with the help of the UV spectra. So correct option is the option number A. We will analyze the UV spectrum. Right? IR we will not analyze here. Fluorescence spectra, there is no concept, right. All of them cannot be your answer. So correct option is your option A. Now moving to the next problem, what it says. For tris ethylene diamine nickel 2 ion, the bands are at 11,000, 18,500 and 30,000 centimeter inverse. Calculate the dq value for the complex. So again, see guys, it's a very simple question, and for this actually you have to have an idea about the Orgel diagram. Okay, so nickel, you have been given nickel in 2 positive state. Nickel is 28, and when it is in 2 positive oxidation, it is your 26 having 26 electrons, and 26 electrons belongs to the first transition series. So it's a 3D8 system. So you have to construct the Orgel diagram. You have to construct the Orgel diagram for D8 octahedral. Okay, so I'll not actually make that diagram here, but I'm giving you the transition which actually generally occurs in that case. Okay, so if you draw, if you write the electronic configuration 1, 2, 3 and 5, you are having octahedral complex A you are having, and it is splitted in that manner. So you are having T2G here and you are having EG here. Now you have to fill the electrons in it, 8 electrons, 1, 2, 3, 4, 5, 6, 7 and 8. 8 electrons are there, that means 2 unpaired electrons are there, only 2 unpaired electrons. So if you calculate the spin, that would be 2s plus 1, that is 2 into 1 by 2 into 2 plus 1, right, that will give you the 3. Okay. So the transitions which are possible in that case, first transition would occur from say 3A2G to 3T2G. I have solved this particular problem 2 slides back actually. Second transition which is possible from 3A2G to 3T1G, 3T1G, and third transition which is possible is from 3A2G to 3T1G of p character. Okay, and whenever we are saying that the transitions, the energy for the transition is given actually. So in that case you should remember that the delta O value, it refers to the lowest energy transition, which is this one. Okay, that is from 3T2G to 3A2G to 3T2G. This for this transition it is given here, and you know it is given that delta O, which is actually delta O is what actually your 10 dq, right? And since it is the lowest energy transition, so you have to choose the option where you have the lowest energy transition is given, which is actually your 11,000. Okay, so what you do here, you will write the 11,000 here, which is in centimeter inverse, and if you want to calculate the dq, so what will happen, 1000 divided by 10, not 1000 actually, it was 11,000. Okay, it was 11,000 divided by 10. So it is 1100 centimeter inverse. 1100 centimeter inverse. This should be the correct option. Okay. So option D is the correct option. If you want to calculate the, if you want to calculate your energy also, see, if you want to calculate the CFSE, then you know the what is the relation, right? CFSE is what? Negative 0.4 of delta O. In this one, you can also calculate the CFSE. I have solved this question a few slides back. Okay. Now moving to the next problem, what it says, among the energy states of the D2 configuration, the one with the highest number of the micro state. Okay guys, so this question you can see here, whenever you have been given this term, this value actually, right, S and L value, then this is known as the term. Okay, this is S value is spin, this is S value, and in all these cases you see here, it is a term, it is a term, it is a term, it is a term. So all terms are given, and if terms are given and you want to calculate actually your number of microstates, so in case of the terms, your microstates would be calculated by using the formula, that is 2s plus 1 multiplied by 2l plus 1. So you will use this particular formula. Okay. So how we can solve? I am solving here only. So if you write 2s plus 1 multiplied by 2l plus 1. So what it says that 2, since spin actually is given 1 in that case. Okay, the spin is given 1. Okay, so how you calculate the value of the S actually, right? So you see, for this you are having 2s plus 1 equals to S. Okay. So what is given here actually, this 1 value is given here, so you will write 1 here and you will write S plus 1 here. So what you will have actually, if you solve this value, okay, am I making little mistake over there? Okay. Now coming back to the problem, I am actually directly I am solving this one. So whenever, see, this spin value is actually what I can do, I can delete this. Okay, sorry, please wait. Okay, now I am solving this one. This actually, this spin is calculated by the formula of 2s plus 1, and which is already solved in this. This will give you the value of the S, and this S is given here. So you will write, for this 2s plus 1 you will write 1, okay, and then you will write 2 and L. So 2 is the constant multiplied by, I already told you, you are having S, P, D, F, G, 0, 1, 2, 3, 4 in that manner. Okay. So your electron is in G. So you will write 4 here. Sorry, you will write 4 here, 4 plus 1. So 4 plus 1 5, 5 2 is sorry, 4 plus 1 5, 5 2 is 10. Okay. Or see, sorry, what I am doing, I am making a mistake. 2 4 is 8, 8 plus 1 9, 9 1 is 9. So total microstates are 9 in that case. Okay. Now if you calculate for this one 3p, so for this actually 2s plus 1 you will write 3 here multiplied by 2. Your electrons is in p orbital. For p it is actually having the value 1. Okay. So it is 1, and this should be added with this plus 1. So 2 1s are 2, 3, and 3 3s are 9. For this also your microstates are 9. And now calculating for the next one, F. So this value for 2s plus 1 you will write 3, okay, and your electron is in f orbital, so you will write 3 here, okay, 2 multiplied by 3, that is plus 1. So 2 3 is 6, 6 1 7, 7 into 3 21. So it is having the 21 microstate. And for D, spin is given that 1, so you will write 1 here, that is 2 electron present in D, that is again 2 into 2 plus 1, so 2 2s are 4, 4 1 5, 5 1s are 5, so it is having total 5 microstates. So in that case your maximum microstates are what, 21. So option C actually is the correct option for 3F. That would be the correct answer. Okay, this is how you can calculate. Now moving to the next problem, what it says that identify the ground term and the electronic transition bands for cobalt 2 positive ion. Okay, what you have been given in that question, you have been given cobalt is in +2 oxidation state, and when it is in +2 cobalt is 27, okay, +2 oxidation state means 25 electrons, and that means it is 3d7 system, okay, and the complex, you see the complex is actually the coordination number 4. If you check here, coordination number is 4 and cobalt is in +2 oxidation state, so it can have the option either a square planar or your tetrahedral. So it is a low field, it is a low field complex, so it's a high spin complex, so d orbitals are not available for this complex, so it is tetrahedral, right? Complex is actually tetrahedral complex. So TD I am writing for the tetrahedral complex, and for tetrahedral complex, if you draw the D7 tetrahedral diagram, so how you can draw? So I am not drawing, I am straightforward writing the types of the transition. So transition, you know, A2, and you will write 4 here. It is very easy to calculate the oxidation state. How? Sorry, not oxidation state, the spin actually. So splitting would be in that manner in that case. T2G on the lower side, since it is a tetrahedral complex, it is Eg. 7 electrons are there, so you have to fill the 7 electrons in it. 1, 2, 3, 4, 5, 6 and 7. So total 3 unpaired electrons are there. So 2s plus 1, which that is give you the capital S. 2 into 3 into 1 by 2 plus 1, that is S, right? So 2 gets cancelled and 4 equals to S. The S value is the 4. That's why I have written 4A2 here, right? And since it is a tetrahedral complex, so there is no need to write G here, because G actually used whenever your complex is having the center of symmetry. That means the G-rayed one. But tetrahedral complex are un-G-rayed one, so there is no need to write G over there. Okay. So when so transition would be just like that, from 4A2 to 4T2. First transition would be just like that. Second transition, your 4A2 to your 4T1, and third transition is from 4A2 to 4 of T1 of P character. Okay. So there is no need to include the G here. Now check the options. Here you can see in the option number 3, option A, you see the G is given here. So it is this cannot be your answer, because G used for the octahedral complexes. Similarly, on the same ground you can opt out option C also. Now you have to select select between B and D. So it seems that your correct option is which is the correct option? Transition A2 to T2. Yes, A2 to T2. Of course it is F, there is no problem. Then A2 to T1, yes, and then A2 to T1, yes. So option D is the correct answer in that case. So this is how you can solve the problem. You see guys, these problems are very important concept building problems, right? And if you practice such kind of the problems regularly, then there would be no problem for you to solve the question based on the based on your coordination chemistry, right? Especially in the CSIR NET, GATE and your IIT JAM, and even your G mains and G advanced examination, right? And now what is my next question? What it says that an octahedral ligand field. So this question is based on the ligand field theory. Okay, that G term splits actually, right? You have to know the Mulliken symbols and the splitting of the G term. So for this, see again, this is a theoretical question, but I am giving you, say first I am writing D here. D is for your dimensions. Okay, and then you are having the symbols, or just like that. Okay, so if your dimension is 1, you will use mullicans A or B, either mullican A or mullican B symbol. Okay, if the dimension is 2, then you will use E, and for 3 dimension, you know, it's triply degenerate, that is T, and for 4 dimension you will use G, and for 5 dimension you will use H, and so on and so forth. So you see, you focus here. For G, you should have the 4 term. How many terms? You should have the 4 different terms actually, right? So this G will split in the 4 terms. So now calculate the 4 terms. 1, see, A1G, EG, T1G. So total 4 terms are there. But in all other options actually 1, 2, 3, 1, 2, 3, 1, 2, 3 are given. So you can blindly mark option A as the correct option. Okay. However, this problem is based on the various aspects of the ligand field theory and your theoretical concept. You can go through the ligand field theory by tetrahedron chemistry classes in the YouTube to learn the concept in the big detail. Okay. Now moving to the next problem, what it says. Okay, you see, the correct order of hydration enthalpy for divalent transition metal ions. Okay, this question is based on actually your CFSE. So remember, see, if you are calculating hydration energy, I am not going to explain what the hydration energy is. I have explained this thing in the detail, and I am also giving you the playlist link of your coordination chemistry, right? So that you can have idea how to actually learn the things in the detail. Hydration energy is actually the energy released due to the hydration plus CFSE, crystal field stabilization energy. Okay, so that the ions which will have the CFSE included in the energy, hydration energy, they will have the higher value of the hydration enthalpy, and the species which will not have any kind of the CFSE, they will have the lower value of the hydration energy also. So if you see what I can give you actually, which ions will have 0 CFSE and which will not have actually any CFSE at all. So see, for example, you have been given here Mn2 positive, manganese is 25 and it is 23 electron, so it's a D5 system. When it is a D5 system, so it will have 0 CFSE. Okay. When it is having the 0 CFSE, so its hydration energy should also be low, because it is 0, see, E plus 0, that means total of E. So you have to select all these kinds of the species where actually the CFSE is 0. Okay. So I am not going into the very much detail of this, but I am giving you a simple plot actually how it looks like actually for hydration energy. Say this is it looks like in that manner. See, generally what can happen, it should have the straight line. This hydration energy should have the straight line in that manner. Okay, but you see what happens actually, some CFSE actually will include in this hydration energy, and we will not get this straight line, but we will get the hump just like that. Okay, just like that, this kind of shape you are getting. Okay, and for your information, for your knowledge, calcium ion is here because it is having no d electrons involved, so there is no concept of CFSE, so it should appear on the straight line, and it is appearing. And for manganese ion, I have already solved you, Mn2 positive, it is also having your 0 CFSE, so it is also on the straight line. Okay, and similarly, if you are having the zinc 2 positive, it is also not having any CFSE, so it is also on the straight line, right? But if you extend this line from here to here, just like that. Okay, so here actually your nickel 2 positive is there, and after nickel 2 positive, the second highest value is for your vanadium 2 positive ion. So here actually your V2 positive is there. Okay, while in all the line you see different systems are there, like here you see D4 is there. This is your D5, right? It is going on decreasing, it increases for D6, okay, D7, and it is highest for the D8, and in this manner you can actually solve the problem. So now if you solve the problem, you have to select whether the nickel is giving the higher value of this hydration energy. Okay, so nickel is not there in the here in the options, and nickel is not there actually, right? What you have, you are having manganese, iron, chromium, and this manganese. So you select for this one, manganese, where manganese is having the 0. So you see here manganese is 0, in that case manganese is 0. So you have to select between B and C, because in that case manganese is having higher value than your say this iron, which is not possible, and in that case also manganese is having higher value than iron, again it is not possible, right? So out of these two you have to select actually. Okay, now if you check, see, vanadium is actually having the higher energy, right? And after vanadium you are having, say, somewhere here iron is also there. Okay, so iron is also there. So if you properly check that, then your option would be just like that, say manganese, chromium, vanadium, and iron. For iron it is the highest one, followed by the, see, somewhere here iron is there, Fe2 positive. Okay, right, and you can see here this one. Okay, so this is actually the theoretical knowledge we should have, which you should have actually. So option B is actually the correct option in this case, it is looking like. Okay, so I am not going into the detail how to explain the things, but you should know something actually, right? So now moving to the next problem. For MnGAl2 spinal structure, the occupancy of S and P block elements in the void of. Okay, see, whenever you forms the spinals, okay, so you have two kinds of the voids. First is octahedral void, and then you are having the tetrahedral void. Okay, so your larger ion will go to the octahedral void, and smaller ion will go to the tetrahedral void, and when this happens, then your spinal is the normal spinal. Okay, and what you are having, you are having your magnesium 2 positive, bipositive, and Al3 3 positive, it is tripositive. So you see this tripositive actually is a smaller one, right? So it should go to the your tetrahedral void, but this aluminum ion has a special affinity for octahedral voids. Okay, though it is a normal spinal. So for this normal spinal also, this magnesium Mg2 positive ion actually, this will go in the tetrahedral void. Okay, and because this aluminum, see, it's a special case, guys. Aluminum is having more affinity for the octahedral void, so it will go there actually. So you can write here magnesium is, if you check the option, magnesium is in tetrahedral, aluminum is in octahedral, so your option B is looking the correct option. Okay, so this is how you can find. So if you don't know what are the spinals and or things, so what are the spinals, how we can classify, so probably in my next question series, okay, this question will come in the detail, then I will explain the concept of the spinals in little detail. But if you don't know about the details of the spinals, again you can go through my playlist of the coordination chemistry, or you can simply type the spinals by tetrahedron chemistry classes in the YouTube. You will get the result and you can learn the things there. Now moving to the next problem, what it says that the correct order of ionic radii for M3 positive low spin octahedral state. Okay. So this question, guys, you can see it's a straight forward question, and it's a very good question. See what you have been given in that case, right? You have been given nickel 3 positive, right? Nickel is 28, that means it is having the 25 electron, and you are dealing with the low spin complexes. So whenever you are dealing with the low spin complex, so it is what actually your 3d7 system, I suppose. Yes. Okay, and you are having electrons here, so you have to put 7 electrons in it. It's a low spin, 1 2 3 4 5 6 and 7. So Eg electron is having 1 electron in that case of nickel. Now if you go for your next ion, say your cobalt ion, CO3 positive, cobalt is 27, it is having 24 electron, that means it is 3d6 system, and if you do the crystal field splitting, okay, it's a low spin complex, so all the 6 electrons would go into the T2G set, 1 2 3 4 5 6, so this is Eg0. And similarly, if you calculate for manganese, Mn3 positive, so it's a simply T2G4 system, okay. And if you calculate for Fe3 positive, so it's a T2G5 system. And you know, if you arrange these metals in their actually atomic number, so manganese come first, atomic number of 25, then there comes the iron, which is 26, right, and after that you are having your cobalt 27 and your nickel 28, and you know the ionic radii decreases from right to left, left to right, it is decreases. So nickel 2 positive should have the smallest size in that case, right. But another thing you should notice that your manganese in the extreme left, so it should have actually the greater ionic radii. All are 3 positive ions. So you have to look for the option where manganese is having the highest value. So on this particular ground, you can opt out this one, because in that case manganese 3 positive is having the lowest ionic radii, which is not possible, okay. So but you see, this could be correct, this could be correct, this could be correct. So out of B, C, D, you have to select this one. Now you see here in the cobalt, where this cobalt is having no Eg electron. When the Eg electrons are not there, that means there is no electronic interaction between the ligands and these metal electrons, and there is no effect on the ionic radii. When there is no effect on the ionic radii, that means cobalt should have the lowest ionic radii in that case, right. So you have to select in the options where the cobalt is given. Here you can see the again you see cobalt is minimum here and cobalt is minimum here. So it's a tricky question. You see two options are matching, but this one is not matching, so you can opt out the third one. Now select between B and D. Now you can check the nickel and the Fe. See, nickel, in case of the nickel, you are having 1 electron. So when nickel is having 1 electron over there, then definitely your nickel will have the electronic repulsion between this Eg electrons and the ligands, right, or not in ligands actually, you can see the inter-electronic repulsion, which increases the ionic radii. So you will check the option where nickel is having the higher ionic radii when compared to your other species. So say your iron species, right, not other species but iron species. So in the option D, you see the nickel is having higher ionic radii than your iron. So option D is the correct one. But guys, it's a very good question, and you have to apply lots of concept of your periodicity and your electrons present in the Eg orbital and all these things, right. Now moving to the next problem, what it says. Also guys, this is the simple theoretical question, and for such type of these are the memory based question. And for these questions, if you have learned the concepts properly, only then you can answer. Otherwise, it would be difficult for you to answer such kind of the question, because it's a theoretical question. And your talc is basically your magnesium silicate. So straightforward, you can blindly mark this option A as the correct option. Okay. So however, see this also is given here, but you can see the silicon is 3 already here, but Si4 unit I will require for this one. Now moving to the next problem. Okay, there is no problem in that. So guys, I have finished these 90 problems today, and I hope you like the lecture, right. If you like the lecture, don't forget to share the tetrahedron chemistry classes with your friends, like the video, and if you are a new viewer, right, you are watching a video for the first time, right, please subscribe the tetrahedron chemistry classes, right, and go through the playlist made by the tetrahedron chemistry classes exclusively for the NET and the GATE examinations. Okay guys, so that's it for today. Thank you very much. Hello friends, welcome back to the tetrahedron chemistry classes. So this is Guys, my last lecture on 150 practice problems on various aspects of coordination chemistry, and so far I have discussed somewhere around 118 problem, right? So in today's class I am going to discuss another 32 problems, and which will give you the complete 150 problems of various types of coordination chemistry. Okay, so my first lecture in today's my first question in today's class is, you can see here what is written. Among the following, the biological system and corresponding mental center involved in the dioxygen transport. Okay, so this question basically belongs to the bioinorganic chemistry. Okay, but coordination chemistry, you know, the way has various application in bioinorganic chemistry and bioorganic chemistry also. That's why this question is here, and this question is again your memory based question. There is no technicality involved in it, right? So for this particular question, if you see here, for this particular question, hemocyanin copper basically is the correct answer. Actually, what happens in the deoxy form of hemocyanin, right? This is hemocyanin, and in its its deoxy form is colorless, right? And contains copper 1 ion. Clear? That transport oxygen throughout the bodies of vertebrate animals, right? So this is hemocyanin copper. You can mark as the correct option. Okay, and now you see my next problem. Identify the correct intermediate for the electron transfer reaction between between hexacyanoferrate 3 ion to aqua pentamine copper 2 ion. So what you can do, see, you can determine the oxidation state of iron. Iron is in +3 oxidation state, okay, and chromium here it is in +2 oxidation state. So if you write the if you write the mechanism for this one, so what is happening in that case, right? Copper, and your 5 of amines are there along with the water molecule. Clear? And 2 positive over there, and it is in +2 oxidation state, and your next complex is Fe CN6 3 negative. Okay, that means iron is +3 oxidation state. Okay, so definitely whenever, see, I told you in my lecture series on reaction mechanism of coordination compounds, I told you whenever you see such kind of the reaction, then the electron transfer would occur from the lower oxidation state to the higher oxidation state. So electron is transferring from copper 2 positive to iron 3 positive. Okay, and in that case what will happen, this water molecule will replace from here. Okay, it's an see, and your cyanide actually, right, this cyanide will forms a bridge between these two. So your species should be like that, your intermediate species should be like that. Chromium, now NH3 5 times, clear, and your cyanide will form a bridge. Okay, and it would be your Fe Cn 5 times, okay, and 2 negative, 1 negative over there. So this would be your correct option. Okay, and if you want, then you can check here. Okay, this one, option C, is the correct option. This is something very, very important. So basically electron transfer is happening in that manner actually, and cyanide groups, cyanide group which are connected to the iron actually, right, through carbon. See, it will replace the water molecule from the chromium complex, and see the mechanism, you know, it will happen through inner sphere. It is inner sphere mechanism. So I am not going to explain what is inner sphere, outer sphere mechanism. If you want, then you can learn from my lecture series, right, of coordination chemistry compounds, right. So it is inner sphere mechanism. Conditions are met for the inner sphere mechanism. Bridge is forming in that case, right. So this you can mark, option 3 you can mark as the correct answer, right. Now moving to the next problem. The reactions of the tetracarbonyl nickel with the ligand of trimethylphosphine and your methoxy trimethylphosphine yields this particular complex. Okay, so the reaction is, what kind of the reaction of this? So you can count the electrons actually. So what will happen, So see guys, to solve such kind of the problem, what we can do, we can count the number of electrons. You know, nickel is actually here is in zero oxidation state in that case, so it's a 3d10 system. Okay, so 10 electrons from the nickel, and carbonyl provides 2 electrons, and 4 carbonyls are there, that means 2 times 4, so it's an 18 electron species. Okay, and when it is 18 electron species guys, so you should remember this particular point. This will occur through SN1 mechanism, and it should be actually the dissociative type. So option A should be correct, because see, your 18 electron system prefers to the dissociative mechanism via SN1 process. So the correct option is the dissociative, option A. Okay, now moving to the next problem. The average residence time for an water molecule, for an aqua molecule in the first coordination sphere of this is 10 raised to the power minus 10 second. The value of the water exchange rate constant. Okay, now this question guys is quite simple, you know. See, basically your average residence time and rate flow. So I can write average residence time, right, and rate flow. They are inversely proportional. They are inversely proportional. So what will happen in that case? If your average residence time is 10 raised to the power minus 10, okay, then definitely, since they are having the inverse relationship, so rate flow would be your 10 raised to the power 10, okay, second inverse, because they have the inverse relation between them. So option B is looking the correct option. Simple problem. Now moving to the next one. The metal ion centers present in the cytochrome C oxidase. Again, see, it's a bioinorganic part, and this question is again based on your memory. If you have memorized this question, then it would be easy for you, otherwise it would be quite difficult. And our correct option is actually the copper and the iron. Basically, cytochrome C oxidase, it contains the two heme part, actually two heme groups, cytochrome A and a cytochrome A3. It is having cytochrome A3, cytochrome A, and two heme parts, and two copper center it is having. Okay, so basically copper A and copper B centers. So basically it is having iron as well as the copper. So correct answer is the option number D. Now moving to the next problem, what it says, in the deoxyhemoglobin part, again it's a memory based question, and for this actually you know the structural aspect of your hemoglobin. So basically in that case what happens actually, in this particular, see, deoxyhemoglobin, what it says, the deoxyhemoglobin, that means hemoglobin without oxygen, right? In that case, see, in this particular say iron is in +2 oxidation. Just remember one thing, in that case iron is in +2 oxidation state. So when iron is in +2 oxidation state, it simply means actually B and C cannot be your answer. You have to select between A and C, and remember in that case the high spin complex, actually high spin system for iron 2 positive is there, and in that case the metal ion is lowered from the heme group. See, if heme group is just like that, so metal ion is lowered somewhere here, so it is below the plane of the ring. So your correct option should be your A. Okay, again it's a memory based question, this cannot be your answer. Moving to the next problem. The next problem, what it says, the complex compound used in the chemotherapy of cancer. So it's a very simple question, and you have studied this question, or you have started to read this particular importance of platinum compounds in your +2, right? And you know the cisplatin is the compound which is used to treat the cancer actually, right? So your correct option should be option D, cisplatin. Again memory based question. Now moving to the next one, what it says, identify the correct statement for the ligand substitution reaction. Okay, it's a theoretical part, and such type of question can only be answered if you have learned the detailed aspects, each and every aspect of the different kinds of the reactions. Okay, only then you will be able to answer. Okay, now guys, if you see here what is happening in that case actually, right? What it says, that see, large negative value of delta V. Delta V is, first of all you have to understand actually what is your delta V. Basically delta V is actually volume, change in the volume. Okay, so I can write here delta V is the volume change, Okay, so what happens basically, see, I'm giving you, see, first of all, you should know that it is a kind of the associative kind of the reaction. Okay, when it is the associative kind of the reaction, that mean your option C is the wrong one. Okay, and this is also option D cannot be your answer because it is discussing both kind of the mechanism. Okay, now what happens in that case? In the associative mechanism, so I can write here, in the associative mechanism, right, the transition state is compressed relative to the reactant. So whatever the transition state is there, it is compressed, and compressed is what, relative to, so I am writing R2, that is relative to your reactants. What it means actually, smaller volume. It means the smaller volume. When volume is smaller, definitely the delta V would be negative. Okay, and that indicates actually the associative kind of mechanism. So delta V negative value indicates the associative mechanism. See, again, it's a theoretical part, so the option A is the correct answer in that case. Clear? Now moving to the next problem. Identify the incorrect statement. Okay, let me check what are the statements. Electron transfer may occur from inner sphere. Okay, both mechanisms are possible, so true, it is true. Okay, it is true. Long range electron transfers such as in cytochromes are most likely to occur. Yes, this happens actually. Okay, this happens. This is also true. Marcus Huss theory applies. No, this is false, because Marcus Huss theory applies to outer orbital complexes, outer sphere mechanism, sorry, outer sphere mechanism. So your option C is the correct, and it is the incorrect statement, and which is the correct answer in that case, right? And this is also true actually. Basically, when in an inner sphere mechanism, electron transfer between two metal centers involves a bridging ligand. I have just shown you with the help of the cyanide and water example, right, in a few slides back actually. So in that case, your option C is the correct one. Now moving to the next problem, what it says, in case of a reaction, the rate constant decreases with increasing pressure. The type of the okay, now this question, guys, you can see it's again a very simple problem. It's a dissociative mechanism. See what happens actually. The value of the volume of activation, listen carefully what I am trying to say actually. The value of the volume of activation can be determined by measuring the rate constant at different pressures. That means you take the different pressures and then you can determine the volume of activation. Okay, and for dissociative mechanism, volume of transition state is greater, right? Here you can see volume of TS is greater, right? This actually, this thing you have you should remember actually. Okay, and it will increase with increasing pressure. If you increase the pressure, and then this volume of transition state is also increases, and when this happens actually, so the rate constant decreases. Rate constant decreases. So if you apply this particular logic from here, so your option B should be the correct option. Okay, so in the dissociative mechanism it happens generally, but all these things you have to learn in detail actually, and I'm suggesting you, if you want to learn these things in the detail, then you can follow the Asim K. Das book. Okay, now moving to the next problem. The reaction of platinum, it is tetrahydroplatinate 2 ion basically. Okay, now you see this question is based on the trans effect. This question is based on trans effect, right? And you have been given actually the complexes, like you have been given I here, and you have been given the pyridine. So I am writing PY for this one. You have to consider the trans effect of this one. So if you follow the trans effect, right? So your say this having is actually this iodine is having the greater trans effect than your pyridine. Okay, so in that case, what you will do, like say I can write the reaction. Okay, I can delete this. There is no need to actually write this. Okay, so how the reaction goes in that manner? See, you are having your platinum in the center, and then you are having 4 of I attached in that manner. There is no problem in that. Okay guys, and it is in -2, right? And you are having the pyridine, say Py. So pyridine will replace any of the iodine from it. So you can write platinum and say you are writing Py here, then I, okay, and then you can write I and I. And I already told you this I having the greater trans effect than the pyridine. So what will happen now, if you do the reaction further with the pyridine, so you will replace either of these I, okay, not this particular I, because pyridine is having lower trans effect. Okay, and there is no replace. If you replace, if it is having the great I effect, there is no meaning of replacing this I, this pyridine from here. So your next species would be pyridine, platinum, pyridine, and you can write Py here, and then your I and I. Of course, you should focus on this particular one, right? Charges you should actually focus here, right? So I'm not putting charges over there. So in that case, what is happening here, your bipyridine type compound is forming actually, which is the cis one. You see the bond angle is 90 degree. So cis dipyridine type of compound will form. So option A is looking the correct option in that case. This is how you can solve the problem based on this. Okay, so I hope you are understanding the things, you are grasping the things correctly, and you are learning coordination chemistry in a new way by these solved problems. Now I am moving to the next problem, what it says actually. Okay, there is no problem. Okay, we can skip this page. Yes, this is your another problem, and now these are the different kinds of the problem. You will not find the options in it, but I will tell you how to solve such kind of the problem. What the question says, the electronic spectrum of titanium 3 positive ion has an absorption maximum at 20300 centimeter inverse. Calculate the ligand field stability per ligand for this question. It's a very important question, guys. Very important and very concept building question. How we can solve this particular question in that case, right? See, you are having, what you are having in that case, you are having titanium. Titanium is in +3 oxidation state. It simply means it's a 3D1 system, only one electron is here. And for this system actually your delta O, that means octahedral crystal field splitting, can be directly related to the maximum frequency of absorption, which is 2030 in that case actually. And the energy of the transition for this question would be given by the delta E equals to H C nu bar. Nu bar is the wave number, and this wave number has is given the value this much, right? So what you have to do, you can put the values, right? So you will put actually the Planck's constant, and that would be 6.62 into 10 raised the power minus 34, and unit, you know, joule into second you will use. Okay, and this value you will multiply with the speed of the light. Say it is 3.0 into 10 is the power 8 meter per second you are writing. Okay, and nu bar is given to you, and that nu bar is actually your 20300 centimeter inverse, and it is in meter inverse actually, right? And if you want to convert this into the centimeter inverse, so you will multiply that value with 100 actually. Okay, when you multiply this value with 100, only then it would be your meter inverse. Okay, this is how you can write. So actually this dimensions are very important, units are very important. So if you multiply all this, I have already multiplied, okay, and you will get the value 4031 into 10 raised the power minus 24 joule per molecule. So you have calculated for one molecule only, okay, because you have been given one of this, right? Now if you want to calculate for per mole actually, right? So if you convert this into per mole, then you will find what you will find 4031, okay, into 10 raised the power minus 24, and you know 1 mole is having the particles equals to the Avogadro's number, which is 6.023 into 10 raised the power 23, okay, right, and it is in again say joule per mole. If you divide this value with 1000, okay, and solve this value, so this will give you 243 kilojoule per mole. This I have already solved. I am not wasting time in solving this problem, okay. So this is actually for per mole, and see in the 1 mole, if you focus here, 1 mole of this particular complex is having 6 water molecule, and you have to calculate the ligand field stability per ligand for this particular complex. If you want to calculate for per ligand, right, so you can write you can write ligand field stability per water molecule or the per ligand. So that would simply equals to 243 divided by 6, right, and 6 4s are 24, 6 1 just, okay, 41 kilojoule per H2O molecule or the per ligand, right. So this is the answer, okay. Now moving to the next problem. What it says, the MLCT transitions are common in the complexes containing the aryl ligands, justify this, okay. So guys, this is a very simple problem, and whenever you have this, see if you see your aryl ligands, right, your aryl ligands are what, which are having the double bond in that manner, okay, and when this thing is there, and if you draw the molecular orbital diagram, then you will have the pi anti-bonding molecular orbital, which would be empty, and these empty pi bonding molecular orbital can accept the electrons from the metal actually, okay. So this is the reason actually this MLCT transitions are very common in the complexes containing the aryl ligands. I hope this makes the sense actually. So you should reply in that manner. If you have the bipyridine, phenolate type of the ligands, they have the empty pi anti-bonding orbitals, and these are actually very low lying. So these are very low lying, you should remember, low energy, they are having the low energy, okay, and therefore the promotion of electron from here to here is quite facile, okay, and that's why the MLCT transitions in such complexes are very common, okay. Very important problem, very nice problem. Now moving to the next one. Explain the following MLCT energy order. Okay, so this question, see guys, is very important question, and it's a conceptual problem, very important problem. So see, first of all, you should remember a certain thing, right. Whenever your LMCT is happening, ligand to metal charge transfer bands are forming in that case, okay. So in that case, actually the energy of such transition decreases if electron acceptor ability increases. This you should remember, right, for a particular metal ion. So basically what will happen, a metal ion which is most easily reduced to its lower oxidation state, basically it would readily accept the electrons from the ligands actually, okay. So if you see here, in that case the stability of the lower oxidation state, so I am writing here stability of lower oxidation state is in the order, right. So lower oxidation state for chromium is very high stability, then your molybdenum, and then your tungsten. So they belongs to the same group, right. Karmov, Karorpati, Murkh, woman. This is this mnemonic which I gave you to remember, Karorpati, Murkh, woman. So in that case, you can see the here you can see the lower oxidation state, stability of the lower oxidation state decreases when you go down the group in that case. So what it means, that means the lower oxidation state is very stable, low oxidation state, okay, and in that case you see in case of this particular chromium CrO4 2 negative, so x minus 8 equals to minus 2, x equals to 6, right. So chromium in that case will very readily accept electrons, it will very readily accept electrons and it will form the stable lower oxidation state. So the energy would be very, very low for the chromium particular complex. So this explains why this order is just like that. Okay. Now if you compare between molybdenum and your tungsten type of the compound, okay. So I think there is no need to actually explain these kind of things. So this order you can explain in that manner also, right, because this chromium can very easily see where lower oxidation state is very, very stable in case of the chromium actually, right. So see because chromium 6 can easily accept the electrons, but you see tungsten 6 and your other metal ions like your molybdenum 6, they cannot readily accept the electrons because they cannot stabilize the lower oxidation state. Okay, this is the basics of your coordination transition metal chemistry also, right. Now moving to the next problem, what it says, the problem says that hexachromium 3 ion is pale violet but chromate is intensely yellow. What causes this color difference? Okay guys, this is quite simple in that case. You see this particular complex, okay, this complex is octahedral complex, and in that case whenever the octahedral complex is there, your center of symmetry is there, and when center of symmetry is there, that means the transitions are LAPORTE forbidden, LAPORTE forbidden, but spin allowed. Okay, and if you see this chromium one, so it's a tetrahedral compound, right. So it is LAPORTE allowed as well as spin allowed, LAPORTE allowed as well as spin allowed. So when both kind of the selection rules are applied to the complex, definitely the color would be very, very intense color. Okay, and for this actually only spin allowed, though the color would be the very pale color in that case. Pale means light color in that case. I hope this makes the sense actually. Okay, so now moving to the next problem, and see I'm not going to explain actually your number of electrons. So you can count the number of electrons and then you can decide how they are spin allowed or spin forbidden, right. So I'm not going into that much of the detail, but I'm giving you this thing. Okay, if you don't know the spin allowed and the spin forbidden transition, then you can again follow the MLCT, LMCT kind of the transitions by tetrahedron chemistry classes, coordination chemistry lecture. Okay, now moving to the next problem, what it says that, okay, explain why the pale red color of this solution changes into intense color on adding it to excess concentrated hydrochloric acid. So guys, it's a simple problem, but you have to understand little things about this. Say you have been given this particular compound, COH2O times 6, okay, and C2 positive is over there, and you see here you are reacting it with HCl. Okay, when you react this with HCl, so it will form your this particular compound. Okay, 2 negative. So it's a tetrahedral compound. Okay, and it is an octahedral. See, it is why this compound is tetrahedral. Why not dsp2? Because it's a weak field ligand and electrons are there in the Eg orbital, so d orbitals are not free to give dsp2 hybridization. Okay, so sp3 hybridization will give you this particular geometry here. So if it is tetrahedral, that means LAPORTE allowed, LAPORTE allowed. Okay, and cobalt is in +2 oxidation state, that means 25 electrons, it's a 3d7 system. Okay, so spin allowed also, spin allowed as well as LAPORTE allowed. In that case only spin allowed but LAPORTE forbidden, LAPORTE forbidden. So this changes the color from pale to intense. Okay, so I hope this makes the sense actually. Okay, so in this way you can actually explain the various things actually. Okay, now moving to the next problem, what it says. This problem is the energy difference between T2G and EG levels are given for this particular complex. Predict the color of the complex. So see guys, for this you have to have an idea about the color wheel. So I am not going to explain that color wheel. Earlier in the earlier lectures I have explained all these problems there actually, right? So in that case, what you have given actually, the compound which you have given in that case is your this particular chromium ion. Okay, and you see CONH3 whole 6 3 positive, it is given here. That means cobalt is in +3 oxidation state, so it is having 24 electrons. That means it's a 3d6 system. Okay, and when it is 3d6 system, okay, so what will happen? So you are having this T2G and EG, and you know the cobalt in +3 oxidation state having ammonia. That means ammonia will act as the strong ligand in this case. So all electrons would be paired here. Okay, and now you see this value. Okay, this energy difference is given by this particular 22900. So you have to predict the color actually. So this is the wave number. You know, if you convert that wave number into your wavelength, okay, so this will give you what? 1/22900 centimeter inverse. Okay, and that will give you here 4.37 into 10 raised to the power -5 centimeter, and you can convert it into nanometer also. 437 nanometer. That means it is absorbing this one, and this 437 nanometer, basically it's a blue light. It's a blue light, so it is absorbing blue. It is absorbing blue. So the complementary of blue, as I think orange in the color wheel. Okay, it is orange, right? So it is a complementary color, so it would appear orange in the compound. So color of this particular complex would be orange, right? But for this you have to have an idea about the color wheel. Okay guys, now moving to the next problem. See guys, it's a simple problem. Antidote used in the mercury poisoning. I hope in your bioinorganic chemistry, or say some in pollution part, you have studied about Minamata disease. Okay, right? You might have heard about this one, Minamata disease, right? In Japan actually it was reported, and it was a mercury poisoning. More correctly, methyl mercury. So mercury poison. Sorry, see, very sorry for my handwriting. To go faster, actually I am mercury poisoning. Okay, I am going little bit slowing. Poisoning. Okay, Minamata disease. So for this actually you need the complexation. So EDTA is used in that case. Okay, you will use the EDTA for to actually overcome such kind of the problems. Okay, now moving to the next problem, what it says that, let me check what the problem is saying here in that case. Okay, my question is actually Fe3 positive ion forms a high spin octahedral complex. Okay, it is forming the high spin octahedral complex, then its magnetic moment. So guys, again see, it's a very simple problem. So how you can understand this particular problem? Fe3 positive, iron is actually your 26, that means it is having 23 electron, that means it's a 3d5 system. Okay, 3d5 system, and it is in octahedral field. So you have to put 5 electrons, 1, 2, 3, 4 and 5 unpaired electron. So mu s equals to what? N under root n into n plus 2, that will under root 5 into 5 plus 2, 7, 7 5s are 45, under root of 45, right? And under root of 45 means, right, 5 5s are 25, 6 is 36, right? So let me check how many. 23 electrons are there. Iron is 26 minus 3 electron, it is having 23 electron, 3d5 system. Okay, then n plus 2, 5 plus 2, 7 7 5s, okay, 7 5s are 35. I'm very sorry, right? Under root of 35 will give you somewhere, see, 5 5s are 25. So see, if you solve somewhere here 5 5s are 25 and remaining all, then you will find 5 here. So you can correct this as the you can mark this as the correct option. Okay, it's a very simple problem. Now moving to the next one, what it says, the magnitude of the delta O value depend upon. Okay, let me check what are the options given here. Charge of the central metal ion, yes, higher the charge, higher would be the splitting, it is true. Nature of the ligand, yes, if ligand is strong, then the splitting would be high, it is true. Principal quantum number of the D, yes, as the principal quantum number actually increases, then the splitting also changes, this is also true. So all of the above, actually option D is the correct answer in that case. Okay, now moving to the next problem, what it says, which one of the following divalent ion is expected to have the minimum octahedral ionic radii? Okay guys, this problem is quite simple in that case, right? So ionic radii, right, ionic radii decreases across the period. Okay, it decreases across the period, and I think decreases. So you have to actually see, titanium is 22, vanadium is 23, okay, and after vanadium you are having, say, chromium 24, manganese 25, all are 2 positive. Okay, in that case, right? So which option you will mark then in this case as the correct option, right? Minimum, you have to go for the minimum. So your titanium 2 should have, see, you can check here, titanium is 22, right? It is in 2 positive, that means it is having 20 electron, it's a D2 system. Okay, titanium is a D2 system. Okay, and your vanadium, actually you see, 23, it is 21, that means it's a D3 system. Okay, so in that case, actually it goes in that manner. So you have to, it is decreases in that manner. Which one of the following divalent ions is expected to have the minimum octahedral ionic radius? It is asking the octahedral ionic radii. So the correct option in that case, actually the option number, you can see this one, right? For this you can go for my ionic radii lecture. I have solved the problem based on this, so I am not going to explain this problem in pretty much detail. Actually you can do by your own. Okay, the ion which is expected to have John-Taylor distortion in an octahedral field. Okay, so for John-Taylor distortion you should know which kind of species will give you the John-Taylor distortion. Okay, in that case you see here, cobalt 3 positive, cobalt is 27, 3 positive means 24 electron, it's a 3d6 system, no problem. CO2 positive, low spin, that means 25, it is 3d7 system. Okay, then nickel 2 positive, it's 26, right, that means it is 3d8 system. Field is not given in that case. Okay, there is no meaning of the field in that case also. Mn2 positive, that means 23 electrons, that means it's a 3d5 system. Okay, the ion which is expected to have the John-Taylor distortion. So for John-Taylor distortion, you have to have which is expected to have the John-Taylor distortion in an octahedral field. This should be where 4th B, low spin, high spin, cobalt. Okay, if you low spin, I am making for a low spin. 1, 2, 3, 4, 5, 6. So Eg orbital is having 1 electron here in that case. Okay, this is having, see, if you draw for this one low spin, so it is not having any electron in the Eg. Eg is empty. So this will feel the John-Taylor distortion. So this option B is the correct option in that case, right? While in case of the nickel 2 ion and your Mn2 positive ion weak field, right, it is not this John-Taylor distortion is not very high. So I am not going to explain the remaining 2 parameters, and if you want to learn the details, then you can go for the John-Taylor distortion by tetrahedral chemistry classes in my lecture, then you will find the answer there. Now moving to the next problem, what it says, that the complex ion developing the highest crystal field splitting energy. Okay, so highest crystal field splitting energy you have to find. First of all, you have to check for the, see, higher the charge on the metal ion, higher would be the splitting. Okay, and first of all you should know the important thing. So it is actually, okay, they belongs to the same group. Okay, and you see they form the inert complexes, and cobalt, the first transition series can form your inert or labile, any one. Okay, and here the d orbitals are diffused d orbitals. Okay, so that means the splitting would be high in that case, high splitting. And if the charge is higher, then the splitting would be further high for this one. So according to me, actually for this 5th one, your option C should be the correct answer. Why? Because it belongs, see, it is 5, sorry, this is 5D series, this is 4D series, this is 3D series. Okay, so 5D, the d orbitals are very diffuse, ligands will reach more close to the metal, and this will give you the high splitting, and of course the charge is also 3 positive there. Okay, so you can answer in that way. If you don't know, then you can go through my lecture series, right, if you don't understand this thing. Now moving to the next problem, what it says, actually, pairing energy for cobalt 3 positive is this much, and delta O for the complex ion is this one. Then the complex is actually paramagnetic, then the complex would be paramagnetic or this one. Okay, see, there is no need to go in that much of detail. Okay, you know the cyanide is a strong ligand, so it when it is a strong ligand, so it is a low spin complex. It is a low spin complex, and cobalt is in +3 oxidation state. When cobalt is in +3 oxidation state, it is having 24 electrons. 24 electrons means it's a 3D6 system. So if you want to draw, now it's a low spin system, so you have to fill all the 6 electrons here, 1, 2, 3, 4, 5 and 6, right? You have to fill in electron in that case, right? But pairing energy is this much. So in that case, actually your EP is higher than your delta O. So pairing energy is higher, so we will actually not follow the phenomenon which actually involves the higher energy. Okay, so EP is lower in that case. I'm very sorry, it is very sorry. EP is lower actually, right? And delta octahedral is high, so EP is lower. So when pairing energy is lower, that means all the electron would get paired up in that case. So our complex would be actually diamagnetic in nature. Okay, I hope this makes the sense. The complex is the diamagnetic, right? Pair energy will low, so electron will tend to pair in the d orbitals. Now moving to the next problem, what it says that the oxide which adapts the normal spinel structure. So this problem I have already solved in my previous lecture. If you have seen that particular lecture, then you will be able to answer in that case. Okay, otherwise it would be difficult for you, right? So this you can see here, this one is actually the normal spinel. Okay, this is inverse spinal, this is also the inverse spinal. Okay, and I have given you the concept of the spinal in my last lecture actually, right? So if you don't know, then you can follow my last lecture, then you will understand actually, right? So I'm not going to explain this thing in detail because I have solved this particular problem. This not exactly this problem, but this type of the problem, right? Now moving to the next one. CFSE for a high spin system is 0, its electronic distribution. Okay, now this question is quite easy actually. Your crystal field stabilization energy, the value, right, is 0 in that case. Okay, and whenever the 0 a crystal field stabilization energy is 0 in the octahedral field actually, so it simply indicates that there are all electrons present in the, see, it's a high spin system. What it says, it's a high spin state. So what is the meaning of the high spin state? 1, 2, 3, okay, 2, 5, right? You have to calculate in that manner, and if you know, then you know. It is 0.6, it is 0.4. If you multiply that value of 3 with this one and 2 with this one, right? So this will give you 1.2 and minus 1.2, that will give you 0, CFSE 0. So the electronic configuration is for this one is actually 3 and 2. That means option D is looking the correct answer in that case. Okay, there is no problem in that. Okay, so it is 0.4 of delta O, negative you can write here, right? And it is 0.6 of delta O. So if you take the difference, then you can multiply 0.6 by 2, 1.2, you can multiply 0.4 by 3, negative 1.2, this will give you the 0. Okay, now moving to the next problem. Which of the following cations is colorless in the aqueous solution? So again guys, it's a very simple problem. I am not going to give much time to this particular problem. Zinc 2 positive ion, right? So you know zinc is having, see, if you see here, zinc atomic number 32. Okay, when it is in +2 oxidation state, that means 28 electrons. 28 electrons means 3D10 system. Okay, 3D10 system means no electronic, no DD transitions. Okay, no DD transitions. So it would be colorless. It would be colorless. Okay, now moving to the next problem. Which of the following cation is colored? Okay, fine. See, you can actually check the options here. Copper positive. Copper is 29. It is 28. That means 3D10. No DD transition, colorless. Okay. Zn2 positive. You have already seen. It's a colorless. Okay. Titanium 4 positive. Titanium is 22. Okay. And when loses 4 electrons, it is having only 18 electrons, so it's a D0 system, so it is also the colorless. The only thing which you left with is nickel 2 positive. Nickel is 28, that means 26. 26 means it's a 3D8 system, so DD transition, so it is colored. So option D is looking the correct answer in that case. You can write in that manner. Okay, now moving to the next problem, what it says. The one with the largest delta, okay, highest crystal field splitting in that case. So first of all, you have to check the charge on the metal ion. So higher the charge, higher would be the your stability. So in that case, this is 3 negative actually. If you check, this is 3 negative, and I don't think it is actually right. Yes, it is 3 negative. Okay, so in that case, you see iron here is +2, iron is +3. It is in +3, it is in +2. Okay, and I already told you when you move down the group. So iron, ruthenium, osmium. Actually this is 3D, 4D and 5D, same group member, and down the group delta O increases, and when the charge is higher it is also increases. So you have to select this species. Option C is looking the correct answer in that case, because ruthenium in the last it belongs to it belongs to your 4D series, and it is also having the 3 positive charge over there. Okay, now moving to the next one. The CFSE for the high spin octahedral complex for a D6 ion. Okay, see guys, this problem is another very simple problem. High spin D6, 1, 2, 3, 4, 5 and 6. So 4 unpaired electrons are there. Okay, and if you calculate, okay, in that manner, I already told you 0.6, 0.4 negative, I already told you, okay, of delta O and delta O. Check whether I have written opposite or not. Okay, and how many electrons? 2 electrons, that means 1.2 with positive sign. Okay, and how many electrons? 0.8, negative 0.8. So the difference if you take, then it would be your 0.4 negative with negative sign. Okay, please check the sign actually. However, there is no meaning of this. So 0.4 is looking the correct option in that case. So if you check, okay, this option D is looking the correct one. Okay, please check the signs actually, right? So now you can check. Now we'll go to the next problem, and this problem is the CFSE for the low spin octahedral complex of the D7. Okay, now you have to make the D7 low spin 1, 2, 3, 4, 5, 6 and 7, and again the same thing, 0.6 and negative 0.4, okay, of delta O, 0.6 and here 0. So 0.6 would be the answer in that case. See, this is 0.6 multiplied by 1 electron only, it will give you the 0.6. 0.4 no unpaired electron, that will give you the 0. So your answer would lie somewhere in 0.6 range actually. So if you check here for this particular option, no, something is wrong. Low spin D7 system 0.6. Okay, sorry. How many electrons are there? 2 to 6 electrons. Very sorry. Multiplied by 6. Very sorry. It is multiplied. Okay. 0.4 into 6 of negative side, right? It will give you 6 4 the 24, 2.4, right? 6 4 the 24. Negative 2.4, right? And 0.6 is already given there. If you take the difference actually for this one, so this would be around, see, right, 0.6, okay, then 8, 1, 1.8 should be the answer in that case. Okay, and option B is the is looking the correct option. So this is how you can solve the various problems in that case. And guys, last problem I want to give, I haven't written that particular problem here, but somehow I have to solve 150 problems. So I am short with one problem, so I am giving you the one problem, right? If you have your F negative, right, this fluoride is having the very small size, in fact the smallest size in the ligand, excluding your hydride and all these things, but it is a weak field. It is weak field, but not a strong field. Please explain. So how we can explain? See, size is smallest, that means it should reach it should have actually very high ligand field strength, but it is not having that highest ligand field strength. So what would be the reason behind this thing? You can pause the video and you can think for a while how we can explain this thing. Okay, so if you have got your answer in your mind, then that's very good. If you don't realize that what is happening here, so I am giving you the idea in that case here. See, but basically in case of the fluoride happens actually, right? With a fluoride ligand, it is having the p pi d pi repulsion. It is having the p pi d pi repulsions. I hope you understand what is the d pi p pi repulsion. Okay, and whenever the d pi p pi repulsion is there, then the delta O reduces. That means the crystal field splitting reduces. Okay, basically the p pi d pi repulsions are responsible for relatively low ligand field strength of the halide ions, not only the fluoride ion but all the halide ions. Why they are having the low strength? Actually due to this d pi p pi d pi repulsions. So guys, this 32 problem I have solved here in this particular example, and this completes my 150 question series on coordination chemistry. I hope you like the series, so please go through the series, and I will combine all the lectures 150 problems all together in one lecture of 5 to 6 hours, and then you will be enjoy more to solve such kind of the problem. If you feel you are not able to understand some of the problem, then you can write in the comment section, right? I will definitely happy to solve your query to the best of my ability. I know I have skipped one or two problem in that case actually, right? Ionic radii and all these things. If you don't find the satisfactory explanation in anywhere, then you can write in the comment section. Okay guys, so that's it for today guys. Thank you very much.